Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 1. Welcome! This is the first in a series of videos that make up a complete course in Software Defined Radio. Software Defined Radio, or SDR, is the use of digital signal processing to implement radio functions. With SDR, we can create transmitters or receivers for virtually any radio signal in software with a single piece of hardware in a general purpose computer. This is HackRF One. It's a software-defined radio peripheral that connects to your computer over USB and allows you to transmit or receive signals over a very wide range of frequencies. You can think of it kind of like a sound card. A sound card enables your computer to produce or record arbitrary sounds. And a software-defined radio peripheral like HackRF allows your computer to produce or record arbitrary radio signals using an antenna instead of speaker and microphone. This course is an outgrowth of my training class that I've been teaching for several years. It's a 2-day class that I teach at information security conferences around the world. And it's a very intense course in which I introduce people to software-defined radio and teach them the basics that they need to get started implementing digital radio systems, and in particular to probe the security of systems that use radio. I came to the field of software-defined radio myself because I was doing wireless security research, and I found SDR to be an incredibly valuable tool in my research. And because I'm used to teaching people in the security community, and I come from a security background, I'll be taking somewhat of a security angle at times in this course. But you don't have to be a security professional to get something out of this course. You just have to be somebody who's interested in learning about software-defined radio. I take an approach that I call software-defined radio for hackers. And you may or may not think of yourself as a hacker, but if you're someone who enjoys coming up with creative solutions to technical problems, then you're a hacker in my book, and I think you'll enjoy this course. I assume that everyone has some background in computer programming, or that you can learn that elsewhere. We won't do a lot of programming in this course, but at times I'll refer to Python or C++, and we might look at a little bit of source code. At times there might be an exercise where I ask you to write a small program that does something. But if you're not a computer programmer, don't worry. As long as you're somebody who's generally good at making computers do things that you want them to do, I think you'll get a lot out of this course. I am very excited to be putting this course online. I've been teaching a 2-day class, as I mentioned, for some years now, and this is an opportunity for me to take that content, put it online under an open content license, and make it available to the whole world. In addition, it's a chance for me to take my time with the content a little bit more than I'm able to in a 2-day class. So as I produce this course in installments over time, eventually I hope that it will contain even more content than my in-person training consists of. Of course, it's great to be able to come and sit down and devote 2 whole days to learning SDR with a group of like-minded individuals, and it's wonderful to be able to ask questions in person, but hopefully I'll be able to, over time, answer everybody's questions throughout the content of the series as I go from one video to the next. I'm going to keep this pretty informal. I'm doing, I hope, most of these videos in 1 or 2 takes, and so they may not be as polished as they could be, but it allows me to get the videos out faster to people. If I make any terrible errors, I will be sure to correct them on the website. Now, there is a website for this course. If you happen to find this video by some other means, go to greatscottgadgets.com/SDR. That's the website for the course, and you'll find a page for each lesson as I post each lesson. Each lesson will have its own page, and the video will be on that page, and some additional text will be on that page. If there are any errors, In the video, I'll be sure to spell them out in the text of the page and correct them there. And I will also have information about the exercises and homework on the page. And then in the subsequent lesson, we'll talk about the homework, and I'll have some more information on that page's or that lesson's page. So I'm going to keep it pretty informal and try to teach it in the same way that I teach my in-person class as much as possible. I'm going to use some blackboarding and some video of me and quite a bit of screen capture as we go through different demonstrations and exercises. And primarily what I'll be using for the exercises is GNU Radio Companion, which is a graphical user interface for GNU Radio. And this course is called Software Defined Radio with HackRF because it's primarily about software defined radio, and we're using HackRF for many of the exercises in the class. But a lot of the course is really going to be using GNU Radio, and the true nature, the core of the course is really about the fundamentals of digital signal processing that you need to understand to be able to build flexible software-defined radio systems in the future. Now, you might have some hardware other than HackRF, and you can probably use that for this course. And you may not even have any hardware that is a software-defined radio peripheral, and that's okay too. You'll still be able to get a lot out of the course learning about GNU Radio and software-defined radio, and some of the exercises won't require any hardware whatsoever. But many of the exercises do require some hardware, so I encourage you to pick up a HackRF or some software-defined radio platform that you can use to complete the exercises in this course. Now, different platforms have different capabilities, and some of them you'll be able to use for one exercise, whereas another software-defined radio platform would be more appropriate for a different exercise. But the one platform that you can use for all the exercises in this course is HackRF. I'm going to now just get started with an exercise. Let's just build something in GNU Radio Companion and get started by doing what's often called the hello world of software-defined radio, and that is an FM radio receiver. This is GNU Radio Companion. In this exercise, we're going to use GNU Radio Companion to create a software radio that allows us to listen to an FM radio station. Now, GNU Radio Companion is a front-end graphical interface to GNU Radio. GNU Radio is a software framework that allows us to create programs in C++ or Python, and GNU Radio Companion is a tool that actually automatically creates Python programs that are software radio programs. So what we're going to do is create in this big blank area a visual flow graph of how we want our program to work, and then we're going to click this button up here, which will generate some Python code and run it for us. So even if you don't know any computer programming, GRC, or GNU Radio Companion, does all that for us. I'm going to start by taking a block from this list of blocks on the right. Underneath sources, I'll take an Osmocom source. And the Osmocom source is an abstraction layer that allows us to communicate with different hardware devices for software radio. And it's a source, which means it produces a digital signal that will be consumed by the next block in our flow graph. And so what happens is the source tells the HackRF to turn on in receive mode, and then it streams samples over USB from the HackRF and then out this output to the next block in the flow graph. Now, I'm not going to go into great detail about how every block in this flow graph works, but what I hope you'll get out of today's exercise is some familiarity with GNU Radio and GNU Radio Companion, and just a little bit of comfort in how to manipulate these blocks and put them together and execute a flow graph and actually build something with GNU Radio. In future lessons, we'll talk much more about the details of why this flow graph works the way it does, or the way it will when we finish it. The next block I'd like to use is under Instrumentation, WX. It's the WX GUI FFT sync. And the FFT sync allows us to visualize the frequency components in a signal. I'm going to connect one output to the other's input, and that creates this directed line between them, this arrow between them. And you might have noticed that their titles, the titles of these two blocks just changed from red to black because their inputs and outputs have been satisfied. So we now have a complete flow graph, and this could be executed, but it wouldn't be very useful yet until we make a couple of changes. I'm going to first of all look at this variable over here, samp rate. 32,000 samples per second isn't very many. So let's go in here. I right click and select properties, and in this properties box I'm going to type 10 million, but it's hard to get the number of zeros right, so I'm going to type 10e6, which is exponential notation. What this means is 10 times 10 to the 6th power. So anytime you see an E6, that means millions, E3 is thousands, and so forth. So now you can see, since I typed 10e6, that value shows 10 million. And it also shows over here 10 million, and over here in this third block 10 million. The reason that those updated to 10 million is because if we look at their properties, their sample rate is configured to samp_rate, which is the name of this variable that I changed. So the variable allows us to change multiple things in one place. Anything that refers to that samp rate variable can be changed just by changing the variable block over here. Now, some other things I'd like to change in this Osmocom source. 100E6, that's 100 megahertz. That is in the FM broadcast band, but I'd like to tune right to the middle of the FM broadcast band, 97.9 E6. And I'd like to change this RF gain to 0, turn off the front end amplifier near the antenna in HackRF. We probably don't need it, and I generally like to leave that amp off unless I'm in a particular situation where I need to pick up a very weak signal. FM broadcast stations are typically very strong signals unless you live a long way from any transmitters. These two gains are good defaults, so we'll leave them, although in the future you may adjust them. Now, one change I'd like to make in the FFT sync is to go into Properties and turn Averaging on. That just makes it a little easier to see the FM radio stations individually in the FFT plot. Now notice I right-clicked and selected Properties, but there's a handy keyboard shortcut. I encourage you to get familiar with all the different keyboard shortcuts in GNU Radio Companion, although I will try to remember not to use them while I'm recording videos so that it's more clear what I'm doing. You can also get to the properties simply by double-clicking on a block. So at this point we have a complete flow graph, and it doesn't let us listen to FM radio, but it at least lets us run the flow graph, visualize the signal, see that something is happening, and validate what we've done so far before we complicate our flow graph further. So I'm going to click this execute button up here, the gears, and the first thing that will happen is that it's going to prompt me for a file name. I'll call it lesson 1, and notice it has a .grc extension for GNU Radio Companion. What this file is a representation of the flow graph. So it contains a listing of the different blocks and how they're configured and how they're connected together. This is one file that GNU Radio Companion creates, but then as soon as I save this, it's automatically going to create a Python program in addition to this .grc file, and the generated Python program is going to be executed. So I save that, it creates Python and executes it, and here we have a nice FFT plot that is showing us live radio information coming from the antenna through the HackRF, through USB, through this Osmocom source, and into our FFT sync. Now you can see several megahertz of bandwidth being represented here, and so each of these major peaks is a different FM radio station. You can see that their frequencies vary from -5 megahertz to +5 megahertz. And we'll talk a little bit more about what that means in the future, but for now you can think of this 0 point as being the center frequency of 97.9 million. Well, it would be nice if it actually displayed 97, 98 million and so forth. So let's just adjust our flow graph so it does that. I'm going to kill the flow graph by pressing this stop button or clicking this stop button instead of by closing the foreground window, because that will make sure to shut things down cleanly so the HackRF is back to its default idle state. So I'd like to set this baseband frequency right here to something other than 0 in the FFT sync. I'd like to set it to 97.9 million. And if I go into the properties, I could just type 97.9E6. But instead of having multiple blocks that all refer to 97.9E6, I'd like to use a variable. So I'm going to create a variable called center freq for center frequency. And now you can see the FFT sync got angry at me because the center freq variable doesn't exist. So I need to create a variable. And I'll call this variable center underscore freq to agree with the other block, and give it a value of 97.9 E6. Now you can see the FFT sync is happy and it agrees with the Osmocom source. However, the Osmocom source still says 97.9, and I would like it to say center freq. That shouldn't have any immediate effect. It should still be set to the same default value, but now if I change it in this one place, it will update in both these other places, and I'm less likely to make an error in the future if I ever want to adjust that parameter. So now if we execute the flow graph, it should look exactly the same, except that the frequencies here show the actual frequency in megahertz that we've tuned the HackRF to. And we can see if you hold the mouse over one of these prominent frequencies, in my neighborhood, 96.5 is very strong, and 98.5 is very strong. And you might notice that the stations that are strongest in your area may not be the ones that you're familiar with. You might be used to listening to one of these over here or there, one of these weaker signals, but you probably live closer to the antenna that is transmitting the stations that appear more prominently in your FFT plot. So now let's see about actually listening to one of these stations. And the first step in doing that, the first step that I'd like to take, is to actually shift one of these frequencies to center. So the center of the plot, or the area what was formerly called 0 megahertz or 0 hertz, that's where I'd like to say move this 96.5 station over to center. And there are a couple of different ways I can do that. I kill the flow graph with the stop button. And now you might think I'll just change my center frequency, but I'd like to show you that I can do this in software instead of actually tuning the hardware to a different frequency. And in the future we'll see why that might be valuable to do it that way. I'm going to use a math operator, a multiply. This simply does a point-by-point multiplication of one digital signal to the other digital signal. Each of these lines going from one block to another I think of as a signal or a digital signal. And really a digital signal is just a sequence of numbers that streams from one block to another. Now I'm going to produce a signal from a signal source under waveform generators. This is a synthesized signal that I'm just producing in my CPU and multiplying that signal point by point against the signal that comes from the HackRF. Now the frequency that I want to set this to is actually the amount of shift that I want, or the difference in frequency between the center frequency and my channel frequency that I'm interested in. So I'm going to create a variable called channel freq. I'll do that by copying and pasting one of these variable blocks, and then in the properties I'll change its name to channel underscore freq, and I'll give it 96.5 E6 as a value, So that'll tune to 96.5 megahertz. Oops, I think I made an error. I was supposed to say channel freak. Now, over here in the signal source, I would like this frequency to be center freak minus channel freak. Now you can see I can type an expression here using multiple variables. You can actually type any Python expression, which is wonderful and terrifying. But remember that GRC is producing Python code for us, so we can influence the way it does that by doing things like using variables and Python expressions in some of the parameters for these different blocks. Now I'd like to verify that this multiply is doing what I want, so I'll take this FFT sync and copy and paste it. And assuming it works properly, the center frequency of this FFT should be channel freak. So I will set this value baseband frequency to channel underscore freak. And that will just change the ruler on the FFT sync to what we think it should be. Now let's execute this and see if it looks the way we want it to. Now we have two FFT plots, and the one at the bottom is the one we had before. And you can see 96.5 is off to the left. But the one at the top, everything's been shifted over 1.4 megahertz to the right. And now 96.5 is centered in our display. So if we had set that baseband frequency to 0, we should see 96.5 right at 0 hertz, which is right where I want it. Now I'm going to do some things to get ready to actually demodulate this station, this signal, and turn it into audio. The first thing I'm going to do is filter it. I'm going to go up to Filters, select a low pass filter. It's low pass because I want to pass frequencies in the vicinity of 0 hertz. I'll connect my output of my multiply block to the input of the low pass filter, and I'm going to give this a cutoff frequency of 75 E3 or 75 kilohertz and a transition width of 25 kilohertz. And I'm also going to decimate. Now, the amount of decimation that I want is related to the amount of bandwidth of the signal that I'm interested in. And obviously we have a lot more bandwidth than we really need. We're picking up multiple radio stations over many megahertz of bandwidth. And I'd like to just pick one out, and I don't want to waste my CPU time dealing with a lot more samples than is necessary to describe that more narrow bandwidth. So I'm going to create a variable here, I'll copy and paste again, called channel width. And the width of a FM radio station is 200 kilohertz or 200 E3. So I'll set that channel width to 200 kilohertz, and then I'm going to set the decimation of my low pass filter based on that channel width. Now decimation is the process of reducing the sample rate. So I'm going to start with the high sample rate, and then I'm going to divide that sample rate down, and the amount that I divide it is the amount of decimation. So I'd like to call this samp rate divided by channel width, which should be 10 million divided by 200,000. Now if I click OK, it actually gets angry at me, and the reason it gets angry might not be really obvious at first, but it's because this particular block only knows how to decimate by an integer number. And in Python, I've created some floating point numbers, but I can restrict this to integer values by putting it in an int function, like so. Now it's happy, and of course 10 million divided by 200,000 is in fact 50. So this value is what we expect. What's going to happen is we'll get 10 million samples per second into the low pass filter. It will divide that sample rate by 50, and it will spit out 200,000 samples per second. Now the next thing I'll do after a filter is a resampler, and I'm going to use a rational resampler. Now this might seem a little funny because I'm changing the sample rate again. I just changed the sample rate here, and now I'm going to change the sample rate again, and I'm going to change it by a ratio of 12/5. I interpolate by 12 and decimate by 5. And the reason I'm doing that is because 12/5 is not an integer number. The low-pass filter was only able to decimate by an integer number, and now I want to adjust the frequency, adjust the sample rate to something that is not an integer relation. It's a rational relation. So I need a separate block to do that for me. And then I'm going to feed that into the heart of the flow graph, the actual demodulator that turns the radio signal, or the complex baseband signal, which is what all these blue things are, into an audio signal, which is this orange output. I'll connect my rational resampler to the WBFM receive block, and then I need to configure it a little bit. Now WBFM stands for wideband FM, and that's a name for the type of modulation that FM broadcast stations use. This wants to have two parameters filled in. One is the quadrature rate, and what that's referring to is the sample rate of the input, which should be 480,000. And then the audio decimation is the amount that this block is going to decimate further. So if you do the math, you can see that most of the flow graph is operating at 10 million samples per second until we get to the low pass filter. 10 million divided by 50 is 200,000. And then 200,000 times 12 divided by 5 is 480,000. 480,000 divided by 10 is 48,000. We're actually going to use an audio sample rate of 48,000 samples per second, which is a very common sample rate supported by pretty much every sound card. So I'm going to go to audio and take an audio sync, and you'll see that this can connect directly from there to there. Everything's happy except we don't want this to be set to sample rate. We want it to be set to 48,000. In some ways, this is a very complicated flow graph for its size because it has so many different sample rates. We have one sample rate, two sample rates, three sample rates, 4 different sample rates in a single flow graph. And that can be very confusing. It's one of the most difficult things to get right, or one of the easiest things to make a mistake is in making these rates and ratios not match up with one another. Although using variables can help with that. For example, the way I used a variable in the low-pass filter divided by another variable. Now at this point, this should actually produce audio. And I'm going to disable one of these FFT syncs because I really only need one way to visualize this signal at this point. The way I disabled that was by hitting the D key, but you can do it by right-clicking and selecting Enable or Disable, or using these buttons up here. So let's listen to radio, see what happens here, see if this works. There we go. I'm listening to a radio station. Now, you might not have been able to hear that, and we can adjust the level of the audio. The way we can adjust that is simply by multiplying the signal that goes into the audio sync. I will use math operators, multiply. I'm not going to multiply one stream by another. I'm going to multiply by a constant. So I'll use the multiply const block. I'll put it in there between these two. And you can see that these arrows are angry because I have a type mismatch. See the orange to the blue to the orange. And I can fix that by going into the properties of the multiply block and changing it to a float IO type. Now it's happy, but it's going to be multiplying by 0. It would be nice to be able to multiply by 1 or 2 And what I would like to do is actually be able to adjust my audio level, my volume, in real time while the flow graph is running. So I'm going to go to GUI widgets, WX, and select a WX GUI slider. I'll call this slider audio gain, and I'll give it a default value of 1, which is no gain at all, a minimum of 0, and a maximum of, oh, how about 10? And that's probably more than I would want, but let's see what happens here. Now I'll take this multiply const block and set its constant to audio underscore gain. And now I should be able to listen to that radio station and turn its volume up or down. There we go. So now we can listen to a radio station, whichever frequency we tune in here by using this channel freak variable, and we can adjust the volume of that audio in real time. Now, this flow graph, you might have problems if you tried to run this flow graph and your computer isn't as fast as mine. Or maybe you're not using HackRF, but you're using something else. One thing you can do if the flow graph is choppy, or if you get a lot of O's, capital O's showing up down here, that is an overrun indicating that your computer is not keeping up with the stream of information from the HackRF. So maybe turn this down to 8 million or 4 million. And notice if I change that, if I change it from 10 million to 4 million, it changed here and it changed here. And also this decimation right here changed, which means that everything to the right of the low-pass filter is still operating at the same sample rates it was operating at before, but the low-pass filter is automatically adjusted because of the way that decimation property is based on sample rate. So all we have to do is change the sample rate in one place, and this should work. Notice I see a much narrower view. I only see this station 96.5 and a few others. I'm not seeing a broad view of many stations in the FM broadcast band. If you have hardware that only goes to 2 million samples per second, just set this to 2E6, and you can still, again, you can run the same exact flow graph, except now 96.5 is off to the side, and funny things happen. So you have to be sure that you set your channel freak to something that's actually within the band that is displayed here. So, for the last thing I want to try, I'm going to set the sample rate all the way up to 20 million, which is about the maximum that you can get with HackRF. And this may or may not work on your computer. It requires a lot of CPU power, and it also requires a very fast USB interface. Some USB host controllers are faster than others. Some of them are busy because they have internal USB devices connected to them, and so they're not able to give all the traffic or all the throughput available on the bus to the HackRF. But I'm going to try it and see what happens here. There we go. Now you notice I got some O's, some overruns, just when the flow graph first started up. And if you see that, that's not really a problem. What is a problem is if you continue to see O's, if overruns continue to happen while the flow graph is running. But now you can see I'm running HackRF with a simple telescopic antenna tuned to the FM broadcast band, and I'm looking at the entire FM broadcast band from 88 megahertz to 108 megahertz, and I can see every single FM radio station that is in my neighborhood. And notice that all this information is coming from the HackRF into the FFT sync, and then in software, we pick out one particular station. So we could actually pick out multiple stations and listen to multiple stations simultaneously. And that's one of the things I'd like you to do for your homework. Yes, there's homework. So here are the things I'd like you to do for homework this lesson. Number one is try out Pen2 Linux. I'm using Pen2 Linux for this demo. All you have to do is download the Pen2 ISO image, install it on a USB stick or a DVD, and boot your computer to that USB stick or DVD. And then you can run GNU Radio Companion and have all the software available to you that you need natively on your computer without having to install it yourself in your own operating system. Once you have Pen2 running and you've started GNU Radio Companion, try to create the same flow graph just like I did, and you might go through the whole lesson here and watch the video while you do that. And then try and update it in a few ways. One thing that I think would be really interesting would be to take something like this GUI slider that we use for audio gain and create a slider for the channel frequency so that you can adjust the channel that you're listening to in real time. That's one step that I think would be very interesting for you to try. And then the next step I'd like you to try is to actually listen to 2 radio stations simultaneously. And I'll be posting this information, a little bit of information about this flow graph, what I've made so far, and the actual exercise, the homework assignment will be spelled out in text on the website for this page, for this lesson at greatscottgadgets.com/SDR. So you'll be able to go to that website and look at what the homework is and get some tips. I'll probably put a hint or two in there for how to accomplish this. And in the next lesson, we'll take a look at what everyone's created, a flow graph that allows us to listen to 2 different radio stations at the same time. Well, that's a wrap for Lesson 1. I hope you enjoyed building an FM radio receiver in GNU Radio. FM radio broadcasts are, of course, analog radio signals. And in this course, we'll actually be spending more of the time talking about digital radio systems. But FM radio is a really easy thing for everybody to tune to the first time because FM radio stations are all over the world. They have a very strong signal strength, and it's easy to verify that you're picking them up. So I hope you'll complete the homework assignment that I gave during the exercise. Please take a look at the website text at greatscottgadgets.com/SDR, and if there are any corrections to the video or any additional information that you might need for the exercise, I'll be sure to post it there. And I hope to see you next time in Lesson 2. Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 2, DSP. In this lesson, we'll begin an experiment that will help us understand the mysteries of digital signal processing, or DSP. But first, let's review the homework from Lesson 1. The first thing I asked you to do was to download Pen2 Linux and give it a try. Because you can install the ISO image from Pen2 on a DVD or a USB flash drive and boot your computer from that ISO image, Pen2 makes it very easy to run all of the software that you'll need for the exercises in this course. Even if you already have the software running on a different operating system, I encourage you to download Pen2 and give it a try if you haven't already. One of the things that it allows you to do is compare the way your software works with the way it works in Pen2 and verify that everything is working correctly. Also, it's really nice to have a complete Linux distribution with all of the software that you need for software-defined radio in a small package. I personally always travel with a Pen2 ISO installed on a flash drive, and then no matter where I am, I can plug that flash drive into a computer and plug in a HackRF and do demos or show people how things work or just experiment. Now let's take a look at the remainder of the homework from Lesson 1. I asked you to take the flow graph that we made in Lesson 1 and enhance it in a few ways. Here's the flow graph that we created in Lesson 1. It's an FM radio receiver, and let's just make sure that it still works. Looks like it's working okay. Now the first thing I asked you to do was to add a slider to allow control of the frequency or the station that you're listening to. So I'm going to take my channel frequency variable and I want to turn that into a slider. I will just copy and paste this slider and call it channel freak. Now the original channel freak had a default value of 96.5 E6 or 96.5 megahertz, so I'll give that the default. I'm going to set the minimum to 89.9 or no, 87.9, which is right at the bottom of the FM broadcast band. I'm going to set the maximum to 107.9 E6. And it just works out that if I have 100 steps, I think that's going to be quite convenient for the number of radio stations and their channel spacing. Now I have an error in my flow graph. These blocks are angry at me because there are two things called channel freak. So I'll just delete this one, or we could disable it. And now let's see if this works. There's that other very prominent frequency, and this looks like it's working very well, and I can tune all the way to the top or the bottom of the band since I'm using 20 megahertz of bandwidth, or I have a sample rate set to 20 million. And this channel spacing nicely agrees with this 20 megahertz wide slider divided into 100 different steps. So now let's take a look at the second thing I asked you to do, which was to make this flow graph allow you to listen to two stations instead of one, two simultaneously. So in order to do that, I'm first going to delete this block, get it out of my way, and I'm going to just move things around a little bit so that I can just make room for what I want to do here. I'm going to take this FFT sync and move it out of the way. I'm going to put my multiply block up there and just kind of move everything closer together up near the top of the screen, hopefully allowing me room to do what I want to do. Now I have an audio gain control for this channel, and I have a channel frequency control for this channel. So if I want to be able to control both those things for my other channel, I should group those together. And now I should be able to copy and paste. Let's see, sample rate should be the same for both, center freak should be the same for both, channel width should be the same for both. Everything that I want to copy and paste is right up here. And actually I'm only going to have one audio sync because I only have one sound card. So I'll just take all this stuff and copy it, paste it. Now, my flow graph is starting to get a little bit more complicated, but if I take this output from the Osmocom source and run it to this new multiply block, it's a little hard to position everything so you can see all of the digital signals going from one block to the next. But now I have everything that I need, except this multiply const now goes to nowhere, and I'd like to combine it with the output of this multiply const. So what I'm going to do is go take a math block and add, and I'm going to simply add these two streams together. I'll get rid of this path by clicking on it and dragging away. Connect these two multiply consts to this add. I'll just scroll over here a little bit and then connect the add output to the audio sync. Now everything's happy except for a type mismatch. These have the floating point orange type, and this add block defaults to the blue type. So I'm going to go into the properties and change its type to float. Now everything's happy. However, I do want to go in and change a couple of things. Now notice it automatically renamed blocks for me. Like this one was called audio gain. This one became audio gain underscore 0. This one was channel freak. It became channel freak underscore 0. So I should probably rename things. And in fact, I'd like to rename things channel 1 and channel 2. So I'm going to go in here and change this one to audio gain 1 and this one to channel freak 1. And that will break some things. Now over here, I need to set this signal source to channel freak 1 and this multiply const to audio gain 1. And that should give you a clue of what we're going to do next. Let's set this signal source to channel freak 2 and this one to audio gain 2. I'll call this slider audio gain 2 and I'll call this slider channel freak 2. Now I think everything matches the way I want it to. The only thing that might be nice to change would be to have these not default to the same channel frequency. I'm going to set the second one to 98.5 because that was the other very strong signal that I have in my neighborhood. I'm also going to set the audio gain default to 0. So I'm only listening to one station when I start up the flow graph, and then we can verify what happens when I turn up the gain of the second station. Let's give this a try. Okay, I'm listening to one station, and if I turn up the audio gain for the other, that's the other station. If I turn them both up, it might be a little hard to listen to, but it gives you a little bit of an idea of what we can do by tuning around in software. And there you go. Now we have a flow graph that allows us to listen to two different stations simultaneously. And HackRF allows us to do that because it can give us 20 megahertz of bandwidth based on this sample rate. This 20 million samples per second maximum sample rate. And even if on your particular hardware you're not able to get 20 million samples per second, you should be able to get several samples per second. Several million samples per second. And that should allow you to listen to more than one FM radio station at the same time. We could even enhance this flow graph to let us listen to more than two stations. However, I would probably run into the limit of my CPU power, and also this flow graph would be overly complicated, but there are some ways that we could maybe outside of GNU Radio Companion make an array of blocks and that sort of thing to allow us to deal with many channels at once. We've just created a pretty complicated flow graph. There's a lot going on in there. And eventually in this course you'll learn the internals of every single block in that flow graph, how it works, and why the flow graph as a whole is able to accomplish the task of taking a radio signal and turning it into audio of two different FM radio stations without even retuning the front-end radio hardware. Now, I'd like to take a step back and think about the basics of digital signal processing, or DSP. You're probably familiar with the concept of an analog signal or a continuous signal, something that we draw as a continuously varying function over time. Radio waves and sound waves are examples of things that we typically think of as continuous signals. A digital signal is similar, except that it's made up of discrete values at discrete points in time, and it's typically drawn as a series of dots with stems extending to the horizontal axis. The horizontal axis is usually time. It doesn't have to be time, but for software-defined radio, we're almost always dealing with digital signals that are from the time domain, or at least originated as time domain signals. And I will sometimes draw these digital signals as a series of dots. I'll usually skip the stems, although they're traditional, just because they take more time to draw. And in fact, I'll often draw individual samples or individual values of the signal as an X instead of a dot, just because it's a little faster. Now I say sample because each value is often something that was arrived upon by measuring an actual continuous real-world signal, and that process is called sampling. So in HackRF, there is a sampler, or an analog to digital converter, that takes an analog waveform, samples it or measures it at discrete periods in time, and then gives us the value at each sample point. Now, every value is a number, so fundamentally, a digital signal is simply a sequence of numbers. And there isn't a whole lot to digital signal processing fundamentally. If you think about it, all it is taking sequences of numbers and manipulating them in various ways. However, there is a whole field of interesting algorithms and interesting effects of different ways to manipulate digital signals. And I think you'll find that the field is very deep, even though at first it may seem like it's a very simple thing. And to get us started in exploring the mysteries of digital signal processing, I'd like to start with an exercise. And we're going to expand on this exercise and have some questions about it for our homework for this lesson. I'd like you to open up a new flow graph in GNU Radio Companion, and you can do that by clicking this New button, or by going to the File menu and selecting New, or using the keyboard shortcut Control-N. Now we have a new untitled flow graph, and I'd like you to start with a waveform generator. This will be a signal source, and the defaults are fine. 32 kilohertz sample rate, or 32 kilosamples per second, that comes from this variable here. Cosine, 1 kilohertz frequency, an amplitude of 1. Now I'm going to run this through a throttle block that comes from the miscellaneous section, and connect these two together. And then we only need one more block in our flow graph to get started, and this will be an instrumentation WX GUI FFT sync, just like we use to visualize the FM radio signals. And the defaults for this block should be fine too. So this is a very simple flow graph to put together, and let's just start it up and make sure it works here. I'll execute the flow graph. It prompts me for a file name. I'll call it lesson2.grc. And here we go. The FFT shows us one spike, and that's all we get. For homework for this lesson, I'd like you to take this simple flow graph and experiment with it and answer a series of questions. Go to greatscottgadgets.com/SDR, and under Lesson 2 you'll find the detailed description, the list of questions that I'd like you to answer. And I think that this is going to open up a lot of doors to interesting questions and thoughts you might have about digital signal processing. In the next lesson, we're going to go through and try to make sense of what this flow graph does when we manipulate it in different ways. And this is really going to set the stage for several lessons to come in which we'll explore the mysteries of digital signal processing. So I hope you'll do the exercise, the homework for Lesson 2, and I hope you'll join us for Lesson 3. Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HackRF. Lesson 3, what is a decibel? Now I told you at the end of Lesson 2 that we would be going over the homework from Lesson 2 in this lesson, but I decided to put that off for one more lesson so that we could take a diversion and talk about decibels. You've seen decibels a little bit on the vertical scale of the FFT plots that you've looked at in GNU Radio Companion, for example, and we're going to use decibels throughout this course, so I want you to be comfortable with them. And the reason I want to take a whole episode to do this is because I see people make mistakes with decibels all the time. Even people who think they know what they're doing with decibels, people who should know what they're doing, make mistakes, and I don't want you to make the same mistakes. So let's just take a little time and go over the basics of decibels and get comfortable with how to use them. When people first learn about decibels, they're usually told something like a decibel is a logarithmic unit of ratio. And they're typically given a definition, a mathematical definition, something like 10 times the logarithm base 10 of a ratio A over B, or they're given a definition like 20 times the logarithm base 10 of the ratio A over B. Well, no wonder people are confused. Let's forget all that. I'm going to tell you the two fundamental things about decibels that you need to know to understand them. The first is that 1 decibel is 1/10 of a bell. In other words, 10 decibels, or 10 dB, equal 1 bell. Now the other thing you need to know is what a bell is. And a bell is a description of the number of orders of magnitude, or powers of 10 of a ratio. So if a ratio is 10 to 1, that's 1 order of magnitude, so it's 1 bell. If a ratio is 100 to 1, that's 2 orders of magnitude, or 2 bells. If you want to put it in mathematical terms, I would say that the ratio A over B is equal to 10 to the n, where n is a number of bells. Let's do an example. Let's say I'm 2 meters tall. Okay, that's a bit of an exaggeration, but we'll go with that. And let's say my brother is a giant and he's 20 meters tall. Now, how much taller is my brother than me? Well, 20 meters over 2 meters, that's a ratio of 10 to 1. That's 1 order of magnitude, or 1 bell, and there are 10 dBs, or 10 decibels in every bell, so he's 10 dB taller than me. What if he's 200 meters tall? Well, 200 over 2 meters, that's a ratio of 100 to 1. So how much taller than me is he? He's 100 times taller than me. Or he's 2 orders of magnitude taller than me, so he's 2 bells taller, or 20 dB taller, because there are 10 dB in every bell. What if he were 2,000 meters tall? 2,000 over 2 is a ratio of 1,000 to 1. That's 3 orders of magnitude, so he's 3 bells taller, or 30 dB taller. Now you kind of see how this works. When we add a bell, we multiply the ratio by 10. Adding or subtracting bells or decibels is the same as multiplying or dividing the ratios themselves. And this is why decibels are handy. Now, one reason they're handy is they allow us to describe quantities that vary widely over many orders of magnitude. The other reason they're handy is that they give us mathematical shortcuts. They let us add or subtract instead of multiplying or dividing. Now, here's a trick that you should know. Everybody should know that 3 decibels is approximately a ratio of 2 to 1. It's a very close approximation. And of course, you know that by definition, 10 decibels is equal to a ratio of 10 to 1. Using those two things, we can actually compute all sorts of different numbers in decibels. So, for example, let's say my brother is 4 meters tall. Well, he's 4 meters versus 2 meters. How much taller is he than me? He's 2 to 1, or 2 times taller than me. How many orders of magnitude is that? Well, it's not obvious how many bells that is until you think about your little shortcut. A doubling is 3 dB. So we just kind of skip the bells step there and say, oh, that's a doubling. We recognize that as being 3 dB. Or I would say that he's 3 dB taller than me, or I would say that he is 3 dB mics in height. That's his height, is 3 dB mic. And it's important to designate that what you're relative to here. And this is one way to do that. A similar thing you might have seen before is something like dBm, which is a way to describe decibels relative to milliwatts. Now, what if he were, let's say, 40 meters tall? How much taller is he than me? Well, 40 meters over 2 meters, that's a ratio of 20 to 1. Or it's a ratio of 10 times 2 to 1. And remember, multiplying a ratio is the same as adding decibels. So from the 10, we get 10 dB. And from the 2, doubling, we get 3 dB. And we add these together. He is 13 dB taller than me, or his height is 13 dB mics. Okay, now what if he's only 1 meter tall? And I'm 2 meters tall. How much taller than me is he? Well, he's not taller than me, he's shorter than me, but bear with me here for a moment. If he's 1 meter tall and I'm 2 meters tall, then the ratio of our heights is 1 to 2, or you might think of that as 1/2 to 1. We're dividing instead of multiplying. And when we divide ratios, we subtract decibels. So he's negative 3 dB taller than me. Or you might say he's 3 dB shorter. But don't say he's negative 3 dB shorter. Say he's negative 3 dB taller. What's his height? What is his height in dB mics? His height is negative 3 dB mic. Now in this case, I'm actually 3 dB taller than him, and he's negative 3 dB taller than me. What if his height is exactly 2 meters, which is exactly my height? The ratio of our heights is 1 to 1, so how much taller than me is he? Well, he isn't any taller than me, is he? And if you think of it in bells, how many orders of magnitude is the number 1? It's 0 orders of magnitude. So he's 0 bells taller than me, which is 0 dB taller than me. And you would say that his height is 0 dB mic. So there are 3 things that people get wrong constantly with decibels. And I don't want you to make the mistakes, so let's go over them. The first is that they fail to tell you what the decibels are relative to. This is extremely important. If I were to tell you that my brother were 3 dB tall, that would mean nothing unless I told you he's 3 dB mics tall, or he's 3 dB taller than me. The second thing that people get wrong all the time is they confuse amplitude with power. Now, amplitude and power are 2 things that we're going to talk about a bit in this course. But for now, all you really need to know is that power is the amplitude squared, or it's proportional to the amplitude squared. This is where that discrepancy between the definitions of 10 times the logarithm base 10 of a over b, and that other definition 20 times the logarithm base 10 of a over b. The reason we have these 2 different definitions is because of amplitude versus power. And you don't really need to worry about it much as long as you're careful that when you're describing power, you only describe power. When you describe amplitude, you only describe amplitude. As long as you do that, decibels work out just fine. But if you mix amplitude and power together, then you run into trouble and you have to keep track of this complicated math stuff. The third thing that people get wrong is that they get their negatives wrong. So for example, what if they said a system has negative 5 dB loss? Well, if they're describing something that actually is lossy, then what they probably meant was that it had 5 dB loss, or they meant that it had negative 5 dB gain. This is similar to the problem of saying that somebody's shorter or taller, right? If my brother is negative 3 dB shorter than me, then he's actually 3 dB taller than me. Does that make sense? If he's negative 2 dB taller than me, then he's in fact shorter than me. It's a little bit confusing. You can see why people get this wrong a lot. You just have to be careful about negatives and double negatives. So, these are the things that people get wrong all the time. But before we finish, I want to go over an example of something that kind of shows why decibels are so useful and are commonly used. Here's an example. Let's say my brother is 2.512 times taller than me, and my mother is 5.012 times taller than him, and my uncle is 3.162 times taller than her. Now, how tall is my uncle? Or how much taller than me is he? Well, you could multiply all these out, but you probably need a calculator to do it well. Or it would take you a little bit of time on a piece of paper. But what if we were to rephrase this just in decibels? This same exact question would be, my brother is 4 dB taller than me, and my mother is 7 dB taller than him, and my uncle is 5 dB taller than her. How tall is my uncle? Well, 4 plus 7 plus 5 is equal to 16 dB. He's 16 decibels taller than me. And all we had to do was add in order to come up with that result. Now, if we want to know that result in the number of ratio instead of in decibels, then we'd take that 16 and divide it into 10 plus 3 plus 3, right? That's equal to 16. And we would say, oh, from the 10, we get a 10 multiplying by 10. From the 3, we get multiplying by 2. Remember, 3 dB is a doubling. And from the other 3, we get another doubling. So he would be 40 times taller than me, a ratio of 40 to 1. And if I'm 2 meters tall, then he's 80 meters tall. But most of the time, and this is part of the reason decibels are so useful, is that people don't even bother turning them into actual ratios. They just use a computation like this to describe a system in dB. You might have something like, maybe with your HackRF, maybe you have an application where you want to transmit a signal through a directional antenna some distance, and you connect the output of the HackRF. Let's say the output is at 5 dBm. Remember, that's decibels relative to milliwatts. And then you're going to connect it to a filter, a bandpass filter that has an insertion loss of 3 dB. Now, you'd actually want to subtract 3 dB because it's a loss. You're subtracting instead of adding. And then it goes through an amplifier that adds, let's say, 12 dB. And then you're running it over a long cable that has 2 dB of loss. And then you're connecting it to your antenna. So now you want to know exactly how much power there is at the antenna. Well, 5 minus 3, and then plus 12, and then minus 2. What is that? That's 12 dBm. See how that dBm over here ends up over here? Because all we did was change it by ratios, and we know exactly how much power there is at the other end of the connection. So this is a very common type of computation that's done in the RF world, and you can kind of see why dBs are helpful here, because we're constantly adding we're constantly multiplying or dividing these ratios, and so decibels allow us to just add or subtract instead. Now, you don't have to absolutely master decibels in order to participate in this course, but I want you to be a little bit comfortable with decibels and know that when you see a big number in decibels, that's a tremendously large number if you think of it as an absolute ratio, for example. And even though you don't have to master dBs, you actually could master dBs. And there are just these important things that you need to know, like a decibel is a unit of ratio, adding decibels is multiplying. And then you need to know those little tricks. 3 dB is 2 dB, and of course, by definition, 3 dB is a ratio of 2 to 1, and 10 dB is a ratio of 10 to 1. But you can actually completely master decibels if you want, and actually be good at computing any number of decibels in your head. And I'm going to show you a little trick for how to do that. And this is an exercise that I'd like you to do for the homework for this lesson. What I'd like you to do is make a table. And first, I actually want you to do this on a piece of paper. Write down one column on the left, starting with 0 dB, 1 dB, and then keep going. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and keep going all the way down to 30. Then I want you to make a column to the right, and starting at 0 dB, write down the number, the actual ratio. So 0 dB is, of course, a ratio of 1 to 1 by definition. And then skip down to 3 dB. What's that? Well, it's approximately a ratio of 2 to 1. And now skip down to 6 dB. That's 3 more dB, so it's a ratio of 4 to 1. Then go 3 dB further. That's a ratio of 8 to 1, of course, because we're doubling again. Now go 3 dB further. That's a ratio of 16 to 1, and you're starting to see the pattern here. Now, if you're a computer person, you actually have an advantage in learning decibels because you probably know powers of 2. And all you need to know are some powers of 2 to fill out this table. And after you've gone through all of these by threes, then take a look at this 10 decibels. Well, you know what that is. By definition, that's a ratio of 10 to 1. And then if you go 3 dB further than that, what's 3 dB more than 10 to 1? Well, it's a doubling of 10 to 1, so that's 20 to 1. And then if you go 3 dB further than that, that is a ratio of 40 to 1. You're doubling it again. You see how now I'm going through powers of 2 again, except now they're powers of 2 times 10. Now, if you look at the exercise of the homework assignment actually written on the web page, greatscottgadgets.com /SDR, I actually guide you through how to fill out this table, and I tell you a recommended order for you to go through and fill out this table. And I think you'll find as you go through it that you're able to very easily come up with a ratio for every single line in the whole table. And just by knowing some powers of 2 and knowing some simple rules about decibels, like what 3 dB is and what 10 dB is, you can fill out this entire table and compute any whole number of decibels and turn that into a ratio.
Isn't that a neat exercise? I hope you'll enjoy filling out the rest of the table, and once you do have it completely filled out, I would like you to think about one question, and I think you'll be able to answer this question by looking at your table. The question is, exactly how much error is there when you use the 3 dB approximation for a doubling? So think about that a little bit, and I hope I'll see you in Lesson 4 when we do go over the homework from Lesson 2. Hi, I'm Michael Lossman of Great Scott Gadgets, and this is Software Defined Radio with HackRF. Lesson 4, Mysteries. Sometimes in this course, I'll explain a concept and then ask you to exercise your understanding of that concept. At other times, I'll give you an exercise of discovery with a very little explanation beforehand. And the Lesson 2 homework was one of those times. I hope that you were able to learn a thing or two from the Lesson 2 homework, and I also hope that it was something that could bring more questions to your mind. Today I'd like to go through that homework together and see what we can learn about GNU radio and about digital signal processing.
For the Lesson 2 homework, I asked you to create a flow graph that looks like this. It has a signal source, a throttle block, and an FFT sink. Let's run this and make sure it works. And we have a single peak displayed in the FFT plot. Now, the second thing I asked you to do, question 2, was to answer the question, does the flow graph behave differently
if you remove the throttle block. Well, one way to do that is to disable the throttle block, but then we have to connect these two directly together to satisfy their input and output. Now, I can't actually demonstrate this running for you very well, and I'll tell you why in just a second, but you may have noticed some different things happen when you tried this. Now, some of you may not have noticed anything, but some of you should have noticed that the display perhaps did not work correctly in the FFT sync. You might have had applications time out. In extreme cases, I've seen people have to reboot a computer, but that's pretty rare. It depends on how many CPU cores you have and how your operating system is configured. Let me show you one way to measure what's going on here. I'm going to open up a window running the htop command. Htop is a handy program for measuring CPU utilization. You can see I have 4 cores here, 1, 2, 3, 4, and overall my CPU utilization is fairly low. It's all kind of under 50%, and the average here is well under 50%. And if I start this flow graph, you should see that the CPU utilization goes up a little bit. Now you can see that I'm using a little bit more CPU. My average CPU utilization across these 4 cores is a little bit higher than it was before. And if I stop the flow graph, you should see it go back down a little bit. It's not a very distinct change, but you notice that without the flow graph running, I sometimes have a core or 2 at under 10%. And with the flow graph running, I was using a little bit more CPU. Now, if I were to remove the throttle block or disable it and bypass it, then I would actually see this across all 4 cores go to about 99% or 100%. And all of my CPU utilization, all of my CPU power would be utilized. And most of it would be utilized by this flow graph. Now, the reason I can't demonstrate this to you is because the CPU utilization that I do have going on right now is for my video and audio capture. And if I chew up all my CPU in GNU Radio, then my video and audio capture don't work very well and I can't record this video. So this is a nice thing for you to try on your own and just verify using htop or your favorite performance monitoring tool. You can verify that running the flow graph without the throttle block uses all available CPU cycles. And why is that? Well, one thing you might experiment with is increasing the sample rate, the sample rate variable. If I were to increase this to, say, instead of 32,000, if I were to increase it to 32 million and still throttle it, then I'm using a lot more CPU power. Look at that. I'm using like 50% of my CPU or more. And the more, the higher you have this samp rate set to, the more CPU power you'll use. And the throttle block is the thing that actually controls the real-time sample rate. How many samples per second are processed by the flow graph, and how many samples per second are processed by your CPU. So if we disable that and connect these two directly together, this flow graph is no longer rate limited. This signal source produces samples as fast as it possibly can, and this FFT sync analyzes samples as fast as it possibly can. Now this may seem a little strange because the sample rate is configured right here in the throttle block. It's also configured right here in the signal source, and it's also configured right here in the FFT sync. But it turns out that this sample rate here isn't treated the same way by the FFT sync as this sample rate configuration in the throttle block. And this sample rate in the signal source is not treated the same way as the throttle block handles its sample rate. Only the throttle block affects the real-time rate of this flow graph. I find that very interesting, and it's something that's a quirk of GNU Radio that is important to learn, that this configuration of sample rate
doesn't mean the same thing to every single block. Now, hopefully nobody had to reboot their computer to participate in that exercise, but if you do have trouble, you might just try adjusting the sample rate variable instead of actually removing the throttle block completely. Now, question 3. Does the FFT sync correctly indicate the frequency produced by the source? I'm going to close my HTOP window here, and I've reset the flow graph to its default configuration with a sample rate of 32,000 samples per second and a throttle block in place. I run the flow graph and it shows me a single spike. Now this is the FFT plot is showing me the output from an algorithm called the FFT, and we're going to talk about the FFT a lot in future lessons, but for now all you need to know is that the FFT is an algorithm that analyzes some samples and tells us what frequencies are present in that chunk of samples. And it does this, the FFT plot does this repeatedly on its input and gives us a real-time display. Now in this case, the display is unchanging, and that's because the signal source is giving us the same samples over and over again. So it doesn't look like it's animated, but it actually is. It's just animated over the same data over and over again. So the signal source is set to a frequency of 1 kilohertz, and the FFT plot has a spike, and if we hover our mouse over it, it is right at 1 kilohertz. And if you look at this ruler down here, the ruler goes from negative 15 or so, maybe negative 16 kilohertz, to positive 16 kilohertz. And you can see that the peak, this very tall peak, is just to the right of center at 1 kilohertz, 1/5 of the way to this 5 marker. Now, the next question I asked is, what if the source and sink have different sample rates configured? Well, let's try something. Let's set the signal source to have a different sample rate. Now, normally I recommend that you always use a variable and have the sample rate the same through all blocks that are using that should be using the same sample rate. So here I'm going to intentionally violate that rule, and I'll set this, instead of setting it to 32,000, I'll set it to 10,000. And so now we have a mismatch between this sample rate here and this sample rate here. Let's see what happens. Now look at that. It looks very much the same, except this peak has moved over. Now this peak is at 3.2 kilohertz. It's closer to this 5 marker. Let's try a different sample rate and see what happens. If I set this to, let's say, 100,000, I'll add another 0. Now, oh, okay, now it looks basically the same, except this peak has moved closer to center. It's only at, what is that, around 300 and some hertz, not kilohertz. That's very interesting. It looks very much the same, except the peak has moved. Now, to understand a little bit better what's going on, I'd like to visualize this slightly differently. I'm going to use an instrumentation block WX scope sync. Now, a scope sync is like an oscilloscope. It shows you the value of every sample over time. The FFT sync is going through some complicated algorithm to determine what frequencies are present, and it goes through a lot more computation than the scope sync. The scope sync simply plots the values that it receives on the time axis, and so it's called a time domain plot, where the FFT is a frequency domain plot. The domain is what we see on the horizontal axis. Now I'll execute this flow graph with both these sinks in place, and now the part of the FFT plot is off the bottom of the screen, but you can see the scope plot up above, and you can see, sure enough, we have this cosine wave, this blue cosine wave that looks similar to what we would expect based on the fact that this signal source is producing a cosine. And there are some other things that are interesting to note about this. Now, one thing is that there are actually two waves. There's this blue curve, and then there's this green curve, and up here it shows those as channel 1 and channel 2. Now, where in the world do we get a channel 2 from? That's kind of mysterious, isn't it? I think we're going to need to explore that mystery in the future. Now, I want you to take a look a little bit at what it looks like if I set this signal source back the way it's supposed to be. I'll just set this to samp_rate, which is 32,000 samples per second. Now let's look at it again in the scope plot. You can see actually that we're seeing more periods of the cosine wave here. And I want to show you something, this marker. By default, the scope plot connects the dots. It connects every sample point with a line that links one sample point to the next. And sometimes that's very handy for visualizing a signal. However, it can be very deceptive. Remember that we're dealing with a digital signal here, and the digital signal only has discrete values at discrete points in time. It's not a continuous curve. So displaying it as a continuous curve can fool us into thinking there's something there that it's not. So I often like to select dot large, which gives me a dot for every sample point. And now, aha, we can see the individual values that are being produced by the scope sync. And if you count them, you could see if you count from this peak to this peak, you should find that there are 32 dots, or there are 32 samples per period. Now look back at the scope, the signal source, and you can see this sample rate is set to 32,000 and the frequency is set to 1,000. That's interesting. Let's try something slightly different. Let's try setting the sample rate to 16,000. I'll set it to 16E3. And now, if I execute the flow graph and change this to dot large, look at that. We have fewer dots per period, fewer samples per period. And there's actually 16 if you count them up here. 8 from here to here, and another 8 from here to here. There are 16 in a complete period. And notice that this ratio, sample rate to frequency, is 16 to 1. Interesting. What if we were to increase the frequency? Let's increase the frequency here to 2,000. Now the sample rate of our signal source is 16,000 and the frequency is 2,000. So that's a ratio of 16 to 2, or a ratio of 8. And if we look at our dot large, hey, look at that. We have 1, 2, 3, 4, 5, 6, 7, 8 samples per period. So it turns out that this signal source produces a number of samples per period of its cosine equal to this ratio of sample rate to frequency. Now, and we could probably make this plot look exactly the same, and notice that the FFT sync here shows a spike at 4 kilohertz, which really isn't correct based on this number. But remember that it says 4 kilohertz here, and let's just do something kind of wacky over with the signal source. We currently have a ratio of 8 to 1. So I'm going to just look at this for a moment and just invent a number. How about like, I just type some random keys on my keyboard. I'm going to copy and paste that up into here and multiply it by 8. Now remember, you can type any Python expression in some of these fields. So this should work. This should be 738.923 kilohertz with a sample rate that's 5 times that many. Even though these are really oddball numbers, notice that the ratio is 8 to 1 because I just multiplied one number by 8. And if we execute this flow graph, it should look quite familiar. We have 8 samples per period in the scope plot, and the FFT shows a single peak at 4 kilohertz. The FFT looks exactly the same as it did before. Isn't that interesting? And the reason it does is because all that matters here, all that matters to the signal source, is the ratio of sample rate to frequency. And that tells us a little bit about what this sample rate configuration means to the signal source. We know what it means to the throttle block. What it means to the throttle block is that's the real-time rate that this flow graph should run. And the way that it implements that is by taking some input samples and then only handing out taking those same input samples and sending them to its output, but it only doles them out to its output at a rate equal to this real-time rate of 32,000 per second. Now, to the signal source, the sample rate configuration means something different. The signal source doesn't care about real-time rates at all. All it cares about is the ratio between sample rate and frequency. And that tells it how many samples per period of a cosine wave it should produce. And it just keeps generating those samples as fast as the next input in the chain will take them. Now, there's one other sample rate configuration here in our flow graph, the FFT sync. There's also one here in the scope plot, but let's ignore that one for now. The sample rate in the FFT sync means something potentially a little bit different. So let us just reset this signal source to the original configuration. By the way, notice I tried to type 1K here. I'm going to show you what happens. I'll set my sample rate to samp_rate. If I type 1K, it doesn't like that. It gets angry at me. Now notice it uses a K as an abbreviation when it tells you what something is configured to. But when you actually type it in, you can type 1000 and then it'll say 1K here, or you can type 1E3 and it'll say 1K here. But if you type 1K, it gets angry. And that may seem a little silly because that is actually how it displays the correct value, but it is an incorrect way to configure it. And it tells you right here, value 1K cannot be evaluated. And the reason it can't be evaluated is because we're typing a Python expression. And 1E3 means something in Python, and 1000 means something in Python, but 1K doesn't normally mean anything to a Python program. So we'll set that back to its original configuration, a frequency of 1 kilohertz, sample rate of 32 kilohertz. And we'll run it through the throttle block into the FFT sync. Everything should run exactly as it did originally. And let's just verify that. We get a single spike at 1 kilohertz. Now, if I were to change the sample rate over here in the FFT sync, let's say I set this to let's do samp rate over 2. Let's see what happens now. Now look at this. I have one spike. It's just to the right of center. And it says the frequency is at 500 hertz. The frequency was divided by half. What if I set this to a much lower frequency, much lower sample rate, like samp rate divided by 10? Now, we run this again. We get this spike just to the right of center, but it's much lower. It says this spike is at 100 hertz instead of 1 kilohertz. And notice, however, that the spike has not moved with respect to center. Take a look at that. Look how it just goes just up to the right of that T in the title of the graph. If I set this back to its original state, samp_rate, we see, sure enough, that spike points just to the right of the T. It's the exact same plot. The only thing that changed when we changed the sample rate was this ruler down here, and then the numbers that we get when we hover our mouse over it are based on this ruler. Nothing at all changed except for the ruler. We could set a wildly tiny value here, for example. We could put a sample rate, I'm not even sure if this will work, but let's try a sample rate of 1 and see what happens. How about that? Now we get a graph that looks exactly the same. This spike is just to the right of center, but it's telling me that this frequency is well under 1 hertz. It's showing me millihertz on my scale. It's an absurd ruler, but the actual plot is exactly the same. So that tells you something about what the sample rate variable or the sample rate configuration means to the FFT sink. To the signal source, all it cares about is the ratio, sample rate versus frequency. To the throttle block, what it cares about is the real-time sample rate that it delivers its input samples to its output at. The FFT sink, what the sample rate means primarily is simply the ruler at the bottom, across the horizontal frequency axis. There's one other thing, however, that is a quirk of this particular block that you might want to know, and that is if we set it very high, if we set the sample rate much higher, let's say we set it to 1 million, and everything else in the flow graph is configured to 32,000. So now it's set to be much higher. If we run this flow graph, notice what happens here. We don't get anything. Aha! Now we got something. Now it looks exactly like it did at first, or with all the other configurations. We have a ruler that's absurd. It's based on that sample rate configuration. But the spike that we see looks in the exact same place. Nothing changed about the actual output here other than the ruler, and there was a little bit of a delay when this flow graph started up. And the reason there was a bit of a delay is because of the way this FFT sync is implemented with refresh rate. By default, the FFT sync displays one frame of information. Think of it as a video display showing you one frame of information 15 times per second. That's what the refresh rate is, 15 per second. And if you assume that you're getting 1 million samples per second and you want to display some information 15 times per second, one way you might implement that is by dividing 1 million by 15 and then taking that number and weighting that number of samples before you display one frame of information. And that's exactly how the FFT sync works. So there's actually two things that this sample rate variable affects when you change it on the FFT sync. One is the ruler, the horizontal ruler, and the other is this refresh rate, because the refresh rate is based on counting samples. So if this sample rate here doesn't agree with this sample rate over here, then the ruler is going to be all wrong with respect to this frequency. If this sample rate here in the FFT sync doesn't agree with this sample rate here in the throttle block, then the refresh rate will be all messed up. So three completely different interpretations of what that sample rate configuration means to these three different blocks. But long story short, if you set them all the same, things generally work correctly. And that's why we use a sample rate variable, and that's why when you open up a new empty flow graph in GNU Radio Companion, this is the one variable that it gives you for free. Before you build any other block, you'll always have a sample rate block, because it's so commonly used, it's so useful to have multiple blocks in your flow graph all configured to the same sample rate. And confusing things happen when things are not configured to the correct sample rate. So having a variable, having one place to change it in multiple configurations, allows us to do something like this: set this from 32 million to 32,000, change it to 32 million, and now all of them agree with each other and everything should work just fine. And the only thing we see difference is that this says megahertz instead of kilohertz, but otherwise everything should work just correctly. And so, long story short, use a sample rate variable, make sure that everything is configured properly using that variable. Now, we've explored a little bit with the scope sync, and it's interesting to note that sample rate means something to the scope sync too, and basically it's going to be the same type of story as we see in the FFT sync. So, Question 3 was, does the FFT sync correctly indicate the frequency produced by the source? Yes, it did. It showed a spike at 1 kilohertz. And if the source and sync have different sample rates configured, it does not correctly indicate the frequency, but it does do the exact same analysis and produce the same looking output, just with a different ruler. So question 4. What happens if you configure the signal source with various frequencies between 0 and 16K, or 16 kilohertz? To do that, I would like to use I bet you know what's coming, I would like to use a GUI widget WX GUI slider. And I'm going to call this slider freak for frequency. Now I'll set it to a default value of 1000 because that was my original value. And I'll give it a minimum and maximum of, let's say, 0 to 16,000. Now it's happy with those parameters. 100 steps should be fine. And then I just want to go into my signal source and tell it, instead of using a frequency of 1000, it'll use a frequency of freak, referring to that variable. So it should still say 1K because that's the default value of this slider. But if I execute this flow graph, and I'll just disable this scope sync again for now. Now I have something a little unexpected. Oh, you know what I did wrong? This peak looks like it's right at 0. It's just very, very close to 0. The reason is because I set my frequency to 1K, but my sample rate is set many times that at 32 million. So I forgot to change this back to 32E3 for this part of the demo. Here we go. Now everything's back to its original state, except that I have a slider for frequency. And so now we should see, there it is, that spike just to the right of center at 1K. And if I move this frequency slider, sure enough, the FFT analyzes the signal and is able to tell me exactly the frequency that's being produced by the signal source. I can move it around between 0 and 16 and everything works fine. If I take it all the way down to 0, I see a spike dead center at 0. So that tells us a little bit of something interesting. It tells us what the signal source is doing, or it tells us anyway that the FFT is actually changing its output depending on the changing input. And you can see a couple of interesting things that happen. One is, watch the delay as I move this from left to right. Do you see how it lagged? The FFT lagged behind my slider? Just a little bit. And that's because of buffering in the flow graph. There are samples waiting here to be throttled. There may be some samples waiting here for the next refresh period and so forth. There's a little bit of buffering that goes on at every little step along the way. Every input and output, every connection in the flow graph has a little bit of a buffer. And also you may notice that the flow graph looks a little, the FFT output, when I'm stationary, when I leave the slider in one place, it looks like one very tall spike. But while it's moving, funny things happen. And you see this wideband stuff going on over many kilohertz of bandwidth instead of just this narrow spike. And that's because of little changes that happen when there's an instantaneous change. If I change this by typing on my keyboard, you'll see an abrupt change where there were kind of two peaks all of a sudden. And if I move it with the slider, I'm actually doing that same thing except many, many times in a row. As the slider goes through each step, it makes an abrupt change in the signal. And the FFT has, I don't want to say it has a hard time analyzing it. It just is given data that are not consistent, that are not of a consistent frequency because they're changing. So during that little transition period, while the FFT is getting maybe just a little bit of one frequency and then a little bit of another frequency, you see a lot more frequencies appear here in the FFT plot. But then while it's stable, you see one spike. I think that's kind of interesting. Now, the next question, question 5, is what happens if you specify frequencies greater than 16K? So I'm going to go into my slider here, and I'll change its maximum value from 16,000 to 50,000. How about? And let's see what happens. So it looks the same when I start up with it configured to 1K. I can slide it down to 0. It looks fine. I move it up. I move it up. It looks fine all the way up to, let's see, 16. And then as I keep going, hey, it's the Atari effect. It wrapped around like playing asteroids. And it went past 0 again. It keeps going to the right as I move my slider to the right. And as I keep going, well, look at that. It wrapped around again. If I move my slider back to the left, there we go. It's doing the exact opposite motion it did last time as I was moving it to the right. And as when we get back down below 16K, things look normal again. This is very mysterious, isn't it? I find this quite interesting. How does this happen? We have this peak that moves, and when it hits 16K, you can actually see just a little bit of blue here and a little bit of blue here. It's actually kind of simultaneously positive 16 kilohertz and negative 16 kilohertz. And when we move past it, we're into the negative frequencies, whatever that means. And as I move up, I think if I get to exactly 32K, it looks like it's at 0 again. And now as I increase, if I were to increase it to, say, 37K, which is 32 plus 5, now it's at 5 kilohertz. Same thing as if I set this to 5 kilohertz. And notice how similar it looks. We have this tall spike. It goes just below 0 dB, it looks like. And if I just type in the value 37K, look at that. Nothing changed at all. The slider moved, but the FFT output, or the FFT analysis of the output, didn't change at all. Let me try that again. I'll just type 5K and hit enter. Look at that. There was no transition whatsoever. I think that's pretty interesting and kind of mysterious. Well, we're going to leave that as a mystery for now and move on to the next one. What happens if you specify negative frequencies? Okay, negative frequencies. We've seen the FFT is displaying negative frequencies to us, but what in the world does that mean? Well, I'm going to change my slider here. I'll leave it the same default we've been using all along, and now I'll set the minimum to negative 50 kilohertz and the maximum to positive 50 kilohertz. Now, if I execute this flow graph, it should start up exactly the same way, and I can move my slider to the right, and we should see the Atari effect. There we go. If I move my slider to the left, we wrap back around, and now we're in the normal region, perhaps. And if I go past 0, hey, look at that. Sure enough, if I configure my signal source to give me a cosine wave of negative 10 kilohertz, then I get an output that's from the signal source that, when analyzed by the FFT plot, actually shows up as negative 10 kilohertz. This is quite mysterious to me because, think about it for a minute. What is a cosine? What does a cosine wave look like? If you plot a cosine wave, it looks like this, and it has a symmetry across the vertical axis. In other words, it's identical forwards and backwards. If you go horizontally, on the horizontal axis, if you go one direction, it's the same as if you went the other direction. It's a mirror image. So cosine of negative x is exactly the same as cosine of x. Or in other words, there's no difference between a cosine of a positive frequency and a cosine of a negative frequency. No difference whatsoever. They're exactly the same. Which tells me that the output of a cosine source running at 10 kilohertz should be identical to the output of a cosine source running at negative 10 kilohertz. But if we go back and look at our flow graph, you can see we have a signal source, and when we analyze it with the FFT sync, we get a difference between negative 10 kilohertz and positive 10 kilohertz. If I type in 10 kilohertz, that's how I configure my signal source using this frequency slider. Then the FFT says, yes, you have samples that appear to have a periodicity of 10 kilohertz. And if I type in negative 10 kilohertz, hit enter, the FFT says, that's different. That's negative 10 kilohertz, not 10 kilohertz. I find that to be extremely mysterious. Now, question 7. Does the plot indicate the presence of any frequencies other than the one produced by the source? Hint, use auto scale. Now, before I do this, I'm just going to set this back to the default, just so it looks the same as other people's graphs. And I'm going to use the auto scale button, or you could use the increase dB per division button. Look at that. Now what just happened was the scale, the vertical scale here in decibels has changed. So it's showing us from 0 to negative 200. Negative 200 is a lot of decibels, right? Or it's a lot of negative decibels anyway. So, what do we see here? We see one big spike at the frequency that we expect. But we also see a whole bunch of other garbage at every other possible frequency that the FFT knows how to display to us. That's mysterious. Now, this is a mystery that I think we can solve right now. Why would there be any noise at all? I would call this stuff noise. That's one way to think of it. First of all, notice how much quieter or how much less powerful, how much lower in amplitude this noise is compared to the spike. We're looking at a plot that shows us 200 dB in the vertical scale. The spike is just around 0 dB, and this stuff is around negative 170 dB. Negative 170 compared to 0. It's kind of hard to express just how inconsequential all this stuff is. It's 17 orders of magnitude smaller than this stuff right here, which was the frequency we expected. 17 orders of magnitude, 17 decimal places. That's tremendously tiny and insignificant compared to the signal that we have here. However, think about this for a moment. We are synthesizing this signal in software. Is there any more pure way to produce a cosine wave than to synthesize it in software? And then we're just delaying those samples a little bit or throttling them to a real-time rate and then delivering them to the FFT sync, which analyzes those pure synthesized samples, and it tells us that there's a bunch of extra frequency components in addition to the one we were expecting. There's this noise. Now, in a real-world system, in an analog system, with an actual antenna, for example, if we were receiving this as a radio signal, we would expect all kinds of noise. There would be radio noise over the air and interference, and there would be noise from the actual electronic device itself. On the analog electronic circuit would have some amount of noise, and we would pick that up when we digitize it, and we would expect noise from a real-world analog system. But do we expect noise from a digital system, a purely digital system? Well, let's think about this a little bit. And the thing I'd like you to think about is data types. Now, if you're a computer programmer, you probably know a little thing or two about data types. And I want to show you that data types exist in GNU Radio. If we were to go into this signal source and look at its properties, you can see right here, output type. And if we pull down this menu, aha, we can select a complex, a float, an int, or a short. Now, short in GNU Radio is a 16-bit integer, where it's an integer value that is represented, where every number is represented by 16 bits. An int is a 32-bit integer. A float is a floating point number, so it can take on values that are decimals, so it allows the decimal point to move around, and it's implemented as a 32-bit float. And a complex data type we're going to talk about later. Pretty soon we're going to have the talk about complex numbers. But what you need to know for now is that the complex data type is built on floats. So we're dealing with floats here even when we select complex. So we have an integer data type, another integer data type, a floating point data type, and another floating point data type. And the default is actually complex, which is maybe a little bit unexpected for some people. If we look at this FFT sync, we see this one only knows how to deal with complex or float. If we look at the throttle block, we can see that it knows how to deal with complex, float, int, short, or byte. And a byte is an 8-bit integer. So, if we were to represent every single sample as an 8-bit integer, that means there are only 256 possible values, because a byte has 8 bits. And each bit gets multiplied by the other in terms of how many values the data type can take on. So we get 2 to the 8th power for a byte. That's the maximum number of values that can be represented. It could be any number from 0 to 256, or it might be a signed byte that lets us take on values that are negative. But there are only 256 possible values that every single sample could take on. If we went to a short data type, well, that's a 16-bit integer. So there are 2 to the 16th power possible values. And of course, 2 to the 16th power is about 65,000, much bigger number than the 256 that we would get with an 8-bit data type. So I want you to think about it a little bit. If you were to plot a continuous signal and sample that signal, or try to represent that signal in the digital domain, well, what we do is we divide up the time axis into a number of distinct sample periods. And at each sample period, we measure that analog signal, or we choose how we're going to represent that signal in the digital domain. But we also are restricted on the vertical scale. We're restricted based on the data type that we use. If we have only a small number of bits to represent every individual sample, then we have to kind of create this grid. We have the time axis carved up, but we also have the vertical amplitude axis carved up into this grid. And then at every sample period, we have to represent something. If we're trying to represent a continuous waveform, we have to choose the digital representation that most closely matches that analog waveform. Now, a cosine wave, of course, is a kind of a continuous function, and when we approximate it in the digital domain, we're going to be going through a process like this, where we take discrete time values, and at each of those points in time, we have to take a discrete amplitude. And this process of restricting the sample values to particular points in the vertical scale is called quantization. And quantization introduces a little bit of error. Aha! Every time we quantize a signal, we introduce error, and it's called quantization error. So if we look back at our flow graph and we look at this, click the auto scale button and look at all this noise down here, if we were to have represented this as a different data type, then we should see that this noise floor is a lot higher. Like if we used an 8-bit byte to represent every sample, this noise floor would be much higher. If we use a 16-bit integer, then the noise floor would be somewhat lower than that. With a 32-bit float, the noise floor is way down here where we see all of this garbage around negative 170 dB. Can you think of a way that we might make that noise floor even lower? Well, it would be using a data type that has more than 2 to the 32nd power of possible values. So you could use, for example, a 64-bit double precision float. Now, that's not an option for us in GNU Radio Companion, but if you were writing your own digital signal processing software, you could use double precision floats to represent every sample, and you'd get more range in the vertical scale between your maximum value and whatever minimum value is going on here. There's some minimum value. In the case of an 8-bit byte, that minimum value is just the byte that has one bit set, the least significant bit. In the case of a 32-bit float, what exactly is the minimum value of a 32-bit float? How close to 0 can you get? I'm not exactly sure off the top of my head, but it's finite. There's a finite number of values, 2 to the 32nd power, which is about 4 billion. 4 billion possible values that every sample could take on if it's represented as a 32-bit float. So it's not arbitrarily large or small. It's very large or very small, but it's not arbitrarily large or small. Now, think about for a moment if this were a real-world RF analog system, we would have some noise floor to deal with. And it probably would be much, much higher than negative 170 dB in comparison to our signal of interest. So in the digital domain, we still have to deal with noise inherently from the quantization of every value that we're dealing with. But we get some control over that noise. We can choose, is this noise floor going to be up higher if we represented our samples with a smaller number of bits per sample, or is it going to be lower if we use more bits to represent every sample? And so we have this control or this power over the noise floor. That's something that you don't have so easily in the real world with analog RF signals. But within the digital world, we have that control. I think that's very interesting. Now, question 8. Try multiple signal sources added together. Let's try this. So I'm going to take this signal source and I will copy it and paste it. And this one I'm going to set to have a sample rate, or sorry, a frequency. I'll set this to the default of 1000. So I'll leave that constant, whereas this other one I'm going to leave as a slider. Maybe I'll even change that a little higher, just so they don't start out at the same frequency. Let's set this one to 5000. So one's fixed at 5000 and the other one is variable. If we add these together, and I'm going to do this with a math operator, we take the input of one signal source and add it to the other signal source. And this does a point-by-point addition. So it takes one sample from this source and then the first sample of this source, adds them together, and delivers that sample to the throttle block. Then it takes the second sample from the first source, the second sample from the second source, adds them together, and delivers that sum to the throttle block, and so forth. Let's try this. Now we see 2 spikes. Now remember, the FFT is getting every individual sample added together, and it's analyzing it and telling us what the frequencies are that were present. And if I move this around, remember one of those is fixed and the other one is being controlled, and it looks basically the same as it did before, except that there's this one peak in addition to the peak that I'm controlling. I want to show you what that looks like with the scope sync. This is kind of interesting. Look at this craziness. We have a frequency. If I control this, if I move this around, look at how wild that scope plot looks. How crazy that waveform looks. And yet, somehow, the FFT is able to look at this right here, what you're seeing, especially if you give it individual sample points. These are the data, these blue dots, that the FFT sync is analyzing and telling us, oh yeah, you have a frequency here at 5 kilohertz and you have one at 8 kilohertz. And if you move this around, things may not look very easy for you to analyze by eyeball. I mean, look at that. Could you eyeball that scope plot and tell me that there's 5 kilohertz and 8 kilohertz? But somehow the FFT is able to do that. So hopefully that gives you a little bit of a respect for what the FFT algorithm is doing for us. Because it's taking, now this one's a little bit easier to see. Do you see how there's this high frequency component up and down and up and down, and then there's this low frequency component? That's a little easier to see by eyeball, and sure enough the FFT shows us a 1 kilohertz and a 5 kilohertz. But when we have two different high frequency components, it becomes very difficult to kind of determine that by eyeball. And the FFT is able to take this list of samples, or this stream of samples, and turn it into this plot that tells us exactly what signals are present. I think that's really cool. So, one more thing I asked you to try, question 9, was try various waveforms instead of a cosine. Well, if I disable my additional wave here that I'm adding together, let's just look at what this looks like with a single cosine wave. And then we'll look at what it looks like if I try, let's say for example, a square wave. And notice you can select a bunch of different things. If I do a square wave and start the flow graph, now look, the scope plot, see that blue curve? It looks very square. If you look at the dots, it's a bunch of lows, a bunch of highs, a bunch of lows. It just goes back and forth square between two different values, which are 0 and 1. And now look at the FFT. Look at how many different frequencies are present. But notice that only 2 of them are very prominent. Remember, things that are below, say, 20 or 30 dB, below our signal of interest, generally are things that we can ignore. So there aren't very many peaks that are very high in amplitude. There's a lot of stuff that's down here, around -30 to -40 dB. That's very interesting. We'll explore that in a little bit more detail in the future, but I want you to recognize something, that when we have a waveform that has an abrupt change, it goes from 0 to 1, and then 1 to 0. When we have a waveform that has an abrupt change, we tend to get a lot of frequency components, or I would call this a lot of bandwidth, this width in hertz of our signal. Whereas if we have a smoothly varying function that looks sinusoidal, then we have very narrow band signal. If I set this to a cosine wave again, you can see our peak is extremely narrow, and there really isn't any other stuff going on at any appreciable amplitude, because we have a smoothly varying function. And that's something I want you to remember. If the time domain plot that we see in the scope plot, if it looks smooth and comfortable, if it looks like you could lie down on it and take a nap, then you have a narrow band signal. But if you have a scope plot that looks really spiky or has sharp edges, then you have a wide band signal, or something with higher frequency components further from 0.
Isn't it amazing how much we can learn from this one simple flow graph? And we aren't even done yet. For the homework for this lesson, go to greatscottgadgets.com/SDR, and under lesson 4 there are a couple more questions that I'd like you to answer about this flow graph. I'd like you to play with data types, and the complex data type in particular, before we have the talk about complex numbers. I hope to see you next time in Lesson 5. Hi, I'm Michael Ossman of Great Scott Gadgets, and this is Software Defined Radio with HackRF. Lesson 5, HackRF One. Most of this course is about Software Defined Radio, but this lesson is about HackRF One, the hardware platform. HackRF One comes in a cardboard box, and inside the box you should find a USB cable and HackRF One itself. Now, HackRF One has a black plastic injection molded enclosure, and at either end of the enclosure you'll find all these various things, and I'd like to go through these things one at a time so you understand what they all mean and how to use your HackRF One. Now, the most important thing you need to know is the USB connector. It's a USB micro B connector, and the reason it's most important is because HackRF One is powered by this connector, so it doesn't do anything unless you plug in a power source. I'm going to plug it into my host computer, and you should see that some of these LEDs illuminated. Let's go through these LEDs one by one and talk about what each one means. The first three LEDs that you should see illuminate when you first plug in HackRF One are 3V3, 1V8, and RF. And those are three different power supplies within HackRF One. Normally they should all three come on when you first plug in HackRF One to a power source, and under normal use they should all remain on. The only reason a couple of them might turn off would be if we implement a low power mode, a power saving mode. And then while the HackRF One isn't doing anything, you might see a couple of those turn off. But if you're trying to use HackRF One, if you're trying to receive or transmit radio signals, then all three of those should be on, and if they're not all on, then that indicates a problem. Now the next LED is called USB, and that indicates that the host computer is actually talking to HackRF One. They're communicating over USB, and the host computer has configured HackRF One as a USB device. So you might notice that the USB LED illuminates just a little bit after the first three. The first three LEDs should turn on very quickly when you plug in the USB connector and power on the HackRF One. The USB LED might come on a second later because that doesn't happen until after the USB host has configured HackRF One. And then the next two LEDs, which should be off when you first plug in HackRF One, are labeled RX and TX. RX indicates a receive operation, and TX indicates a radio transmit operation. So you should see one of those turn on when you're actually using HackRF One to receive or transmit a radio signal. So most of the time while you're trying to use HackRF One, you should see four LEDs illuminated, the three power supply LEDs and the USB LED, and then you should only see the RX and TX LEDs illuminate when you're in the middle of a radio receive or transmit operation. Now those last three LEDs, USB, RX, and TX, are under software control. They're controlled by firmware running on the microcontroller within HackRF One. So if you were to install your own custom firmware, you could use those three LEDs to indicate whatever you want. But using the default firmware that most people will be using most of the time, those indicate specifically USB configuration, receive mode, and transmit mode. Now you might notice that all six of these LEDs are various colors, and the colors don't mean anything. The only reason they're different colors is so that you can distinguish one of these LEDs easily from its neighbors. Each of these LEDs is a single color LED, and there are various colors across the row. Now, the other two things you might notice near the LEDs are these blue buttons, the reset button and the DFU button. The reset button resets or reboots the microcontroller within the HackRF. One way you can reset HackRF, of course, is to unplug the USB power supply and then plug it back in. But it's a lot more convenient and easier on the USB connector if you just press
the reset button briefly. That reboots HackRF, and it will reset, so the host computer has to reconfigure it on the USB bus. It's kind of like what happens when you unplug the power supply and plug it back in, but it's quicker and easier to press the button. The other button is labeled DFU, and that's used for a firmware update mode, but you don't actually need to use it most of the time. HackRF One is able to update its own firmware without having to go into DFU mode. The reason we support DFU mode is because that's a way that you can unbrick a HackRF if you have a firmware update that went wrong. If for some reason your HackRF does not actually enumerate on the USB bus and you never see that USB light come on, then that might indicate there's a problem with the firmware. And if that happens after you tried to do a firmware update, well, then you can use DFU mode to recover your HackRF. And the DFU bootloader is actually in ROM, so it can't be overwritten. Now, to get it into DFU mode, what you do is you hold down the DFU button while unplugging the USB connector and plugging it back in. Actually, what really matters is that you're holding the DFU button down while you plug in the power supply. And if you do that, you should notice that the 3v3 LED comes on, but the other two power supply LEDs don't come on, or at least they don't come fully on. And that's a good way to check that you're actually in DFU mode just very quickly. The other way to get into DFU mode is, I'll just reset it here so now it's in normal mode. The other way to get it into DFU mode is to hold down the DFU button while you press and release the reset button. Then you can release the DFU button, and now HackRF One is in DFU mode. Either way, whether you hold down DFU during a reset or if you hold down DFU during initial power on, then HackRF One will start up in DFU mode, which is using a ROM bootloader, and you can use a special piece of software on your host computer to actually install HackRF firmware on HackRF One, even if there is no currently functional firmware on the device. Now, I'll just press reset again, and it should actually reboot the regular firmware and be back into the normal mode. The DFU button doesn't actually do anything except during reset or during initial power on. So it is available to you if you are interested in making your own custom firmware for HackRF One. You could actually use that DFU button as an input to your firmware, because it doesn't do anything normally. It's only during reset that it matters by default. Now, the other thing on this end of HackRF One is the antenna port, and on the other end we have these two ports, clock in and clock out. All three of these are similar connectors. Let's take a look at them. They're SMA connectors, and they come with these red plastic caps that are protective caps. It's a good idea to leave those on if you're not using the port. So for example, these clock in and clock out ports I don't use very often, so I usually have them covered by the red cap. These are SMA connectors, all three of them. And you might have seen similar connectors on Wi-Fi equipment, for example. It's very popular on Wi-Fi equipment to have RP SMA. Now, RP SMA is different than SMA. SMA has a female connector, that is the connector with external threads. The threads are on the outside here. The female connector, if you look inside, has a female connection in the inside, and then the other connector that mates with this one has a male pin in the middle. And an RP SMA connector has them the other way around, so the female connector, or the one with the external threads, actually has a little male pin inside. It's a little bit confusing that they have these two different styles of connectors that are almost identical, except they change which side has the pin internally. So be careful that when you're selecting equipment or antennas or cables to plug into the connectors on HackRF One, be careful that you use SMA connectors and not RP SMA connectors, because an RP SMA might appear to actually connect correctly, but there will be no internal connection because neither side will have a pin. And that's a very annoying problem to have because it can be hard to troubleshoot because it looks like everything's connected, but then there's no actual internal connection. So be careful of that. Now the SMA connector here that's labeled antenna is the antenna port, or you can think of it as the RF port. You don't have to connect an antenna to it, but you should have it connected to either an antenna or a cable going to some other RF equipment. One antenna you might use is ANT 500, which is just a simple telescopic antenna. This is a good starter antenna for HackRF, but realize that there's no one antenna that is good for every application that you might use HackRF One for. This is just a good antenna to get started because it is very simple, telescopic, and because it's telescopic, it can operate over a pretty wide range of frequencies, and it has an SMA male connector that allows you to connect it directly to the HackRF One without any adapters. So be sure that you do have an antenna or something connected to the HackRF at all times when you're doing receive or transmit. Now, if you're ever tempted to not have an antenna connected at all, what you should do is get one of these little dummy loads. And this is just a little SMA male plug that has a 50 ohm load within it. This just screws right on the SMA connector, and it allows you to use your HackRF One safely even with no antenna attached. So that's very important. Never use your HackRF One for receive or transmit without having something connected to the RF port. It should be a dummy load or an antenna that is suitable for the frequencies that you're working with, or a direct connection to RF equipment. Now, if you are using a direct connection to RF equipment, be aware of the maximum input and output power levels that you can find on the HackRF wiki. It's very important that you don't exceed those limits or else you might damage the HackRF One. Now, the other two ports on the other end, also SMA connectors, are clock in and clock out. And these are for clock synchronization between multiple HackRF Ones. So, for example, you can take two HackRF Ones, take an SMA cable and connect it from the clock out of one HackRF One over to the clock in on the other HackRF One, and then their clocks will be synchronized, which is useful for certain applications. Now that only matters if you have multiple HackRF Ones, or if you would like to take your single HackRF One and would like to synchronize it to a particular external time source. For example, you might have a GPS disciplined oscillator, or you might have a rubidium frequency standard, or something in your lab that provides a more stable clock source than the crystal that's within HackRF One, for example. And if you do, all you have to do is take a 10 megahertz signal and connect it to the clock in, and the HackRF One will automatically synchronize to that external clock. It's always looking every time. Actually, it's when you start a receive or start a transmit operation. Every time you start an operation, a radio operation with HackRF One, then it checks to see if there is a 10 megahertz signal on the clock in port, and if there is, it synchronizes to that signal, and if there isn't, it uses its own internal crystal. Now, the signal that you need to give it on the clock in port is a 10 megahertz square wave ideally, and it should vary between about 0 volts and about 3.3 volts. So it's a 3.3 volt square wave, and that's exactly what you should see on the clock out port of every HackRF One. So you can connect them directly together from one clock out to the other's clock in, or you could connect one or more HackRFs. You could take their clock in and connect them to a single source, a single time base for all of them. Most of the time, for most applications, I don't use those ports, and so I just leave the red protective caps on those SMA ports, and I don't worry about them. Now, let's talk about how to use HackRF One a little bit, and a little bit about the software that is available for HackRF. The HackRF project provides two different software packages, and they are called libHackRF and HackRF Tools. Now, libHackRF is a library that allows other software to communicate with HackRF. So, for example, this is how GNU Radio communicates with HackRF, is through libHackRF. HackRF Tools is a small software package that provides some command line tools for working with your HackRF. Let's get familiar with those a little bit. The first command you should know is HackRF info. And if your HackRF is plugged in and you type HackRF_info, you should see that it finds that HackRF unit and it tells you that it's a HackRF One, and it tells you the firmware that is installed. In this case, it's 2014.04.1, which is from a release package. You might see that your firmware says git something or other, which is telling you the particular git commit from the source code repository. But if you install firmware from one of the release packages, then your HackRF One should tell you when you use the HackRF info command that it is running that particular release. Now, the next command I'd like you to know is HackRF transfer. And I'll just type it here and show as help output. There are quite a few different options. Now, this is a small utility that you can use from the command line to transmit or receive data. So if you receive if you turn the HackRF One on into a receive mode using the HackRF transfer command, then data will stream over the USB connector and into a file that you specify. And if you use transmit mode, the -T option, then you will specify a file name, and that the data in that file will be streamed over USB to the HackRF and then turned into a radio signal out the antenna port. Now, there are a whole bunch of different options here for configuring the radio section and turning on different gain stages and all sorts of different things. But let's try this out a little bit. And I'm going to type HackRF_transfer, and I'm going to tell it to do a receive operation and put the data into a file called /dev/null. And if you're on a Linux system, you should always have a file called /dev/null. It's a special file that just throws away everything that you give it. So this is just a quick test to make sure that our HackRF can transfer information to us. Let's give this a try. Now, it says stop with Control-C, so that's what I'm going to do in a few seconds here. I'll just hit Control-C, and I'm done. Now, you should notice that the default sample rate that it set to was 10 million hertz, or 10 million samples per second. And I got an average of 20 million bytes per second from the HackRF. And that's normal. You should see 2 bytes transferred for every sample, because a sample is made up of two values, each of which is a signed 8-bit integer, or a signed char. And that's the actual data format that's used over the USB connection of HackRF. And so the HackRF transfer utility is just a simple way to take the raw data that comes over USB and put it into a file, or to take data from a file and transfer it over USB to the HackRF. So in this case, we just verified that everything was working correctly. All the HackRF digital section is working correctly and giving us 10 million samples per second. And if we want to, we can change the sample rate using the -S parameter. For example, if you wanted to find out, does your USB connection on your host computer actually support 20 million samples per second? If you type -S 20 million on this HackRF transfer command, now we'll be operating at 20 million samples per second, and we should see that we get an average of 40 million bytes per second, because that's 2 bytes for every 1 sample. And sure enough, on my particular computer, on this particular USB port, I can get that 40 million bytes per second, and that means that HackRF is able to operate on this computer at its maximum sample rate of 20 million samples per second. Now that's the advertised maximum sample rate, but I found that on at least some host computers, and with some HackRFs at least, I am able to operate at 21.5 million samples per second. And if you do that, you should see that you're getting 43 million bytes per second. That's the absolute maximum, pretty much, that I've seen work reliably on any host computer. Now, some host computers won't be able to operate that fast, and it could have to do with the speed of the CPU, but more likely, if you're just using the HackRF transfer utility like this, more likely that would indicate that there's a problem with the USB connection itself. The USB host controller within the PC might not be able to operate that fast, or there might be other USB devices on that bus inside the PC that you can't see, and they may be slowing down the available throughput for HackRF. So you might find, and this is a good way to find this out, you might find maybe your particular USB port only allows you to operate up to 16 million samples per second. And HackRF transfer utility is an easy way for you to find this out. And it's a good way to find it out because it is only exercising the USB connection. If you are writing the samples to /dev/null, then you're actually not saving the samples anywhere. You're discarding them, and so you're not requiring your CPU to do anything with those samples. So it makes it it isolates any problems you might have with a USB connection from problems that you might have with your CPU keeping up, and it allows you to determine exactly how fast your USB connection is able to go. Now, personally, I've had computers, I've had a laptop, for example, where on one USB port I could get 20 million samples per second, and on a different USB port I was only able to get 16 million samples per second. You may have various different maximum rates that you find that different USB hosts are able to achieve. But in general, you should, unless you're trying to connect to a very busy USB port, or you're connecting to a port that's broken or doesn't support high-speed USB, as long as the port that you're connecting to is functional and not too busy, you should be able to get at least 10 million samples per second, which is the default transfer rate with HackRF transfer. You should be able to get at least 10 million samples per second with pretty much any USB port. And the HackRF transfer utility is a way to verify that. Now, again, I want to look at the options here just a little bit. If we did the same thing, only use the -T, transmitting /dev null doesn't make any sense, but you could transmit dev 0, for example, or you could transmit data from a file. And the data format, as I mentioned, is two 8-bit signed integers for every sample. And we'll talk about why there are two integers per sample in the next lesson quite a bit. Now, there are a number of different command line switches, like setting the frequency, and if you want, you can use these options to set the intermediate frequency, the local oscillator frequency, and the image reject filter selection. Normally you wouldn't do that. This is just a way to kind of override the default tuning algorithm that's within HackRF One. In the future, we'll talk more about the internals of HackRF One and what these exact options mean and what they do inside HackRF. Most of the time, you should use the -F option to set the frequency. Now, the amp enable option enables the RF amplifier. Notice it says RF amplifier. And so you might have noticed, for example, in the Osmocom source in GNU Radio, there is a RF gain setting. And that RF gain setting we set to 0 dB, I think, when we were doing an example the other day. Now, in HackRF transfer, you can notice that this is actually set to either 1 or 0. You either enable or disable the RF amplifier. There are only two settings for that particular gain stage, and that's the stage that's closest to the antenna. And so normally, and nominally, that gain stage gives us about 14 dB of gain, although the amount of actual gain varies by the frequency range. So if you set that to, I think, 10 dB or higher in the Osmocom source, then it will enable the RF amplifier. If you set it to 0 in the Osmocom source, it will disable it. Now here with the HackRF transfer utility, we simply type -A0 or -A1 to enable or disable that gain stage. There's also this antenna port power control. Now normally antenna port power is off, which means there's no DC on the antenna port. There's no direct current power supply there. But it's possible to enable a small amount of power on the antenna port. That could allow you to use an active antenna, for example, like there are GPS antennas that are compatible with HackRF One that can be powered by HackRF One if you use this option. And then we have these other gain options, and these are different gain stages, and these relate to the other gain options that you might have noticed in the Osmocom source in GNU Radio. -S lets us set the samples per second. -N lets us transfer a particular number of samples. So if you only wanted to transfer 1 second, for example, and you were operating at 10 million samples per second, then set this to 10 million. Otherwise, it'll just continue until you hit Control C. And this -C option is new. It lets us transmit a CW signal, or just a constant carrier, which is useful for various testing states that you might want to put the HackRF in. And the -B option lets us set the baseband filter bandwidth. We're going to talk about that more in the future, and this is also something that you can control from the Osmocom source in GNU Radio. But the default, notice, is less than the sample rate in hertz. So whatever you choose for your sampling rate, it's going to automatically select the filter, the baseband filter that is just slightly under your sample rate. So that's the default, and normally that's fine for most applications. But we'll talk in a future lesson more about when you might want to use a different baseband filter value. Now, the other utilities that are good to know are the utilities that are used for updating the firmware in HackRF. Now, if you type HackRF info, you'll see the firmware version that is installed on your HackRF. And in this case, this one has 2014.04.1, and that's not actually the most recent version that's available. The most recent version available right now at the time that I'm recording this is 2014.08.1. So let's update the firmware. Now, I'm going to use a copy of the release package, and this is actually a file that I've downloaded that is the release package for HackRF. Now, if you're using the Pen2 ISO, the most recent version that's coming out right about now actually has the contents that we'll need on the ISO itself, so you won't have to download the release package, but you can always download the release package, the most recent release, and find the files that you'll need for doing a firmware update. So I'm going to extract this HackRF release package and look at the contents here. I'm going to go into the firmware bin directory. These are the firmware binaries, and you can see that there are some firmware binaries for HackRF One and some for HackRF Jawbreaker, which is the beta platform. And then there's also this CPLD configuration file that we'll work with in just a moment. The first thing I'd like to do is to use the HackRF Spy Flash utility. This is another tool that's part of the HackRF Tools package. And I'm going to write to the HackRF the file HackRF One USB ROM to RAM.bin. So just remember that ROM to RAM. And the reason it's called ROM to RAM is because we write this file to the flash that is on the HackRF, and then when it boots up, it actually copies it from flash to RAM and then executes it. So this particular binary has the code in it that allows it to load itself into RAM, as opposed to this other one, which only is for use during recovery operations using DFU mode. So I'm going to write this file, and it only takes a few seconds. Now it's done. Now if I type HackRF info, you should see I'm still running the old firmware because I haven't rebooted the HackRF One, and I haven't gone through that process of having the firmware copy itself into RAM and execute. So I'm going to hit the reset button on my HackRF One, and now if I type HackRF info, look at that, I'm running 2014.08.1. That's how easy it is to update the firmware. Now there is one other step though that you should take, and that is updating the configuration of the CPLD. That's the complex programmable logic device on HackRF One. Remember, there's this other file here, HackRF CPLD default. Anytime you see an XSVF file, that is a configuration file for the CPLD. And this is, the CPLD is a chip on HackRF One that is between the microcontroller and the analog to digital converter and digital to analog converter. And it provides some interface functions in between those two. And from time to time, there may be a new version of the CPLD configuration that comes with a particular release of HackRF software. So, in this case, there is one. So I'm going to run the HackRF CPLD JTAG utility with a -X option and give it a HackRF CPLD.xsvf, and I will run this, and it tells me to wait until write is finished, and sure enough, it tells me write is finished, and it's telling me to power off and disconnect the HackRF. Now in the future, this may actually reboot itself when we do a CPLD update. It might reboot itself when we do a HackRF SPY Flash update. But right now, in both cases, I have to reset the HackRF to actually activate the new code. So now I've reset the HackRF, and if I run HackRF info, it tells me the firmware version. Note that it does not tell me the CPLD version. So it's very important that you do update the CPLD to the latest version when you update the SPY Flash or the actual firmware to the latest version. You have to remember to do that. So do both, and you'll have your HackRF running the latest software, the latest firmware, and the latest CPLD code, and that will go along with the latest software that you have installed on your host computer. I'll save an in-depth discussion of the internals of HackRF One for a future lesson, but I hope that getting familiar with the externals and with some of the software that's available for HackRF was useful for you. It can certainly be useful to use those command line tools for troubleshooting your HackRF One or for performing firmware updates. Now there's one thing about the inside of the HackRF One that I would like you to know about right now, and that is the RF amplifier that I mentioned when we were looking at the HackRF transfer utility. Now the RF gain stage, or the RF amplifier, is right next to this antenna port. It's right here. And there are actually two RF amplifiers. There's one for transmit and one for receive. And then there's a third path that just is a bypass path that allows you to completely bypass those amplifiers and operate either in receive mode or in transmit mode without that amplifier active. So if you set that amplifier setting to 0, or if you set RF gain to 0 in the Osmocom source or sync in GNU Radio, then you will disable that amplifier stage completely. And that's how I recommend that you operate most of the time, unless you need that extra boost for a particular application. And the reason I want you to know about it in particular is because it's right next to this antenna port. There's no filter between the antenna port and that gain stage. So, for example, if you were receiving FM radio stations in GNU Radio, and you turn that amplifier on, and you happen to be in close proximity to a high-powered amplifier running at say 2 gigahertz, completely different frequency than the FM radio stations that you're trying to receive. That RF amplifier stage is actually receiving that 2 gigahertz signal and trying to amplify it before it gets filtered out later in the receive chain in the HackRF. So be aware of that. You could potentially overpower a gain stage. You could potentially damage an amplifier in that gain stage if you don't, if you're unaware of that, and if you were to exceed the power limits of HackRF One. So some tips just to keep your HackRF One safe. Be sure that you always operate with an antenna connected, or a dummy load connected, or a cable to some RF equipment connected. And usually if you do use a cable, you'll probably have an attenuator that you'd want to put in place. Be sure to check out the wiki and look at the power limits of HackRF, and that way you'll know how much attenuation you might need when you directly connect equipment to HackRF. But if you always use an antenna or a dummy load, and you're careful, and you don't activate that gain stage except when you really need it, then your HackRF should last quite well, and everything should work. But the most sensitive part that you should probably be aware of is that gain stage right by that amplifier. So be aware of that, and I hope to see you next time for Lesson 6. Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 6, Complex Numbers. You've seen complex numbers used by several different blocks in GNU Radio. I'd like to tell you all about why complex numbers are used in digital signal processing, and in particular in Software Defined Radio. I'd also like to show you how complex numbers can be used to explain the various DSP mysteries that we've encountered so far. But first we need to have the talk about complex numbers. Now perhaps you're familiar with complex numbers and imaginary numbers, and perhaps you're not. Either way, I'd like to show you how I think about complex numbers. Now personally, I first learned about complex numbers in school, and then I forgot about them and thought I would never see them again for the rest of my life. Then I started doing software-defined radio, and I quickly discovered that complex numbers were something that I would have to get familiar with again. So I made a deliberate effort to relearn complex numbers, and I learned how to conceptualize them in a way that makes sense to me, and I hope will make sense to you. When I think of numbers, I like to visualize them on a number line. For example, 0, 1, 2, 3, and so forth. Every number is a point along a line. And I think of addition like this. If I were to take 1 plus 2, that's starting at 1, shifting over 2 spaces to the right, and ending up at 3. Or let's say 2 plus 3. That's starting at 2, shifting 3 spaces to the right, and ending up at 5. And I think of subtraction in the same way, except we shift the other direction. So 6 minus 2, we start at 6, shift 2 spaces to the left, and end up at 4. Or let's say 8 minus 5. That's starting at 8, shifting 5 spaces to the left, and ending up at 3. In other words, I think of both addition and subtraction as a way to translate or shift to the left or right along the number line. Now, how about something like 3 minus 5? Can I subtract a bigger number from a smaller number? You'd probably say, sure, all you have to do is extend your number line to the left and end up at the result of -2. But the existence of negative numbers hasn't always been obvious to people. Mathematicians argued over the legitimacy of negative numbers for centuries. And you can imagine why. They're a little bit different. They're a little bit more of an abstract concept than positive numbers. For example, if I walked up to you and I said, I have 2 apples. Do you want one? You would say, sure, and I'd give you an apple, and then you'd know that I had 1 apple left. But what if I walked up to you and I said, I have -3 apples. Do you want one? what would that mean? How many apples would I actually be carrying? Do I owe somebody some apples? Could you ask me for a negative apple? How does that work exactly? It's a little bit of an abstract concept. And you can understand that people had to make a leap of reasoning to start to accept that negative numbers were legitimate numbers, just like positive numbers. So let's pretend that we haven't come to that conclusion. Let's pretend that we don't know anything about negative numbers. How might we decide how to handle this problem of 3 minus 5? Now, you know that you can add any two numbers together. As long as we agree that we can extend this number line arbitrarily to the right, then we can add any two numbers together and keep adding and have no problem. But when we subtract, we do sometimes run into a problem where we might want to go off the left edge of this number line. So let's see what happens. If we take our visual approach, our geometric interpretation along the number line here, then 3 minus 5 would look like this. We'd start at 3. We would shift over 1, 2, 3, 4, 5 spaces to the left, and we would end up right about here. That suggests that we've gone 1 and 2 spaces to the left. So maybe we could extend this all the way. Who knows? Maybe it goes forever. Maybe we could have 1, 2, 3, 4, 5, and so forth. Now this, we might number them. 1, 2, 3, 4, 5. However, this is confusing because now I have 1s on the 1 and 2 and 3 and 4 on the left, but I have 1 and 2 and 3 and 4 on the right, and I have to have some way to distinguish one direction from the other. Well, maybe if we look at our numeric, our arithmetic version of this down here, this might give us a clue as to how we could represent this. Now, how could we simplify this expression, 3 minus 5? One way we could simplify it would be by changing it to 2 minus 4. Now, that should end up in the same place, right? We would go 2 and shift 4 spaces to the left. 1, 2, 3, 4. And we'd end up there, 2 spaces to the left of the origin. If we continue to reduce this, it could be 1 minus 3, or it could be 0 minus 2, and now we've reduced this term as far as we could go. In fact, a 0 is nothing, so we could just erase that. And what we're left with is minus 2. So that suggests that what we should call this number over here on the left is minus 2. That's how we should designate that it's different than this 2 over here on the right. And it suggests that we should call all of these things negative numbers, or minus 1 through minus 7 and so forth. And this is, I like to think that this is a kind of approach that people might have taken long ago to come to the conclusion that negative numbers were legitimate. And the reason that we can tell that they're legitimate, I think, is that this visualization and this arithmetic interpretation are completely consistent with one another. The idea that we can translate numbers to the left or right by adding or subtracting completely agrees with all the arithmetic we can do once we understand that negative numbers exist. So let's think about multiplication for a moment. How would we multiply 2 by 3? Well, we would start here at 2, and then we move over. Are we translating 4 spaces to the right? No. You know the answer is 6, but it's not a translation. The way I think of it is that we have this arrow that extends from 0 to 2. It goes from the origin 2 spaces to the right. And then we're taking that 3 times. So we go 2 spaces to the right once, and then twice, and then 3 times. We triple this distance from the origin and end up at 6. Or take, for example, 1 times 4. We start at 1, and I think of that as being an arrow that goes from the origin to 1. And we take that arrow 4 times, once, twice, 3 times, 4 times, and we end up at 4. In other words, multiplication allows us to scale a number. We scale its distance from the origin, from 0. It's scaled, not translated. And what about multiplying by a negative? If we were to, say for example, take 2 times negative 3. Well, we'd start at 2, and you probably know the answer already. It's negative 6, right? But how do we get there? The way we get there, the way I like to think of it, is that we take this arrow, this vector that goes from 0 to 2, we triple its length, or scale it. And we scale it by 3 times because we're multiplying by something that has a distance from the origin of 3. So we take that once, twice, 3 times. We end up over here at positive 6, but then we flip it around. We rotate it, and we end up at negative 6. That's interesting because it suggests that multiplication does something more than scaling. Multiplication can scale a number, and it can also rotate a number, or flip it around the axis. Flip it around the origin, I would say. How about taking a number like negative 1 and multiplying it by a negative number, negative 5? Well, I think of that as starting at negative 1, or having this arrow that points in this direction. And we're going to scale it 5 times. So that's once, twice, 3 times, 4 times, 5 times. And then from here, I'm going to flip it around because I'm multiplying by a negative number. I'm going to flip it around and rotate it over to positive 5. Now, we rotate by a half turn when we multiply by a negative number, or we rotate by no turns when we multiply by a positive number. So we can rotate either a half turn or no turns. Now, multiplication and division both work the same way, except in one case we're scaling up, and in another case we're scaling down. So both multiplication and division can scale and rotate. And of course, addition allows us to translate, and subtraction allows us to translate. So just using these very basic arithmetic operations, we can scale, rotate, and translate. And I think that that fully describes all of arithmetic. Now, can we translate by an arbitrary amount in either direction and end up anywhere on this number line? Sure. Can we scale by an arbitrary amount and end up anywhere on this number line? Sure. Can we rotate by an arbitrary amount and end up anywhere around the origin? Well, that's an interesting question. We can certainly rotate by a half turn, and we can rotate by no turns, or you might think of that as rotating by a full turn. But can we rotate by, say, a quarter turn or an eighth of a turn? I'd like to approach this question by playing another game of what if. What if it is possible to rotate a number by multiplication to some place that is not on this number line? Can we rotate? We know that we can rotate, for example, 2 times negative 1. We know that multiplying by negative 1 rotates us a half of a turn, and that equals negative 2. But is it possible to rotate by less than half a turn? Let's say we could multiply 2 by some number that rotates us a quarter turn. Well, if that were true, then we should be able to rotate again by the same amount, the same quarter turn, and end up over here. In other words, if we were to say 2 times some mystery number z times that mystery number z again, we should end up at negative 2. Is that possible? Well, let's check this out. if we were to just solve for z here, we'd see z squared equals, that's negative 2 over 2, so that's negative 1. In other words, z is equal to the square root of negative 1. So apparently, the square root of negative 1 is the amount that we have to multiply by in order to rotate a quarter turn. Well, that's interesting. At some point in your mathematical career, somebody might have told you that there's no such thing as the square root of negative 1, but we seem to have just discovered it here. Let's try a different one. Let's try starting at negative 3. If we start at negative 3 and rotate a quarter of a turn, and then rotate a quarter of a turn again, we should end up at positive 3. So negative 3 times some mystery number z times z again should get us to positive 3. Okay, if we solve for z, we get z squared equals, well, that's 3 over negative 3, which is negative 1. And so again, we find that z is equal to square root of negative 1. It's consistent with the answer that we got trying a different case. That's a good indication that we might be onto something here. So if this number, the square root of negative 1, exists, where is it on our number line? Well, here's a trick we can use to find it. What if we were to take 1 times the square root of negative 1? Sorry, it's supposed to be times square root of negative 1. Now 1 is the identity, the multiplicative identity, but we can also use our geometric interpretation here and say we're starting at 1 and we're rotating by a quarter turn, because that's what the square root of negative 1 gets us when we multiply by it. So we rotate a quarter turn and we end up right here, which suggests that this is the exact location of this number, the square root of negative 1. And if we were to multiply that number by 2, where would 2 times the square root of negative 1 be? Well, it would be scaled from the origin, so it would be right here. Aha! This suggests that we could have any number of multiples of the square root of negative 1. We could have 1 here, here's times 2, here's times 3, here times 4, and here's times 5, and so forth. That's pretty interesting. It's a completely different axis than the axis that we're used to. And if we were to multiply those numbers by negative 1, then presumably we should find that we can also have numbers going down this axis here, or this lower extension of the vertical axis. And here's 1, like negative 1 times the square root of 1, and negative 2 times the square root of 1, and negative 3 times the square root of 1, negative 4 times, negative 5, and so forth. Now, the square root of negative 1 is referred to by mathematicians as I. It's called the imaginary unit. And this axis is called the imaginary axis. This axis, this horizontal axis, is called the real axis. And numbers that you're used to, positive and negative numbers, are called real numbers. Numbers that are on this vertical axis are called imaginary numbers. Now, to make things more confusing for you, some people also call this number J, especially electronics engineers, because I was already taken. And in many programming languages, I've seen J used as an imaginary unit. For example, in Python. So sometimes this number is called the square root of negative 1, sometimes it's called I, sometimes it's called J, but in any event, no matter what you call it, it lives right there. And this is 2i, 3i, 4i, 5i. This is negative I, negative 2i, negative 3i. Notice that when we multiplied negative 3 by I, we ran right through that point. Negative 4i, negative 5i, and so forth. Now, is it possible to rotate by other amounts? We've rotated by a half turn, we've rotated by a quarter turn, but could we rotate by, let's say, an eighth of a turn? Well, I think we could play the same exact game. Let's say we started at 4. We wanted to rotate an eighth of a turn to here, and then rotate another eighth of a turn would get us to 4i. So we could play the exact same game and say 4 times some mystery number z times some mystery number z again equals 4i. And we could solve and find out that, yes, in fact, we can have a number that is right here that is not on either axis. It's not a real number and it's not an imaginary number. It has some real component and some imaginary component. And we call these numbers complex numbers. Really, anywhere in this entire plane, we could have a number, and it would have some real component and some imaginary component. If it's on the real axis, then we also call it a real number, and it has a 0 imaginary component. If it's on the imaginary axis, then we call that an imaginary number and it has a 0 real component. But all of these numbers, anywhere in the whole plane, including on its axes, is something that we call a complex number. Another way that we can arrive upon numbers that are complex but are not on either axis is by translating, by addition or subtraction. Take, for example, 1 plus 2i. Well, we would start at 1 and translate 2 spaces in this direction and end up right here. Now, how do we reduce this? 1 plus 2i? Well, there is no way to reduce that further. It's always going to be 2 terms. And that's what happens with complex numbers. We call them complex because they have those 2 different components, a real part and an imaginary part. Well, let's just make sure that things are consistent here, that we can do things like addition and subtraction and multiplication and division. What if we were to take this number, 1 plus 2i, and let's say multiply it by I? Well, algebraically, we would say that's I plus 2i squared. But remember that I squared is -1. So really this is I minus 2. And we usually write the real part first. So that reduces to -2 plus I. So we would go over 2 and down 1, up 1 to I. And this is the result. So we multiplied 1 plus 2i, which was over here, and we multiplied it by I and got to -2 plus I. Now let's make sure that our geometric interpretation is correct. Multiplying by I should be a rotation of a quarter turn. And if we were to look at this as a vector going from the origin to that point, and then we look at this one as a vector going from the origin to that point, hey, sure enough, that's a right angle, or a quarter turn. So all we did when we multiplied by I was that we rotated this point by a quarter turn. We end up the same distance from the origin, just rotated. And the algebraic interpretation agreed with our geometric interpretation. That's a very good sign. Now let's try taking this point. We have this point -2 plus I. And if we were to take that and, let's say, subtract something. Let's subtract 3i. Well, -2 plus I minus 3i, that's minus 2i. So if we subtract 3i, we should end up at -2 minus 2i. Or the geometric approach, or the interpretation here, our visual interpretation, is that we should be shifting down 1, 2, 3 spaces and ending up here, Sure enough, that agrees with our algebraic result of negative 2 minus 2i, which is this point right here. What if we were to take this point and multiply it, let's say by a number that is 1 plus 2i, the number that we started with? Well, negative 2 times 1, that's negative 2. Negative 2 times 2i, that will be negative 4i. Now, negative 2i times 1 is minus 2i. And negative 2i times 2i, that's minus 4i squared. Now, these terms can combine in the middle here, so we have minus 2 minus 6i minus 4i squared. But remember that I squared is negative 1. So really this is negative 2 minus 6i plus 4. And then we can combine the two real terms and end up with positive 2 minus 6i. Well, positive 2 minus 6i, where is that on our number line? Well, that's positive 2, and we shift 6i downwards. We end up right here. And think about the geometric interpretation for a moment here. We started with this number over here, minus 2 minus 2i. And we can think of that as a vector that goes from the origin to that point. We ended up over here, this vector goes this way. And it looks like we have scaled and rotated our starting vector. And the amount we rotated it was a little bit less than a quarter turn. Well, guess what? We multiplied by this number that is a little bit less than a quarter turn from the real axis. And that's where we normally measure angles from, is from the real axis. So what we did was we took one number and rotated it by the angle of the other number. That's very consistent with what we've seen before with rotations. Or another way to think of it is that we've added the two angles together. We have this one angle, and then we have this angle to the other number, and then we added those angles together and got this big angle to this vector. Now notice, in addition to rotating, we also scaled. We scaled by the magnitude of this vector 1 plus 2i. This number 1 plus 2i has a magnitude greater than 1, so that means we scaled it. Its distance from the origin is greater than 1. So we scaled it, and it became, the number here became bigger when it was multiplied by the number over here. Pretty interesting, huh? And I think that if we were to continue this exercise, you would find that you could add, subtract, multiply, or divide any complex number by any other complex number, and you would find that the algebraic interpretation completely agrees with this visual interpretation. That's an extremely good sign that our concept here of complex numbers is consistent, and it's totally consistent with our concept of real numbers. Now, negative numbers, as I mentioned before, were not accepted for a long time, and even just a few hundred years ago, mathematicians called them things like absurd or fictitious. They eventually accepted them, but only about 100 years or 200 years ago did mathematicians finally agree upon the legitimacy of negative numbers. And I think that if you are to accept negative numbers as being legitimate, then you should also accept complex numbers as being legitimate. Now, I don't like the terminology very much. We call them complex, and we call these numbers on the vertical axis imaginary. I think that calling these numbers imaginary is a slight against them, and it would be nice if we had different terminology, but these terms are very well established, and it's not something that we're going to change overnight. I think that calling them imaginary makes them seem less legitimate, but I think that they're perfectly legitimate. Also, calling them complex. Now I can see why people call them complex numbers, because they have two parts instead of one part. That makes them more complicated. But they're not that much more complicated. It's just one additional axis. And I think that calling them complex scares people away from them. People think, oh, they're complex. They must be difficult to deal with. They're not very difficult to deal with. They take a little bit of getting used to, that's for sure. But I think you'd find that just knowing a little bit of arithmetic and very elementary algebra, and knowing this geometric or this visual interpretation, if you know these things, then you can easily master complex numbers. They're not that hard. Now let's zoom in on the unit area. So this is 1, and this is I, and so forth. What if we were to take this number I and multiply it by I? Well, we would start at I, and we would rotate around a quarter of a turn to -1. And of course that makes sense algebraically, because I is the square root of -1, so I times I equals -1. What if we were to take that result and multiply it by I? We'd rotate around a quarter of a turn and end up at -I. What if we were to take that result and multiply it by I? We'd rotate a quarter of a turn and end up at 1. What if we were to take that result and multiply it by I? We'd rotate around a quarter of a turn and end up at I. What if we were to take that result and multiply it by I? We'd rotate around a quarter of a turn and end up at -1. What if we were to take that result, and okay, you see what we're going to do here. We're going to keep going around the unit circle, around and around. Every time we multiply by I, we go around another quarter of a turn, and then this can keep going forever. Now, there's a name in mathematics for multiplying by the same thing over and over again, and it's exponentiation, or raising something to an exponent or to a power. We take I to the first power, I to the second power, I to the third power, and if we increase the exponent, we go around and around and around the circle. That's pretty cool, isn't it? It's very rare in mathematics that we have such a simple way to create a function that repeats itself, to model, potentially, periodic phenomena with such a simple method. Now, we can do this with other numbers. For example, let's take this one that's 3/8 of the way around the circle. Let's call that z. Well, if this is z to the first power, its angle is 3/8 of a turn from the positive real axis. So if we multiply by z again, then that means we go around the unit circle 3/8 of a turn to here, and that's z squared. If we were to multiply by z again, we would go around 3/8 and end up over here. That's z cubed. If we were to multiply again, 3/8 of the circle is over here, z to the fourth, z to the fifth would be over here. We keep going around and around and around the circle. And we could choose numbers that aren't even on the unit circle. If we chose a number, say, right here, well, the next number would have this amount of angle more than where we started from. If this were z to the first, well, z to the second would be about that much of an angle, but it would be a little bit further out from the origin because z has a magnitude or a distance from the origin that's greater than 1. So we would scale and rotate. So that would be z squared. Z to the third would be out here somewhere, and z to the fourth would be out here. We would spiral out away from the origin. What if we had a number that was inside the unit circle? well, the next one would be here, and the next one would be here. It would spiral in towards the origin. But if we choose a z that is on the unit circle, any number that's on the unit circle, and exponentiate it, we will always end up with another number on the unit circle. And if we increase the exponent, then we just go around and around and around and around. Now, let's say we start here, and let's say we increase the exponent over time. So I want you to imagine a new axis, a third axis, coming out of the screen right at you. And we're going to progress along this axis. So this first one is right on the screen. The second one is a little bit closer to you. This third one is a little bit closer to you. And each one gets a little bit further closer to you away from the screen. And they're getting closer and closer and closer to your face. As we increase this exponent, what figure are we tracing in 3 dimensions? Can you visualize the shape in 3 dimensions as every one of these x's gets closer to you?
It's a helix, just like this toy.
Let's choose a z, or a base, that is just 1 degree of rotation around the unit circle. So this is z, or z to the first power, and that's 1 degree around the circle. If we square z, we'll go 1 degree further. It's kind of hard to draw here, but this number z squared is 2 degrees around the circle. Z to the 45th power is right here. It's 45 degrees around the circle. Now where would z to the 180th power be? It would be a half turn around the circle to this point right here. Z to the 180th power is 180 degrees around the circle, and of course z to the 180th is equal to -1. Now what's z to the 360th? It would be 1 complete turn around the circle back to the positive real axis. 1 is of course equal to z to the 0th power, because anything to the 0th power is 1, and that's equal to z to the 360th power, and it's equal to z to the 720th power, and we could keep going on and on and on, around and around and around the circle, and keep finding larger and larger exponents that would give us the same results that we got with smaller exponents, because this function is periodic. And this particular z would be a convenient base to use if we wanted to use this complex exponentiation to represent degree measure in the complex plane. But it's not the base that most people use for this sort of thing. The base most people use for complex exponentials is right around here somewhere. We'll call that z. If that's z, then z squared is over here, and z cubed is here, z to the 4th, z to the 5th, z to the 6th, and when we get back to the positive real axis and make a complete turn, that's z to the 6.283185, etc. And some of you are probably saying, aha, I know this number 6.28318, and so forth. That number is tau. Now some of you might be saying, tau, I've never heard of this number tau, but I bet you've heard of this number by a different name, and that name is 2 pi. Now if you haven't heard of tau before, I recommend reading the Tau Manifesto. It will tell you all about why all the cool kids are using tau these days instead of pi. But just remember that when I use tau, I just mean 2 pi. It's the exact same thing. Now the reason that it works out that tau of exponent is equal to 1 complete turn of rotation is because this arc length, this amount of circumference from 1 to z, is equal to 1, or it's equal to 1 radius. In other words, the angle of z is equal to 1 radian. And radian angle measure is, of course, preferred by all sorts of people, scientists, mathematicians, engineers. Everyone likes to use radian measure instead of degree measure. And this particular z happens to be equal to e to the I, where e is Euler's number, 2.71828, and so forth. You might have heard of this number before. And it works out that e to the I theta, let's just designate some number here, e to the I theta is the number along the unit circle that has angle theta with respect to the positive real axis. That's a very special thing to remember, e to the I theta, or e to the I of whatever angle you want in radians. So for example, z squared, that's e to the I squared, and following the rules of exponents, that's e to the I times 2, or e to the 2i. And of course, this number, if we were to take a complete turn around the unit circle, this is e to the I tau. That equals 1. A half turn around the circle is e to the I 1/2 tau. Oh, that's interesting. A quarter turn around the circle is e to the I 1/4 tau. Do you see how easy it is to use tau here? A quarter turn is a quarter tau. Now, the pi people are fond of pointing out that this number over here is e to the I pi. That's -1. And they usually rewrite it as e to the I pi plus 1 equals 0. And they say, look at that. Is that not the most beautiful equation in all of mathematics, relating all these fundamental numbers to each other? And I say, well, this one is more beautiful. I mean, it relates all these fundamental constants to unity. What could be more beautiful than that? Now, if you look through the literature, the digital signal processing literature, or really any literature of any subject that studies periodic phenomena, you'll see all sorts of equations with terms that look like this: e to the I 2 pi ft, stuff like that. And it might look scary at first, but keep this in mind. This is a constant, this is a constant, this is a constant, this is a constant. This probably is frequency, that's a constant. And all we're doing is taking some number on the unit circle and exponentiating it over time. It's a helix. This whole big scary term is just a helix. And you'll see these all over the place. So don't be scared of those. Every time you see e to the I something, it's a helix. Now, remember the unit circle from trigonometry? If you studied trigonometry, you might have been presented with something like this, where you saw this angle theta going to a point along the unit circle, and you might have been shown that this distance along the horizontal axis was cosine of theta, and this distance vertically to that point was sine of theta. And you might have even been told that that's how cosine and sine are defined. And it turns out that this works out quite nicely with e to the I theta. In fact, e to the I theta is equal to cosine theta plus I times sine theta. And this result is quite interesting. That is called Euler's formula. It's one of many things that is named after Euler. And it relates e to the I, it relates the complex exponential to cosine and sine. Now, one way to think of this is if you visualize remember a helix that's going around and around and around the circle. If you imagine this coming out towards you, away from the screen, and then you imagine, well, what is the real part of each of those numbers as we go around and around and around the circle? Well, the real part starts at 1, and it kind of slowly starts towards 0, and then it speeds up, and then it goes towards -1, and then it slows down, and then it goes back towards 0 and speeds up, and then it slows down, and then it's back here at +1, and then it goes back and forth as the helix goes around and around and around and around and around. This is easier to see in 3 dimensions. If you look at a helix and you look at it from the side, it looks sinusoidal. If I look at it from this direction, it looks like a cosine wave, and if I look at it from this direction, it looks like the same thing, except it's shifted. It's a quarter of a period out of phase, or a quarter of a turn out of phase. Notice that I've actually changed the orientation that I'm viewing it from by a quarter of a turn. Now I'd like you to do me a favor, just a tiny little favor for the rest of your life. Every time you see something that looks sinusoidal, imagine the 3rd dimension. Imagine that it is a helix, instead of seeing it as a 2-dimensional figure. Now here's something your trigonometry teacher probably didn't tell you. The most useful application of trigonometry is the study of periodic phenomena. That's the reason why people consider trigonometry to be an important field of study. It's because it's so useful for periodic phenomena. But here's something else your trigonometry teacher probably didn't tell you. You can use complex exponentials instead of trigonometry for the exact same applications. And if you just get comfortable with complex numbers and comfortable with the algebra of complex exponentials, you don't have to use trigonometric functions at all, and you never have to memorize any of those trigonometric identities that you might recall from your trigonometry studies. Now I want to point out that there are 2 completely different ways that people represent numbers in the complex plane. One is in rectangular coordinates. In other words, this point is 3 to the right and 4 up, so it is 3 plus 4i. Or you could represent that in Cartesian notation, 3, 4, but I recommend using the algebraic notation, 3 plus 4i. And that's called a rectangular coordinate because we're describing that point in the complex plane by its horizontal and vertical components. Now, another way that people sometimes represent complex numbers is in polar coordinates. They tell you what the distance from the origin is. You might call that a radius, or r. And then they'll tell you what the angle is. I'll call that theta, from the positive real axis. And sometimes people notate this as r at an angle of theta. But really that's just shorthand for r times e to the I theta. Remember, e to the I theta describes a point along the unit circle, right around here, that has that angle. And then we multiply that unit vector by r, and that gets us out to this point here. So 2 completely different ways to represent the same number. You can do it in rectangular coordinates, and sometimes people will say a plus bi or something like that, or in polar coordinates where you use r times e to the I theta, or r at an angle of theta. And sometimes polar coordinates are more convenient than rectangular coordinates, and at other times rectangular coordinates are more convenient than polar coordinates. For example, rectangular coordinates are quite convenient for addition and subtraction, but polar coordinates are quite convenient for multiplication and division. Now, unfortunately, there are a lot of different terms that mean the same thing when people talk about complex numbers. For example, the distance from the origin. Now, I've called this probably 3 or 4 things already just today. I've called it the distance from the origin, I've called it a radius, I've called it probably a magnitude. It's also sometimes called a modulus, and it's sometimes called an amplitude. It's amazing how many different words we have for the same thing. But this R here could be referred to in any of these different ways. It's also referred to as the absolute value. Now, you've probably heard of absolute value before in the context of real numbers. Of course, the absolute value for a real number is its distance from the origin. And we use the same terminology sometimes to refer to the distance from the origin of a complex number. And in fact, in Python, for example, in Python you would use the absolute value function to give you a point's distance from the origin, any point in the complex plane. And we also have multiple words that refer to the angle, like this angle theta. The angle is sometimes called an argument, and it is also sometimes called a phase, although usually when people say phase, they mean something a little bit more specific than just the angle from the positive real axis. But any of those 3 words in certain contexts could mean this exact same thing. And we even have multiple words for a number itself. Now, I call this number, this point, I just call it a number or a complex number, but sometimes I might call it a vector because I'm specifically thinking of it as this vector that points from the origin to that point. Sometimes people call it a phasor, although most of the time when they use the word phasor, they're talking about a vector that is rotating around the unit circle or rotating around the origin over time. But all of those numbers can, in some contexts, mean the exact same thing. All of those names can mean the exact same thing. They can refer to a complex number. There's one completely different set of terms that you should know before we finish, and that's the terminology of quadrature signals. And this terminology comes from signal processing and electronics. The horizontal axis is called in phase, and the vertical axis is called quadrature phase. And the thing that can get confusing is that these are typically abbreviated. So the horizontal axis is called I, and the vertical axis is called Q. Now, do you see what can be confusing? I is what you can think of as the real axis, not the imaginary axis. Fortunately, this I is capitalized, and the imaginary unit from mathematics is always lowercase. Now, you'll hear people talk about I and Q sometimes, or they'll talk about IQ samples, or they'll talk about a quadrature sampling system. For example, HackRF is a quadrature sampling system, and it delivers samples to the host computer one at a time. I followed by Q, and then the next sample's I followed by Q. It delivers this stream, I, Q, I, Q. And let's say the first I was 2, and then the next Q was 3, and then the next I was -2, and the next Q was 4, and so forth. If that were the case, then you could think of this first I and Q being a complex number 2 plus 3i. And you could think of the next pair, I and Q, as being -2 plus 4i. It's just a different way to refer to something that can be thought of as complex numbers. For homework for this lesson, I'd like you to write a small computer program. You can write it in any language that you choose. And if you're not a programmer, that's okay. Take a look at the exercise and think about how you would approach the problem. What method could you use to solve the problem, even with pencil and paper? And think about what method you could use that would actually work for all different inputs.
Now, the exercise is adapted from an exercise in Practical Signal Processing by Mark Owen. It's my favorite introductory book to digital signal processing. So thanks to Mark Owen for writing such a good book and for teaching me this exercise. Go to greatscottgadgets.com/SDR and take a look at the Lesson 6 homework, and that's where you'll find the exact problem that I'd like you to solve. I hope to see you next time in Lesson 7. Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 7, Complex Numbers in DSP. In this lesson, we'll talk a little bit more about complex numbers and why we use complex numbers in digital signal processing. Let's start by reviewing the homework from Lesson 6. For this exercise, I'm using IPython Notebook, which is a convenient way to use the Python programming language. You could complete the Lesson 6 homework assignment using any programming language, but I'm using Python for a couple of reasons. One reason is that Python is one of the languages you can use to write GNU radio programs, and in future lessons, we'll look a little bit at how to use GNU radio from Python. And another reason I like to use Python is because of IPython Notebook itself, which is a very convenient way to interact with Python, and it's a nice way for me to show you what I'm doing. Now, the Lesson 6 homework assignment was a problem that I asked you to solve. I asked you to create a program that would compute the average of a set of wind direction readings. And so one way you might approach this problem would be to create a function. I'll define a function called average, and the input to the function will be readings. Now, how are you going to solve this problem? The first solution that you might try is to simply take a simple average or a mean of the inputs. So one way to do that would be to start with a total at 0 and then add to it. This is kind of a verbose way to solve this problem. I'll say for r in readings, which means I'm going to loop through every reading, no matter how many there are, and in this loop, each time I'll set r to that particular reading. And then I'll take total and add r to it. So at the end, I can return a result, which is return total divided by the number of readings, or the length of readings. Now this is just a simple average. We add them all up and then divide by the number of readings. So let's see what we get when we try this. If I call this function average, I'll call it with the first list of readings that I told you to try. 12 degrees, 15 degrees, 13 degrees, 9 degrees, and 16 degrees. And the function returns 13, and that looks like a pretty good result. Now let's try the second set of readings I asked you to try. 358 degrees, 1 degree, 359 degrees, 355, and 2. And what do we get? 215. That's interesting. And I would say that's completely wrong, because if you look at these numbers, they're all very close to 0, or very close to 360 degrees, which is the same as 0. And then we take the average and we get this number 215. Well, 215 degrees is nowhere near 0 degrees. It points almost in the opposite direction. Well, let's see. Average. Let's try the third one. The third set of numbers I asked you to try was 210 degrees, 290 degrees, 10 degrees, 90, and 170 degrees. And these are kind of all over the place. And the result it gives us is 154. And off the top of my head, without doing some more math or drawing this out on a piece of paper, I can't really say how good a result that is. So we clearly have a problem here with this particular input, this particular set of inputs. And one way you might think of to solve this problem is to normalize the input so that maybe instead of 358 we say -2,
negative 2 degrees. This should be the same as 358. Or, on the other hand, maybe we could, we could leave that as 358. And instead of saying 1 degree, we could call this 361 degrees. And then maybe that would work. Let's try one of those approaches. If we just put a conditional in here, if R is greater than 180, say, then we'll subtract 360 from R. Let's see if that works. Now, if I execute the first set of readings gives me the same result, 13. And the second set of readings gives me negative 1. Hey, that looks good. That's very close to 0. Negative 1 degrees. That's the same thing as 359 degrees, which is right there. And let's see, the third set now gives us 10 degrees. I'm not really sure if that's good or bad. Let's try another set. Let's try something that's near 180 degrees. 170, 171, 180, 181, 190. So we should get a result somewhere around 180 degrees. And we don't. We get 34. Now, why did that happen? That happens because we took the problem here, the problem that we had around 360 degrees, we shifted that problem around. We avoided it by shifting it over to 180 degrees. Now when we have results or inputs around 180 degrees, this thing goes haywire. Now hopefully some of you tried this approach and at least got this far to recognize that using the method of a simple average is not correct for this problem. And if you came up with an actual solution for this problem that works with all possible inputs, then I think what I've seen, the only solutions I've seen that actually solve this problem are solutions that take into account the two-dimensional nature of these directions. And in general, the right way to approach this problem, I think, is to approach it as a vector addition problem. So the error here in our method, I think, is right here. We add up all of these values as if they're one-dimensional, but they are in fact two-dimensional, or vectors. So I'd like to show you my solution to this problem, and to solve this, I of course use complex numbers. You don't have to use complex numbers to solve this problem, but I think that complex numbers make vector arithmetic very easy, and it's a convenient way to conceptualize how to solve this problem. So let me show you what I do. The first thing I would do is to import CMath, or import the complex math library, and then define tau to be equal to 2 times pi. I have a lot of programs that start this way. Now, I will use the same function name, same inputs, but I'm going to start by defining a base. I'm going to exponentiate this base. I'm going to use a method of complex exponentials. And the base that I'm going to use is e to the, and then the stars here are the double star operator in Python is the power or exponent operator. So e to the 1j, and 1j in Python is the imaginary unit. So you can think of that as pi. Now if I just stop there, that would be, this point, this base would be a complex number that is on the unit circle and is 1 radian around the unit circle from the positive real axis. If I multiply that by tau, that makes it 1 turn around the circle. So this ends up back at 0 degrees or at 1. And then if I divide that by 360, now I'm dividing the angle of the unit circle. I'm dividing a complete turn into 360 parts. In other words, base is now the complex number that is on the unit circle and is exactly 1 degree of rotation above the positive real axis. And this is a very convenient base to use if we want to manipulate degrees. So I'm going to take the same method and start with total, and I'm going to take a simple average, but now the average is going to be of these complex numbers instead of being an average of degree measure. I'm going to not do this trick that didn't work. And instead of adding up R, I'm going to add up base to the R. So if R is 1 degree, then I'm adding the complex number, or the vector that goes from the origin to that point that is 1 degree around the unit circle. If R is 45 degrees, then base to the 45th power is the complex number that is 45 degrees around the unit circle. And then I'm going to, I don't want to actually return the complex number result. I prefer to return a result that is in degrees and is the real value result. So I'm going to add an additional step here and say result, or my resultant vector, the average, is equal to total divided by length of readings. Same expression we used before, but now the actual return value that I'm going to use is cmath.log. Wait a minute, what am I doing here? I'm taking a logarithm of the result. Now remember that a logarithm is the inverse operation of exponentiation. So if I take the base to a power, and that power is a number of degrees, to find some point in the complex plane, then to reverse that operation, if I have a point in the complex plane and I want to find the number of degrees, then I use the inverse function of exponentiation, which is a logarithm. And I use the log function from the CMath library specifically. And I'm doing one thing wrong here I have to fix. I want this logarithm to be with respect to my base. So it's a logarithm base this thing. Now let's see what result we get. If I execute this function on the first set of readings, which previously gave me 13 when I used a simple average of degrees, now I get a number very close to 13. However, it has this extra little imaginary component. And the reason it has this extra little imaginary component is because my result isn't actually on the unit circle, and I'm doing a complex logarithm that is with respect to a base that is on the unit circle. So there are a number of ways to correct this problem, but notice that just the real part is basically the answer we were looking for. And so for now, I'm just going to say that a good way to, or an acceptable way to solve this, avoid this problem with this complex result, is just to take the real part of the result and ignore the imaginary part. Now let's see what happens when I try it on these other sets of inputs. This one here that seemed to be about -1 degree. Sure enough, I get a result that's very close to -1 degree. And this one, with numbers that are all over the place, this gives me -170 degrees. That's the same as 190 degrees going in the other direction. And this one that should be somewhere near 180, I get 178 degrees. That looks pretty good. I think we have now a function that does the job. This is one way to solve this problem. We're doing vector addition and then taking the average of those vectors and then using a logarithm to convert back from that vector in the complex plane into a number of degrees. And we're using this trick of using exponentiation and logarithm with respect to this base, this special base. Now the second thing I asked you to do in the homework assignment was to also consider the wind speed in addition to the wind direction. So one way that you might do that would be to maybe make your list of readings be something that includes both speed and direction. So you might specify, instead of specifying 12 degrees, maybe you specify 12, 1. And that's, say, 12 degrees of direction and 1 mile per hour, or whatever unit you're using, and then 15 degrees, comma 1. Each of these is a pair of values. And if we give them all the same value, we should end up with the same result that we had before. If they're all equal to unit speed, we should get the exact same result. But if we enter in different speeds for different directions, we should weight the result toward that direction. So I'm going to use basically the same approach, except here when I take a total, when I exponentiate my base, I'm going to say, instead of r, I'll say r sub 0, which is the first part. It's the 0th index of this pair. So r0 is this 12 degrees. And then I'm going to multiply this base by r sub 1, which is the second number. R1 is the second number in a reading, and that's the speed. So notice what I'm doing is I'm just multiplying or scaling this number in the complex plane. I'm scaling that vector by the amount of speed. So I'm increasing its distance from the origin if the speed is high, or I'm reducing its distance from the origin if this number is low. And then I'm going to use the same approach, take a simple average of these vectors, and they're two-dimensional values, not one-dimensional values, and see what we get. So theoretically, this should give me the exact same result that it did before, and it did. And if we weight it, let's say we had a big gust of wind when it was 9 degrees. Let's see what happens. Look at that. My average reduced closer to 9. This seems to work. Now, interestingly, I'm only returning degree or angle information here. But what happens if we also return the speed, or the average speed? What I'm going to do is take the absolute value of the result. That is its distance from the origin. So if I return that as a tuple, now my result is 10 degrees with an average wind speed of 2.8. If I set this back to 1, and all of them were about 1, then my average should be near 1. It is very close to 1. Now let's see what happens. I'm going to try these other values. And I think I'll skip ahead in the video here so you don't have to watch me type all of these. Now let's try this new function on all these other inputs. If I take this one, I still get a direction very close to -1, and I get an average speed very close to 1. That makes sense. Now I'll try this third set of inputs. Now I still get the same average direction of -170 degrees, but now look at the average speed. The average speed is very small. It's only about 1/10 of a unit of speed. And if you think about what's going on here, what we're doing is we're taking an average of a bunch of vectors that are going all different directions. And it turns out that their result is pretty close to the origin, which means that this average direction of -170 degrees is a weak result. And so this actual output of speed, or the magnitude of the average wind direction and speed, actually gives us some indication of how much overall wind motion there's been, or how much average motion of air there's been. And since it's moved a lot in different directions, those different directions have canceled each other out, and we end up with a very small average, or a weak result. Now, maybe it was a really gusty day. Maybe this was 3 miles or maybe 15 miles per hour that direction, and 10 miles per hour this direction, and 1 mile per hour in that direction, and maybe 3 miles per hour in that direction, and 6 miles per hour in that direction. Now in this case, we end up with a different result vector that is negative 138 degrees. It's a little bit of a different direction, and a much higher average here because we have more speed going roughly the same direction and then weaker speeds when we're going different directions. So this whole approach of doing vector addition gives us a really nice indication of perhaps a confidence value or an average error motion in this case. Now let's try it on this last set of values. I end up with a very similar result, 178 degrees, and the average speed of 1. Unless I tweak some of these, then things change a little bit. Now, I'd like to plot this a little bit and just visualize so you can kind of see what's going on here. And I'm going to use matplotlib. And I'll just type a little bit and skip the video ahead so you don't have to watch me type all this. Now my function returns the exact same thing, but I also plot a couple of things. I plot each input vector, and I plot the result vector, or the average of all of those inputs in the complex plane. Let me show you what happens when I try it on this first set of readings. Here we go. We get bunch of red inputs that all extend from the origin in roughly the same direction, and this blue result is right in the middle. And if we play the same trick of making these different values, then maybe we'll make this one 0.5 and this one 0.2, and now you can see we get different little vectors here, but their average ends up in roughly the same place. Now let's try this next set of inputs. In this case, again, we have a bunch of readings that are clustered around 0 degrees, or clustered around one place, and we get an average, this blue vector, that points in that direction. And for this third set, now we have numbers that go all over the place. And you can see I'm going way off the screen here because I'm using some numbers that are much larger than some wind speed numbers that are much larger than our original ones. But let me just try kind of putting these all into scale here. Now you can see if these different wind speeds, if these different wind measurements had different speeds, then the preponderance of the wind, or the average air motion, is in the direction of the blue vector here. But if these all have the same speeds, or if we have no speed information, and we just have to assume that they're all the same, then we end up here with all of these input vectors at the same distance from the origin, but the output vector is very, very weak and in a slightly different direction. And if we take all these numbers that are near 180 degrees, we should see, yes, they all point to the left. And if I give them all the same magnitude, or the same distance from the origin, or the same wind speed, then this is what it looks like, and we get this blue vector resultant right in the middle. My approach to solve the Lesson 6 homework might not be the best approach or the most efficient approach, but I think that it is a conceptually interesting approach. I think it's great that we can use complex numbers to express the solution to this problem in Python. Now, I'd like to talk about why we use complex numbers in digital signal processing. Hopefully you've gotten a little bit of a taste of how complex numbers can be useful, but you may still be wondering why we use them so much in digital signal processing. You've seen those blue inputs and outputs on blocks in GNU Radio Companion, on so many blocks. That's the complex data type. Why is the complex data type the default for so many blocks that are useful in GNU radio? Well, there are a lot of answers to that question, a lot of reasons why complex numbers are useful in digital signal processing. One of those reasons has to do with the hardware, and HackRF and other software-defined radio platforms are quadrature sampling systems. That means that the input and output over the USB connection is actually a series of complex numbers. So that's something that we'll talk about in the future, the architecture of the hardware and why quadrature sampling is useful. But that's one reason that we use complex numbers in digital signal processing, because that's what the hardware gives us, or that's what the hardware expects when we want to send samples for it to transmit. Another reason that we'll talk about in more detail in the future has to do with the FFT. You've seen the FFT algorithm in action using the FFT GUI sync in GNU Radio Companion. And the FFT is a wonderful and interesting algorithm that we'll talk about in more detail in the future. But something that you should know about the FFT right now is that the FFT is inherently a complex function. It takes complex input and it gives complex output. And when you use the FFT sync in GNU Radio, what you're seeing is a display of the magnitudes of a bunch of complex numbers. We're throwing out the direction information and just showing the magnitudes. And for the rest of this lesson, what I'd like to talk about is some specific examples of modulation, how we encode information on radio signals, and how we can decode that information by demodulating radio signals. The first modulation I'd like to talk about is amplitude modulation, or AM. The way that AM is traditionally visualized is as a sinusoid that varies over time. And if I do a good job of drawing it, you should see that the amplitude changes over time, but the frequency should not. So the peaks should be at approximately the same amount of time along the time axis from one another. So the frequency doesn't change over time, but the amplitude does. And specifically, what we see is this envelope, or the bounding function around the sinusoid, is something that changes over time. And this envelope is what actually carries the information. Now, it might be an analog envelope, like AM radio that you listen to that carries audio. That's an analog audio signal that is used as the envelope function. Or in this case, what we might have here is a digital signal. Maybe this is a 0, and then when the amplitude is high, it's a 1, and then this is a 0 over here, and then another 0. That would be what we'd call ASK, or amplitude shift keying. Amplitude shift keying is just a name for digitally encoded data, or it's the modulation in which we use amplitude to digitally encode data. Now, remember that in a software-defined radio signal, what you actually receive in software is a series of samples at discrete points in time. And so think of every little red X here as being a number. Sometimes it's a positive number, and sometimes it's a negative number. But what we get if we're trying to build a software-defined radio receiver is a series of numbers over time. Now, what I want you to imagine for a moment is that you're designing a software-defined radio receiver, and you receive this list of numbers, this sequence of red X's. How would you recover the information? How would you demodulate this sequence of red X's to reproduce the envelope function and determine whether a 0 or a 1 was sent at any particular point in time? Think about that for a moment. Can you propose an algorithm that you could use to take this list of numbers and turn it into the data that were originally transmitted? One thing you might think of is to rectify the signal. And a way that we do that in software is by taking the absolute value. So the positive values are unchanged, but the negative values are mirrored across the time axis and become positive values. This is an absolute value function where we just take the magnitude of each sample and take it as a positive number every time instead of a negative number. Now this is one way to rectify the signal, and you may have heard the term rectification from analog electronics, where people might use a diode, for example, to rectify a signal, instead of here in the digital domain, where we might use something like an absolute value function. So that would be a rectified signal. However, we still have this problem where, what if we look just at this sample right here? Well, it looks like 0. But is the amplitude 0 at that point? No, it's not. What we really want is the envelope, not that particular 0 value. That 0 crossing might mess us up. So what we really need to do then is to take a rolling average over time, an average of these samples, so that the average over time is going to look something more like this envelope curve. But in order to do that, we have to average several samples in a row, several of these dark blue x's in a row, in order to produce one x of average. So how many samples in a row do we have to compute this average over? Well, in this case, it looks like we might have to compute it over at least 4 or 5 samples, but it all depends on your sample rate and the frequency of the signal, the carrier frequency we call it, and the ratio between your sample rate and the carrier frequency. If the sample rate is very high compared to your carrier frequency, you might have to do this averaging over a much larger number of samples, maybe tens of samples or hundreds of samples or even thousands of samples. And that is a lot of CPU power that you need just to produce one output sample that tells you that we have a 1 that was transmitted instead of a 0 that was transmitted. It's a whole lot of processing. Now what I'd like you to do is to imagine that this is represented as a complex number instead of as a real number. So instead of seeing a sinusoid, imagine that that green curve is actually a helix, and you're just looking at it from the side, and the helix grows larger and smaller over time. Now if you look down the time axis, we can plot this in the complex plane. And what we should see is, instead of something that looks like this, varying in this just one dimension over time, we should see something varying in 2 dimensions over time. And it has a low amplitude or a low distance from the origin, and then it becomes a higher amplitude. It's bigger around, and then it becomes a lower amplitude again, and it's a low amplitude for a long time, and we see something that looks kind of circular if we look down the time axis. But again, remember that what we really get is a series of samples over time. So if it were to be a low amplitude for a while, we'd get a series of samples like so, and then if the amplitude were to increase, we would see a series of samples like this. And eventually, if we keep going around, we'll get samples that are low again, or have a low magnitude. They're closer to the origin here. Now, if we were to represent this signal as a series of complex numbers like this, instead of representing the signal as a series of real numbers, now can you propose an algorithm that you could use to extract the envelope information? Think about this for a second. How many samples do you need at a time to compute the distance from the origin? Notice that we no longer have this 0 crossing problem. This signal never actually goes through the origin. And so all we need to do if we want to demodulate or recover the amplitude information over time, is look at this distance from the origin of this one sample. Then look at the distance from the origin of that sample. Then look at the distance from the origin of that sample. If we think of each of these as a vector and just take its distance from the origin, now this sample is a little bit bigger. This sample, now we seem to have a high amplitude. So this may be this region here where we had a 1 transmitted. And eventually we'll go back to a lower amplitude. Now, how do you compute the distance from the origin? Well, it depends on how your sample is represented. But if you have IQ quadrature information, then what you have is you can think of as a horizontal component and a vertical component. You have rectangular components. So if we wanted to find this first sample here, take its magnitude, or its distance from the origin, then we would take its I value, which is this horizontal component, and then its Q value, which is vertical component, and we could use the Pythagorean theorem, and this distance from the origin would simply be the square root of I squared plus Q squared. Now think about this for a moment. How many samples at a time do you need in order to compute this? Remember that up here we needed to average several different absolute values of samples together. And it may vary how many samples we have to average together. It could be a whole lot of samples at a time that you need to get one output value. How many samples at a time do you need to compute this algorithm over in the complex view of this signal? It's only one sample. You only need to compute this over one sample at a time. And here's something that could make this algorithm even simpler. Notice that the only really hard part is taking the square root. Squaring a number is very easy for a computer to do. Adding two numbers together is very easy for a computer to do. But taking the square root is harder. And it turns out that in many cases we can just skip that step. If all we're doing is comparing the result to a threshold, then it doesn't really matter if we have the magnitude or if we have the magnitude squared. So we can skip that and just compute I squared plus Q squared, or the real part squared plus the imaginary part squared. Isn't that an amazingly simple algorithm to demodulate a signal and recover this envelope over time? I think that's pretty neat. The next modulation I'd like to consider is frequency modulation, or FM. The way that FM is traditionally visualized is again as a sinusoid over time, but this time instead of the amplitude changing, we'll see the frequency change. We'll see a shorter period, and if I've done a good job of drawing it, then you should see that the envelope does not change over time. The amplitude is the same, but the frequency gets higher and then lower again. So remember that if we are building an FM receiver in software, we actually get a series of samples that are discrete points in time. Now, think about this for a moment. If you were to be given this list of samples, this sequence of red X's, some of them positive, some of them negative, what algorithm could you use to decode this information or recover the frequency over time? You should be able to recover a low value over here, and then a high value, a high frequency, and then a low frequency again. It may be the exact same information. Perhaps this is not ASK but FSK, frequency shift keyed information, and this is a 0 and then a 1 and then a 0 and then a 0. It could be the same exact information, just using a different modulation to encode that information onto this carrier wave. So you're given this series of red X's. Can you propose an algorithm that you could use to decode this information, to extract the instantaneous frequency over time? Now this might be a little bit harder than thinking about AM demodulation, but one thing that you might propose is to look at how often these peaks happen. Or another thing you might propose, like notice that these peaks are very close together and then they're further apart. However, that is potentially error prone if we have much noise in the signal. Another thing you might propose is to look at these zero crossings. How far apart are the zero crossings? They're closer together and then they're further apart. But again, things might be error prone. What if you have a little bit of noise in your signal? Each of these samples is randomly moved up and down a little bit. You might have some extra little zero crossing somewhere that could throw things off. So you have to do some kind of smoothing over time. You have to make sure that your signal is normalized so that you can, like if you're looking at zero crossings, you need to make sure that your signal actually crosses zero and doesn't do something like this, where it never crosses zero, or it just crosses zero on rare occasions. There's a bunch of work that you have to do, and every algorithm that I can think of that would do this for a real valued signal like this, without thinking of it as a complex number, I think would have to compute something over quite a few samples at a time, similar to the problem we had with an AM demodulator. And the amount of samples that you have to compute over at the same time is dependent on a number of factors that aren't entirely in your control, perhaps. So again, you might have to compute over tens or hundreds or more samples at a time just to get one output value, just to determine whether or not this is a 1 here versus a 0 over here. So now I'd like you to think of this as a complex valued system. And so instead of seeing a sinusoid, imagine that this is a helix and you're just looking at the helix. This green curve is a helix that wraps around the time axis. So if we were to look down the time axis and look at our complex plane, we should see this curve does something like this. It goes around slowly and then around faster and then slowly again. If I were good at drawing, it would pretty much just look like a circle. But the rate at which it advances around the circle changes over time. Sometimes it goes around slowly, sometimes it goes around fast. And if there isn't very much noise in the signal, it should look very much like a perfect circle. So remember that this is going to be a digitized signal, and so you'll see a sample here, and then a sample here, and then a sample here, and so forth, while the frequency is low. But then what happens when the frequency increases? We'll see the next sample here, and then here, and then here. Notice that we move around the unit circle faster, or around the origin faster. From sample to sample, the angle increases. So now think about this. If we have a complex valued signal that is an FM radio signal, how would you extract the frequency information over time so that you could decode this signal? Well, the method that I would propose is to look at each of these as a vector and look at two samples in a row and measure the angle between them. It's a low angle, then it's a low angle, then it's a low angle, then it's a low angle. And the angle maybe gets a little bit bigger, and then quite a bit bigger. And now we're dealing with a very large angle from sample to sample. So this is the information that we're looking for right here in the angle. So just the only thing that we have to do to recover frequency information from this signal is to measure angles, or to compare the angle of one sample from the next. So one way you might do this is to take the angle of each sample with respect to the positive real axis here, this angle, and then take the next angle from the positive real axis and subtract one from the other. So it's determining an angle twice and then subtracting. Of course, subtracting is very easy, and determining the angle may not be. Remember that this is a IQ. So what we have at our disposal is the information of how far over this way and how far up this way this sample is here. And in order to determine the angle from those two numbers, I and Q, can you think of a way to do that? Well, one way that I used in my program that I talked about as my solution for the homework from lesson 6, one way is to take a complex logarithm of that particular point in the complex plane. And another way you might think of is an arctangent function. Either way, how is that going to be implemented in a computer? It's probably going to be implemented with a lookup table. So what we do in order to compute the instantaneous frequency at any given sample is to do a lookup for one sample, lookup for the next sample, and then subtract those two values. And the result is the frequency, or the instantaneous frequency, from sample to sample, or between those two samples, we get its instantaneous frequency. So how many samples do we need in order to compute the instantaneous frequency? We need 2 samples at a time. And then we can move on. We could start with these 2 samples, and then we can move on to these next 2 samples overlapping the first set of 2, and then we move on to the next 2 samples, and so forth. So we can get an output value for every single input value that we receive, or every single input value minus 1. And we only have to compute over 2 samples at a time. It doesn't matter what the carrier frequency is, it doesn't matter what our sample rate is, it doesn't matter how much noise there is. Well, it matters a little bit, but it's not going to throw off our algorithm as much as, say, spurious zero crossings would up here. So we have what I think is a much simpler algorithm, and something that can be computed very easily and very efficiently by a general purpose computer.
The homework for this lesson is listed at greatscottgadgets.com/SDR under Lesson 7. And what I'd like you to do is to look for a couple of different blocks in GNU Radio Companion that do the exact algorithms that we talked about in this lesson. I hope I'll see you next time for Lesson 8.
Hi, I'm Michael Ossman of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 8, On-Off Keying. In this lesson, we will receive and analyze a radio signal from one of the simplest types of digital radio transmitters, a garage door opener remote. The first thing we'll need to know in order to receive the signal from this device is its frequency of operation. There are technical means of determining the frequency, but my favorite method is to use the FCC ID that is printed on the device. Let's see what public information the FCC makes available about this equipment. If you direct your web browser to fcc.gov, you'll go to the website of the Federal Communications Commission, or FCC. The FCC is a government agency that manages radio spectrum in the United States. Now, of course, there are agencies that manage spectrum in other countries, but the FCC is unique in the tremendous amount of information that it makes available to the public about equipment authorized to use radio spectrum. We're going to look under Tools and Data, Data. And if the FCC website changes, you'll probably be able to find this by looking for the word Data. And then under Data, search FCC databases. There is a long list of databases available for us to search, and we are going to look at the Equipment Authorization Search. We're interested in equipment, this garage door opener remote, that is authorized to transmit radio signals within the United States. And here we find, under Equipment Authorization Search, that we can search for a variety of fields. We're only going to use the first two fields, the grantee code and the product code, which are portions of the FCC ID that is printed on the device. A grantee is the organization that is granted this authorization, and then the product code is the particular device, and that code is issued by the grantee. In the case of the garage door opener remote that I have, the complete FCC ID is HBW2392, and the first three characters there I should cut and paste into the grantee code, because the first three characters are the grantee code and the remaining characters are the product code. Now, in the past, all grantee codes were 3 characters long, but the FCC has recently begun issuing 5-character grantee codes. So for newer equipment, you may find that the FCC ID consists of a 5-character grantee code and then some number of characters of a product code. But most equipment, you'll find, has a 3-character grantee code, and then the rest of the code is the product code. But it isn't always clear exactly where the delineation is. So watch out for that. You might misinterpret a 3-character code as being a 5-character code, or vice versa. Once we have the grantee code and the product code entered into this form, we can start our search and see a listing of the authorizations for this device. And this device is kind of interesting because all on the same date in 2007, this device was granted authorizations to operate at a number of different frequencies between 300 megahertz and 390 megahertz. I'm going to look at the detailed listing for one of these, and this should bring up a list of documents in PDF format that I can look at. And one of the first things I like to look at is the external photographs. The reason I like to look at external photographs is because it helps me verify that this is, in fact, the device that I have in my hand. And yes, this looks like the device that I have in my hand. And you can almost see the FCC ID printed there. If you really want to see where that's located, you can see the ID label and location. And this should be a diagram that shows us exactly where on the device the FCC ID is printed, HBW2392. And in this case, it's actually embossed, or it's part of the plastic mold, as opposed to being printed on after the fact. Which means that if this device were sold in another country, it probably would still have the FCC ID on it, because it's part of the plastic mold. And that's very common. Even if you live in another country, a lot of the radio equipment that you might find in your country may still have FCC IDs printed on it, even though it wasn't sold in the US, just because it's a product that could be sold in the US. And the next thing I like to look at is the internal photographs. The internal photographs are fun because it gives you a look under the hood. It lets you open up a device virtually and look at it in your web browser without having to actually open the device yourself in person. And that's especially handy if you're trying to get information about a piece of equipment that you don't even have in your possession. In this case, this is an unusually complicated circuit for a garage door opener remote. It isn't tremendously complicated. It isn't anywhere near as complicated as, say, a HackRF, but it is more complicated than a typical garage door opener remote. And the reason that it's more complicated is because it's a universal remote. It has the ability to emulate many different types of garage door opener remotes. So we have a couple of different chips, and this looks like a crystal and a coin cell battery and a series of dip switches. It looks like 12 switches, a couple of buttons, and then another button down here. And these two buttons are exposed to the outside, which you can see if you look at the external photos. This button is not exposed to the outside unless you open the battery compartment, which you can see right here. That third button is exposed, and these dip switches are exposed when you open up the battery compartment. And those other two red buttons are pressed with these two buttons here. So it's a 2-button universal garage door opener remote. And if you know a little bit about electronics, this can be a very useful tool for reverse engineering how the circuit works. Sometimes you can even read the identifiers that are printed on chips in the device, or read the crystal frequency and so forth. But in this case, it's pretty hard to make out some of those features. But you can easily see that it is more complicated than a typical garage door opener remote that only supports one type of radio transmission, which you will see if you open up one of your own devices, perhaps. Now I'd like to take a look at the user manual, and presumably this is the same information that is provided to the user and actually ships with the device. And this is often very handy, especially if you don't have the user manual yourself. This is a great way to be able to find the user manual for a device that if you've lost a manual or you're borrowing a device for somebody. And notice here that most of what this one-page manual tells us is about how to program it for the various different modes of operation under Chart A and Chart B. How many numbers of times you have to press the button during its setup in order to get it to go into that particular mode where it's emulating a certain device. And the kind of the big important document that I really get a lot of information from in a typical FCC equipment authorization filing is the test report. The test report contains the information usually from an independent test lab that measures the emissions from the device to determine if it is compliant with particular FCC regulations. Now, there may be other interesting documents here. I'm not going to go through every single one, but when you look up a particular device, you may find some other things like a block diagram or a theory of operation. There could be all kinds of different documents that were submitted with this filing and are made available to the public. In this case, I think we're going to get a lot of information from the FCC test report. And this says, yes, it's a universal 2-button remote control transmitter. And it's quite a long report. This is 83 pages. And one of the reasons it's so long is because they tested this device in all of its different modes. In the modes where it's emulating one type of remote or emulating another type of remote. And if we scroll down, we're going to see some information here, like the particular frequencies that it's intended to operate at and its operating mode. Now this is interesting because these correspond to those modes that were listed in the user manual, but in this case it tells us a little bit more. Like here, this first one is a 10-position dip switch, and then the second one is a key lock based secure code, and then here's a dip switch and a dip switch, and then here's a new rolling code. So some of these modes apparently use a rolling code. That is to say that the code that is transmitted changes every time you push the button. A new code is generated, as opposed to these other modes that say dip switch, which are presumably fixed codes. That is, every time you push the button, the same code is transmitted over and over and over again. And it'll be interesting to see which format this particular device is using when I push one of its buttons. If we scroll down a little bit further, we'll see some information about the results of the test. And for the most part, this information isn't going to be too interesting to most of you yet. However, as you learn more about radio communications, you may find more and more that you understand what more of this means and that it could be useful information. You can see a little diagram of where how they set up the test and photos from the test. And then we get to these actual test results that are the screenshots from test equipment. And you can see these bursts that are of transmission over time in this particular mode. And then here, maybe zoomed in or a different configuration. And I'll keep scrolling down, and you can see that the transmission looks a little bit different depending on what mode it's in. In this mode, there's a little bit of a gap here that's kind of interesting between a long series of pulses. Here's a mode where you can see pulses of different length, which is quite interesting. And so now that we know a little bit about this device, and we know that it can be set up in a variety of different operating modes, we also know that it can operate on a variety of frequencies between 300 megahertz and 390 megahertz. Now we know enough information that we can go poking around with HackRF and GNU Radio and see if we can locate the signal directly. And once we do, maybe we'll be able to compare the results, compare the signal that we receive to some of the diagrams in this document. Another FCC database that is very useful when looking for equipment authorizations is the grantee search. The grantee search allows us to look for grantees instead of looking for individual pieces of equipment or individual authorizations. So if we type in a grantee code, for example HBW, which was the grantee code we saw before, we see this grantee name and a little bit of information. Not a whole lot. But what's more interesting is if we go back and instead of filling in a grantee code, we fill in a name, then we should find that we can find the grantee code that way. This is extremely useful if you're trying to find information about a product and you don't have it. You don't know what the FCC ID is, but you do know who manufactures it. You can look up that manufacturer and find a grantee code. Unfortunately, this doesn't work every time. Sometimes you'll find that the name of the company that you do know is not listed in the database as a grantee, but there's some company that you don't know that is listed, and the equipment you're looking for is actually under that grantee. This happens sometimes if there's an OEM relationship or there's a partner company that is doing the equipment authorization on behalf of the company that you've heard of, or you've heard a brand name but you don't actually know the name of the company behind it. Those kinds of things happen a lot. And one trick that I've found is that if you're looking for something and you don't find it right away, look up the address of the company that you're looking for, and then see if you can find another company in the grantee database that has the same address or a similar address, a nearby address. For example, here we can see when I search for Chamberlain, we can see 3 different companies that all have the exact same address that have different grantee codes. So we might find different equipment listed under different grantee codes that all belong to the same group of companies that share the same address. And one really nice thing about the grantee search, if we go back to the grantee search page, is that you can download all grantees on file in one big XML file. Do this. Download this file. It's very handy to have a copy, and then you can search through it yourself locally to find information about grantees. And once you know a grantee, once you know a grantee code, then you can go back to the authorization search, the equipment authorization search, and just fill in that grantee code. Leave everything else blank. You don't need the entire FCC ID, and you can get a list of all the equipment authorizations for that particular grantee. This list happens to be pretty long. Here we have 217 records. Remember that the device we were looking for had several different authorizations. So this number, 217, really probably isn't 217 devices. It's just 217 authorizations spread out over some smaller number of devices. Now, the FCC website isn't the most user-friendly thing, and sometimes it changes. It's a little bit difficult to find what you're looking for sometimes. So I want to show you another website that is very useful. If you go to fcc.io, this is a little tool that was put together by Dominic Spill, and it is a quick and easy way to search for equipment authorization. You can look for any FCC ID or a grantee code. For example, if we type fcc.io/HBW, you don't even have to go into you don't even have to type it in here. You can just type it in the URL, and it automatically redirects you to the results of the search. And you can type in a complete code like fcc.io/HBW. I'll use one of these as right here up front, 0708, and it'll just take me to the authorizations or authorization for that particular FCC ID. I'm going to use GNU Radio Companion and a HackRF One to try to receive the radio signal from the garage door opener remote. I'll start with a source, an Osmocom source, to receive data from the HackRF One, and I'll visualize the signal with an WX GUI FFT sync from instrumentation WX. Connect these together, and I need to configure the sample rate. I'll set it to 2 million, or 2E6, which is the lowest sample rate that I recommend using with HackRF One. And then, of course, I like to turn off the RF amplifier. And I need to set the frequency to something between 300 and 390 megahertz. Why don't I use a slider for that? I'll call my variable freq. And now I need to create that variable. It will be a GUI widget WX GUI slider. I'll call it freq. Give it a default value of 300 million or 300 E6, 300 megahertz. And I'll set the minimum to 300 E6 and the maximum to 400 E6. And somewhere in that range we should find the signal from the garage door opener remote. Now I'll run my flow graph, call it lesson8.grc. And this lets me visualize the radio signal at 300 megahertz being received by HackRF. Now I'll click the button on the remote, and I'm not seeing much. So let's try sliding the frequency up while I click the remote. Oh, there's something. Right at 310, or just below 310. I'm holding down the button of the remote. And sometimes I like to use the peak hold feature. That's helpful to find signals that are fairly transient. Or the average feature. The average allows me to get an idea of the bandwidth of the modulation. And you can see the bandwidth is pretty narrow. It's just about as narrow as this spike in the middle here that's at 0 hertz. Of course, that is my DC offset, and we'll talk more about the DC offset in the future. But there's always a bit of a DC spike, or a 0 hertz spike that we see. And since I'm tuned to 310 megahertz, something just below that 0 is something that is just below 310 megahertz over the air. So it's around 30 or 40 kilohertz below 310 megahertz. Pretty close to 310 megahertz, and it's definitely there while I'm holding down the button. Definitely not there when I release the button. And you can see that happen more abruptly if I turn averaging off. Now, one way to be absolutely sure that this is the device, that the signal we're seeing is in fact the device we're looking for, is to turn on the transmitter and then move it closer to the HackRF. And if I do this, you should see that the spike gets higher. It's up around, oh, look at that, way up there. If I hold it right next to the antenna of the receiver, you can see, and we're actually getting some other frequency components because we're distorting a little bit, because we're way up about pretty close to 0 dB. But if I hold it at a more reasonable distance, like a meter away, then I'm at somewhere around -30, -40 dB, and we seem to get a nice clean signal for as long as I hold down the button. Now, the next thing I'd like to do is to visualize the signal using a scope sync. A scope sync is like an oscilloscope. I'm going to stop this flow graph, and I'll use under instrumentation a WX GUI scope sync. I'm just going to connect that to the same source. So now I have one source going to two syncs. And I might as well set my default frequency now to 310 E6 because we know that that is the frequency we should be expecting this signal on. If I run this, now I'll turn off auto range and just adjust my counts per division a little bit. I hold down this. Now you can see, I'll keep going with counts per division. There we go. Now you can see kind of complete periods of these bursts happening. Now sometimes there's very little going on. You can see this these two lines, blue and green, going right around 0. But then at other times we get these flickers of activity of these big sort of sinusoidal curves that are clearly have an amplitude much greater than 0. And if I increase my number of seconds per division, that allows me to kind of zoom out horizontally or zoom out along the time axis. And we can see that there are these bursts of transmissions that happen. I keep zooming out, and you can kind of see a pattern here. If I stop this, let me try stopping it. I'll just run and stop it until I get a whole set of bursts. And if you look closely, you can kind of see the difference between the burst and the stuff around 0. This is a short burst, and then a short, and then a long, and there's a little bit of 0 there, and then another long. So it's short, short, long, long, short, long, short, 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 long. And one of the things I notice about this is that this pattern, short, short, long, long, short, long, short, 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 long, is the same pattern that I have the dip switches set to in the garage door opener remote. They're set to 0, 0, 1, 1, 0, 1, 0, 0, 0, 1. And actually there are 2 more dip switches, but we seem to be only using the first 10 here. The first 10 dip switches correspond exactly to this pattern of short and long pulses. And another thing you might notice is that the beginning of each pulse seems to be at the same amount of time, from the beginning of one pulse to the beginning of the next, and then from the beginning of the second pulse to the beginning of the third, the beginning of the third pulse to the beginning of the fourth. And you'll often see this with digital transmission systems, that these symbols are evenly spaced over time. It isn't always true, but it's usually true. And sometimes you might see the end of a pulse lining up, or in this case we see the beginning of a pulse lining up. And if I release the button and press it again, and if I run this some more and stop it and try to get that whole set of pulses on screen at once, we see the same exact pattern. Short, short, long, long, short, long, short, 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 long. The same pattern of 10 bits over and over and over again in these groups of 10 pulses. This modulation is known as on-off keying. It's the simplest form of amplitude modulation. the amplitude is changing to extremes. The transmission is either on or off, and that's why it's called on-off keying. In many ways, it is similar to Morse code. You can imagine this type of transmission coming from a telegraph key. You could manually hit a telegraph key, short, short, long, short, and so forth. However, you couldn't do it. A human couldn't do it this fast. Notice that we're getting pulses, many pulses over over many milliseconds here. We're looking at maybe in the neighborhood of 1 pulse per millisecond, or maybe 2 milliseconds per pulse, somewhere around there. This is much faster than a human could key manually, but it's the same type of transmission. You might call it a CW transmission, which is what folks call Morse code, but in this case, since it's produced digitally by a digital electronic circuit, and it's produced much faster than a human could, I would definitely call this on-off keying. It doesn't look like the frequency changes over time. When we look at the average in the FFT plot, it's very consistent and narrow, very narrow band signal. And if we were to look in the scope sync and look at the, if we zoom back in again on the time axis, you can see that every time we see this sinusoid, it does look quite consistent, right? Every time it looks like it has the same period every time it shows up here. And so those are two indications tell us that this frequency, or that this signal, isn't changing frequency over time. It is changing its amplitude to extremes. It's being shut on and off. Now, if we look back at the test report, remember we found this signal just around 310 megahertz. If we look back at the test report, we should see that among these various plots, we should find something around 310 megahertz. This one was at 300. This one's at 310. This is configuration 18. And it looks like 1, 2, 3, 4, 5, 6, 7, 8. This is 8 pulses. We should be finding something with 10 pulses. If we keep going down, here's configuration 16 at 309.95 megahertz. That is very close to the frequency that we found. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pulses. 10 pulses, groups of 10 pulses. And you can see this is 10 milliseconds per division, so we could go back and line that up exactly. But I think what we have here is the configuration, configuration number 16. And it is, in the test report here, it looks like they have all the dip switches set to the same position, the on position, which gives a long pulse. In my device, I have the dip switches set to various positions, and so we get a pattern of short and long pulses. And if we look back at the user manual for this device, sure enough, under 16, configuration 16 is a 10-position code at 310 megahertz. So this user manual agrees with the test report, and they both agree with what we're finding under GNU Radio Companion. Now I'd like to take this just one step further and visualize these demodulated waveform. If you remember from lesson 7, we talked about an algorithm for demodulating an amplitude modulated signal. If you have a complex valued signal, which we have here, we should be able to take the magnitude of each sample and look at the magnitude over time instead of looking at the complex value over time, or the real and imaginary parts independently. So I'm going to go into type converters and select complex to mag. Could also use complex to mag squared, as I talked about in lesson 7. And I'll just plug this in here between the Osmocom source and the scope sync. But then, of course, I need to make my types agree. The complex to mag block takes complex input and produces a real valued or a floating point output. So I just need to go into my scope sync and change its data type to float from complex. Now let's run this flow graph again. And this time the scope plot looks a little bit different, but if I hold down the button on the remote, I should be able to adjust my settings here. I'm turning my counts per division up quite a bit, and then I'm going to turn up my seconds per division, and we should start to see a pattern emerging. I'm going to increase my counts per division again. Here we go. Now we're seeing the individual bursts looking like these square peaks. If I stop this, look at this. You can see short, short, long, long, short, long, short, 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 long. And it's a little bit clearer and easier to read now that we're looking at the magnitude of the sample values over time. So we don't, within one of these bursts, we're not seeing a sinusoid. We're seeing the magnitude of that sinusoid. And you can see it's fairly consistent. It's a little bit spiky, a little bit inconsistent, but you can clearly see the difference between when the signal is on and when the signal is off. And it wouldn't matter how much of a frequency offset we have here. We should still see the same sort of pattern emerge after the demodulation step. For homework for this lesson, I would like you to find your own garage door opener remote, or other simple digital radio transmitter, perhaps a remote keyless entry system for an automobile, and see what you can find out about it. Go to greatscottgadgets.com/SDR, and under Lesson 8, you'll find a series of questions that I hope you'll be able to answer about your own device. And I hope I'll see you next time for Lesson 9.
Hi, I'm Michael Ossman of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 9, Aliasing. In this lesson, we will explore sampling and the phenomenon of aliasing. We'll use our knowledge of complex numbers to understand, solve the mysteries that we encountered in previous lessons. First, let's review the homework from Lesson 8. In Lesson 8, I demonstrated how to get started reverse engineering the signals from something like a garage door opener remote. And I asked you, for the homework for Lesson 8, to investigate your own remote keyless entry device. Let's go through the process with a remote keyless entry system from an automobile that happens to behave a little bit differently than the garage door opener remote that I used in Lesson 8. Instead of starting with the FCC filing, this time I'm going to just try to receive a signal from the device. I have a pretty good guess that it will transmit between 300 and 400 megahertz. So let's just try firing up a HackRF with an FFT to look for the signal. Instead of using GNU Radio Companion, this time I'll use Osmocom FFT, which is a program that should be installed if you have GR Osmo SDR installed. And GR Osmo SDR is the interface for HackRF to GNU Radio. So it should be there if you've been using HackRF with GNU Radio and GNU Radio Companion. Now Osmocom FFT starts up and immediately displays an FFT. It's 8 megahertz wide, centered at 3.625 gigahertz in this case. Now if we want to see 20 megahertz wide, all we have to do is type in 20 million for the sample rate, and now we see a much wider bandwidth. And this will help us if we're looking around for a signal and don't know what signal, what frequency to start at. Well, I'm going to look between 300 and 400 megahertz, or really this shows me, if I tune to 300 megahertz, it shows me some below the frequency of interest. So I'll start at 310 megahertz, and now that gives me the range from 300 to 320, and I can go up in increments of 20 megahertz to find out to look for the signal that is being transmitted from my remote keyless entry device. So I'll just press the button on the device and hey, look, it's right there.
just below 314 megahertz. I didn't have to scroll around at all. Well, let's see. If I wanted to get a closer look at that, what could I do? I could tune to 314 megahertz, and now you can see that that is just really close to my center frequency there. I'm going to reduce my sample rate down, which will reduce the amount of visible bandwidth. Now I'm looking at 2 million samples per second, which gives me 2 megahertz of bandwidth from 313 to 315. And if I push the button on the remote keyless entry device, you can see, isn't that interesting? I see 2 different peaks. If I press peak hold, then you can clearly see those 2 peaks, not just one peak like we saw with the garage door opener remote, but 2 distinct peaks. And that suggests very strongly that this is 2-level or binary FSK, frequency shift keying. Probably this device is transmitting one frequency to represent a 0 and a different frequency to represent a 1. Anytime you see twin peaks from a transmission, that is a good indication that it's probably 2FSK. And in this case, we see 2 very distinct peaks, which is a little bit unusual for 2FSK, but it is a very strong indication that this is, in fact, 2FSK. Now, it may be helpful to know the exact center frequency, and if I hover my mouse between these peaks, it looks like it's about 313.85 or 313.84 might be about right. And if I just type that in here, 313.84, and select peak hold, I'll push the button on the remote while it's close to the antenna, and yes, that looks like it's pretty well centered around that spike in the middle. Now the spike in the middle, I'm not sure if we've talked about it much before, but you've probably noticed it. And if I scroll around to different frequencies, notice how that spike in the center is always there. We'll talk about that a little bit later today, but for now, we're going to just ignore that. And if I tune to 13.84, the important thing to note is that I'm able to get my signal of interest many dB higher by holding it close to my antenna. It's many dB higher than that spike in the middle, which means I can pretty much ignore that spike in the middle and not worry about it this time. Now, let's see what happens if we look at this signal using GNU Radio Companion. I'm going to close this Osmocom FFT window and start up GNU Radio Companion. Let's start with the flow graph that we used in Lesson 8, only this time we'll use what we've learned already and start with a default frequency of 313.84 E6. That's 313.84 megahertz. And I will save this as lesson 9a.grc and run the flow graph and see what we get. And when I push the button on the remote, you can see in the FFT plot on the bottom, I'm getting output similar to what I got from the Osmocom FFT utility. Now on the top, if I increase my counts per division, you can see the result of my amplitude demodulation. It's showing that there is a higher amplitude while there is a transmission. But during that transmission, the amplitude stays about the same because there isn't any information being carried in the amplitude. The information, as we've already observed from the FFT plot, is probably being carried in the frequency. So how are we going to demodulate it? How are we going to extract frequency information over time so we can scope that instead of scoping the amplitude? Well, if you recall from Lesson 7, we talked about an algorithm that allows us to do that for complex valued signals. And here we have a complex valued waveform that instead of amplitude demodulating, as we did with the complex to mag block, we should be able to frequency demodulate it. And the algorithm that we talked about in Lesson 7 for for extracting frequency information from a complex valued signal is in a block called quadrature demod, which you should know if you did the homework for lesson 7. It's under modulators, and we will pull quadrature demod out there, and notice it's similar to complex demag in that it takes complex valued input and produces this orange data type that's floating point valued output. The reason it produces floating point valued output is because every time there is an input sample that is complex valued, it measures the change in angle from one sample to the next, and it spits that angle out, or that difference of angle, out on its output. And an angle is a real valued number. It isn't a complex valued number. So all we have to do is remove this complex to mag block and insert the quadrature demod block in its place. Now, the quadrature demod block is unhappy because this gain setting is unsatisfied in some way. Oh, look at that. It's this very complex formula, and it refers to a variable that doesn't exist. Now, what I usually do is this. I observe that this gain parameter, all it does is just scale the output, and I don't really care about the scale of the output, so I set this to 1 and remove all of that complicated stuff. Now, let's see what we get this time. Now, we still have a scope plot, only this time, instead of representing the instantaneous amplitude over time, it's representing the instantaneous frequency. And if I press the button on the remote, you can see things are a little bit different. I'll turn off auto range and increase my counts per division, and maybe increase my seconds per division. It's a little bit messy, but you can see some things are moving a little bit. Oh, look at that. Do you see? As I've increased my seconds per division to a scale where I'm seeing milliseconds, you can see a little bit if I stop here during a transmission. Do you see how it kind of goes up and then down and then up and then down and up and then down? This, I think, is how the bits are being transmitted, but it looks really noisy. So one way that we can reduce that noise is by filtering. And we did this in the flow graph that we used to demodulate FM radio transmissions in the very first lesson. And we're going to talk about filters in much more detail in the future, but for now, let me show you a trick that we can use that is taking probably the simplest type of filter that I use all the time in GNU Radio, and that is a low-pass filter. And all I have to specify is a cutoff frequency and the transition width. Well, let's see, what cutoff frequency do we want? In other words, what frequencies are we interested in? If we look back here and I set peak hold and turn on my transmitter, we can take a look and see that these peaks are at about plus or minus 30 kilohertz. So I'm going to set my cutoff frequency a little bit higher than 30 kilohertz. Let's say 40 kilohertz or 40 E3. And then I'll set the transition width to something a little bit less than that, maybe 20 E3. And I'm going to insert this low pass filter between the Osmocom source and quadrature demod. And I'll also use its output for my FFT sync so that we can visualize what effect the filter has. Then I'll enable my filter by plugging it in or hitting the E key. And let's see what happens here. Now look at the FFT plot. Most of the noise at frequencies far away from 0 hertz have been knocked down very far. If I use auto scale, I can maybe see some of them. Nope, not anymore. It doesn't want to show me those. There we go. If I turn this way up so I see a lot of dB per division, 20 dB per division here, now I can see all that stuff way down at negative 160 dB. That's much lower than it was before. It's only the frequencies between positive 40 and negative 40 kilohertz that are being passed by this filter. Now, if I turn off auto range and increase my seconds per division and counts per division, if I look at on this scale where I'm looking at milliseconds again and press the button on the remote, hey, look at that. If I stop this, do you see how I had maybe the beginning of a packet here? There was zero frequency for a while, and then suddenly there was a low, a high, a low, a high. This looks very much like a digital transmission, and if I look over here, yes, it looks very consistent. Let's try this a little bit more. I'll run it some more and press the button some more, and I'll increase my seconds per division a little bit, and my counts per division, maybe increase that a little bit, and we should be able to see that. Look at that. Over time, we can clearly see bits being transmitted. Sometimes the frequency is low, sometimes it's high. To me, this looks like maybe 2 units of time high, 2 low, then 3 high, then 2 low, then 2 high, and then maybe that's 4 low. And we could go through and just decode this by eyeball just by looking at the output over time. And this is probably the end of a packet of information because we're low and then high, and then we're back to 0 frequency deviation. Whereas normally we're seeing a high frequency and a low frequency, each of those representing a data bit of a 0 or a 1. I'd like to draw a complex valued signal for you. The first sample is here, the second is here, the third is here, the fourth is here, the fifth is here, and so forth. And I'd like you to answer a question about this signal. It's a periodic signal. It keeps repeating these same samples over and over again. The question I'd like you to answer is, what is the frequency of this signal? Now, when I ask my students this question in person, I usually get the same couple of answers, and the most common answer I get is that it depends. The answer depends on the sample rate. And they'll say, what's the sample rate? And I might say, well, let's say the sample rate is 1 million samples per second. If the sample rate is 1 million samples per second, now can you tell me what frequency that signal is? Well, it's 1, 2, 3, 4, 5, 6, 7, 8 samples per period. It repeats itself every 8 samples. So that suggests that this should be the sample rate divided by 8, or 125 kilohertz. But what if you didn't know the sample rate? What if I never told you what the sample rate was? Could you tell me what this frequency is without knowing the sample rate? Well, you might say it's the sample rate, which is sometimes written f sub s. It's the sample rate over 8. That is a reasonable answer. Another answer that you might propose is that you could define the unit of frequency as being the angle that the sample goes for, or the angle that the signal progresses over from one sample to the next. And if you think of that in radians per sample, which is perhaps the most fundamental unit of frequency that we can think of in the digital domain, if you think of this as radians per sample, how far does this signal progress around the origin? How far does it progress around the unit circle in one sample period? Well, the amount that it progresses is tau over 8. So if you know the sample rate, it's very likely that you would express the frequency in hertz, like 125 kilohertz. But if you don't know the sample rate, the more universal or the more generic answer to the question of what is the frequency in the digital domain is to express it in radians per sample. And I like to express it as a ratio of tau. In this case, it goes 1/8 of a turn around a circle in one sample period. So the frequency is tau over 8. Now let's take a different signal. Let's say we start here, and then the next one's here, and the next one is here, and the fourth sample is here, and so forth. What is the frequency of this signal? Well, you might say it's the sample rate divided by 4, or I would just say it's tau over 4. That is the frequency of this signal. How about, let's see, how about this one? We'll go, first sample is here, and then the second sample is here, and the third sample is here, and the fourth sample is here, and the fifth is here, and so forth. Now, notice this time, we're going around this direction. We're going around clockwise instead of counterclockwise. So you can be thinking of this as being a negative angle instead of a positive angle. In other words, this is a negative frequency instead of a positive frequency. Hey, do you remember earlier one of the mysteries that we had? I think it was lesson 4. We talked about these mysteries, and one of the mysteries was, what in the world is a negative frequency? What does that mean? Well, and now we can finally see that if we're dealing with complex valued signals, a signal that progresses in the opposite direction around the unit circle can be thought of as a signal with a negative frequency. So what is the frequency of this signal? 1, 2, 3, 4, 5, 6 samples, 7, 8 samples around the unit circle, and then it repeats itself? Well, I would say that's negative tau over 8. That's the frequency. But hang on a minute. How do we know that this signal is actually going around in the negative direction or the clockwise direction? Isn't it possible? Let's back up a minute here and look at those first 2 samples. Isn't it possible that this is a sample of a signal that actually progressed around this way, 7/8 of a turn? And then if we were to go and look at the next sample, this one, well, couldn't that have been from here around 7/8 of a turn this way? Well, that's interesting. Instead of being negative tau over 8, couldn't this be positive 7/8 tau? Huh. It could be either one, couldn't it? And let's look at a different example. Let's look at an example where we have one sample here, and then the next sample here, and then the next sample here, and the next here, and the next here. It's going back and forth between 2 opposite points. So I would say that it's going a half turn. But is it going a half turn in this direction, or is it going a half turn in this direction? In other words, is the frequency here of this signal, is it tau over 2, or is it negative tau over 2? And I think you'll agree with me that there's no difference. It doesn't matter whether you go around the clockwise direction or the counterclockwise direction. You're going to end up with the same sequence of samples either way. In other words, there's no difference between the frequency tau over 2 and the frequency negative tau over 2. They're exactly the same. Let's take another example. Let's say that we have a signal that starts here and then is here and then is here and so forth. Well, we could say that it progressed a quarter of a tau, quarter of a turn, and then another quarter of a turn. Or we could say that it progressed negative 3/4 of a turn, And then from there it progressed negative 3/4 of a turn. So the frequency could be thought of as tau over 4, or it could be thought of as negative 3/4 tau. But guess what? It could have gone even further. What if this went, in fact, in the positive direction, 1 time around and 1/4? And then from here it went 1 time around and 1/4. Oh, guess what? This could actually be 5/4 tau. Hey, this could be any number of frequencies, couldn't it? It could be 5/4 tau. Really what it is tau over 4 plus n tau, where n is any integer number, positive or negative. That's pretty interesting. There's an infinite number of frequencies that could describe this one signal. And this is a fundamental characteristic of all digital signals. Anytime you have a digital signal that has periodic sampling, like this, then the frequencies are actually periodic, or the frequency domain is periodic. And let's take a look back at the exercises, the lesson 4 homework, to look at see how this looks again in GNU Radio Companion. Here's a flow graph similar to the one we used in the lesson 2 and lesson 4 homework. If we execute the flow graph, we see that our signal source was producing a cosine wave at a frequency of 1 kilohertz, and our FFT sync in fact shows it correctly at 1 kilohertz. Now in the exercise or the homework for lesson 4, I asked you to add a scope sync to this flow graph. So we'll go in and look at instrumentation WX scope sync and add this so we can scope the output or look at the time domain representation at the same time that we look at the FFT or the frequency domain representation. And this is what it looks like. We see a spike at 1 kilohertz, and here we see what appears to be a 1 kilohertz cosine wave. But there were a few mysteries that we left unsolved at the time. One of them was, why do we have a blue channel 1 cosine wave and then a green channel 2 cosine wave that appears to be a quarter of a period out of phase from the first one, from channel 1? Well, by now you might have an idea about this, and it has to do with the fact that all of these data types are blue. And you can see that these are all set, every single block in this flow graph is set to use the complex data type. So if we're pumping a complex number into a scope sync, then we should actually see a real part and an imaginary part. And what we see here in the scope plot is the real part in blue and the imaginary part in green, called channel 1 and channel 2. So it turns out that this signal source was lying to us. It was lying to us all along about the fact that the waveform it's producing is a cosine wave. In this case, it's not a cosine wave. It's actually a complex exponential. And if you look at the XY version of this scope plot, that means it's plotting channel 1 on one axis and channel 2 on the other axis. And you can see that it plots a circle because it's going around and around the unit circle. This is what it looks like if you connect the dots. If you don't connect the dots, you can see there are 1, 2, 3, 4, 5, 6, 7, 8, and if you count all the way around, there are 32 dots in one period. That's, remember, a ratio of 32,000 samples per second and a frequency of 1 kilohertz. That's 32 samples per period, and that is in fact what we see if we look at the XY plot, which is the complex plane instead of showing the time across the horizontal axis. So what we're seeing here is actually a complex exponential, and it was all along. And there is a way to get the signal source to give us a true cosine wave, and that is to do what I asked in the exercise in the lesson 4 homework. Let's try that now. I asked you to change all of these to a float data type instead of a complex data type. Now you can go in and select the properties and switch them all to float, or let me show you a trick. If you have a block highlighted, you can use the up and down arrows to change the data type. If you highlight all these blocks and hit the down arrow once, they'll all change to orange, which is the float data type. And now we can look at the difference here. First thing you'll notice is that the scope plot only shows us one channel. This looks like a true cosine wave, not a complex exponential. Now the other thing you may notice is this FFT sync. The FFT sync, it looks similar in that it shows us a spike at 1 kilohertz, but notice that 0 hertz is now on the left. It only extends from 0 hertz to 16 kilohertz. It isn't showing us negative frequencies. And this kind of makes sense because we originally expected that negative frequencies should be identical to positive frequencies. There should be no such thing as negative frequencies for a cosine wave, a true cosine wave, or if there is a negative frequency, it's no different than the positive frequency. So all we really care about is the positive frequencies, and that's what the FFT plot gives us. Now, is there a way to get this to show us negative frequencies even though we're giving it a cosine wave and not a complex exponential? There is, in fact. As long as the FFT sync is configured to use a float data type, it'll only show us the positive frequencies. But if we were to configure it to use the complex data type, it then shows us negative frequencies. However, we have a type mismatch. We can correct that by doing a type conversion. Under type converters, you can take float to complex. And the float to complex block allows you to take two input streams, one as real and one as imaginary. So I'm going to connect the throttle output to the real input on the float to complex block and connect the float to complex output to the FFT sync. And notice that it is now happy. It's okay with me not connecting its imaginary input. What it's going to do is take a floating point number on its real valued input and then add a 0 value imaginary component and produce that complex number on its output. And then it will do that repeatedly for every input sample. And it will constantly send a stream of complex numbers to its output that have their imaginary parts always set to 0. Let's take a look at what that looks like. And I'll just disable my scope sync for now so it doesn't get in the way. Now we see the FFT plot shows us two peaks. We have a peak at 1 kilohertz and we also have a peak at -1 kilohertz. I think that's pretty interesting. One way to interpret this is that we actually have two complex exponentials added together, one with a positive frequency and one with a negative frequency. If I turn this frequency down to 0, at 0 we see one peak at 0. If I turn it up, well, that's interesting. When it's at 0, the amplitude's a little bit higher, isn't it? Or the power is higher. And then if I turn it up, that power gets split between those two signals, one at a positive frequency and one at a negative frequency. If I keep going up and up and up, watch what happens. It looks like each signal kind of bounces off the edge and then comes back to 0. If I keep going up, I'll go faster, then they bounce off 0 and then go back across. And if I go again, they bounce off the edge and come back. Now, that is one way to interpret it, and that's the way most people interpret it if they're only looking at the positive frequencies and not the negative frequencies. But I like to interpret it a little bit differently. If I start at 0 and I start increasing my frequency, I go up and up and up and up. Imagine that both of these signals, the positive and the negative spike, are going to wrap around. It's the Atari effect again, but this time it's happening for both signals. one of them went off the right side of the screen and came on the left, and the other one went off the left side of the screen and came off the right. If we look at it with a real valued FFT plot, and I disable this float to complex, then, and we do the same thing, then it appears that you have one spike that is bouncing off one side and going back the other way. But the way I like to interpret it is that it's actually the Atari effect. It's wrapping around one side, and it is wrapping around from one side to the other, but the other side is a negative frequency. And then, in addition to that, we have a symmetric frequency domain. So if I look at it again with complex valued FFT, we have a symmetric frequency domain. And anytime you have a real valued signal, you always have symmetry in the frequency domain, because with a real valued signal, there's no difference between positive frequencies and negative frequencies. But with a complex valued signal, a signal can go around the complex plane in a clockwise direction or a counterclockwise direction. So there are negative frequencies that can be different than the positive frequencies. When we looked at both the positive and negative frequency components of a cosine wave, a real valued cosine wave in GNU Radio Companion, we saw something that looked similar to the sum of two complex exponentials that have one with a positive frequency and one with a negative frequency. So let's take a look at what happens if we take two complex exponentials that are equal in every way except that one has a positive frequency and the other one has a negative frequency. If we add them up, if we do a point-by-point addition, then let's see, we add these first two. That's 1 plus 1, which is 2. Then we add these next two. Now, one has a positive imaginary component and the other one has an equal but opposite imaginary component. So they cancel each other out when we add them together. And what we end up doing is we just double the real part, and we end up here on the real axis over here. Now we take the next two, and you'll notice again we're going to, if we add them together, we'll cancel out their imaginary components, because they're what's called complex conjugates. A complex conjugate pair is two complex numbers that have the same real part but opposite imaginary parts. So we add these two complex conjugates together and we get a number somewhere over here. And we add these two together, we get a number somewhere around here. We add these two together, now they have zero real part and they have opposite imaginary parts, so we end up right at the origin when we add them together. The next pair added together is somewhere around here, and you'll notice that we started out at 2 and then we kind of zoom past the origin and then slow down as we'll get to -2, and then we'll speed up and zoom past the origin as we get to +2. What we're tracing here, if we were to look at the real axis versus time, would be a cosine wave. In other words, cosine of theta is equal to e to the I theta plus e to the -I theta. Two complex exponentials with opposite frequency added together, but then we take this whole thing and divide it by 2, because when we add those two together we get out to ±2 instead of ±1. So all what we see here is that, in fact, mathematically speaking, a cosine wave is a sum of two complex exponentials. So we can see that, and we can derive that from Euler's formula algebraically, or we can see it just by looking at the frequency analysis of a cosine wave in GNU Radio Companion. When we have our flow graph configured for complex valued signals, and we select a low positive frequency, the signal source produces a series of samples like so, and the FFT sync shows us that we have a spike that is a little bit to the right of 0. But if we increase the frequency, then the spike in the frequency domain moves to the right. If we increase it all the way up to half the sample rate, then the first sample will be here, the second is here, the third is here, the fourth is here. It's going back and forth between 1 and -1. And the frequency domain representation that the FFT plot shows us is a spike, not here at 0 hertz, but way over here right at the edge. And if you look closely, when you have it configured for exactly half the sample rate, you should be able to see a little bit right over at this edge also, because we don't know whether the signal is going around this way or this way. It's the same either way, right? Exactly the same. And this frequency over here is Fs, so the sample rate over 2, and this over here is negative S over 2. And it's actually, you can think of it as being both frequencies at the same time. If we increase the frequency further, then we go a little bit more than half a turn over to here. And then the next one is a little bit more than half a turn over to here. But you can think of that as being a little bit less than half a turn in the negative direction. So what we see as we increase the frequency this way, we see it wrap around over to here, and our spike is right there. And this is the Atari effect that we saw several times before, where when we increase the frequency, we go to the right, it wraps around to the left. If we decrease the frequency and it goes to the left, it wraps around to the right. And we can keep wrapping around forever with increasingly higher frequencies or lower negative frequencies, and find many, many different frequencies, an infinite number of different frequencies that are all the same as one another. So for example, this frequency that is here and then here and then here and then here and so forth, we could think of that as tau over 8. Or we could think of it as going around this way, negative 7/8 tau. Or we could think of it as going around maybe in the negative direction once, and then twice, and then to there. Well, what's that? That's negative 15/8 tau. Or we could think of it as going around in the anti-clockwise direction once and then twice, or once and an eighth. So that would be 9/8 tau. We could keep going here and think of any number of integer numbers of rotations between samples that occur, and we can come up with all these different aliases. They're called aliases because they're different names for the same thing. It's one frequency that can go by the name of a different frequency, and we can come up with an infinite number of them, but they're all related to tau, or they're all related to the sample rate. So what I have called the Atari effect, or the wrapping around from one side of the frequency domain to the other, is in fact aliasing. The phenomenon of aliasing is when we consider one frequency by another frequency's name, or we consider the frequency component of a signal as being a different frequency than you might expect. And this is because this happens because the frequency domain is periodic. Anytime you have periodic sampling, then you have a periodic frequency domain. And so if we plot the frequency domain representation, we usually see 0 hertz in the middle, and then f of s over 2 on the right-hand edge, and minus f of s over 2 on the left-hand edge, and we always see wraparound from one side of the screen to the other, one side of the plot to the other. And we can wrap around as many times as we want. If we keep increasing the frequency, for example, we'll see a spike that moves this way and then wraps around to this side, and we keep increasing the frequency, and it wraps around again, and we can keep increasing the frequency infinitely. And no matter how high a frequency we go to, it will always be represented in some way in our little bandwidth here. And this bandwidth is, in fact, our sample rate. Notice that the bandwidth is always equal to the sample rate. And this is one way to state the sampling theorem. Now the sampling theorem, which you might have heard called the Nyquist-Shannon sampling theorem perhaps, although it was discovered independently by various people, you may have heard of it stated something like this. Maybe you've heard of it like the sample rate, f of s, must be greater than twice the frequency of interest. And remember that people who are stating the sampling theorem in this way or something similar to that are thinking about real valued signals. Real valued signals only have half of this bandwidth. They go from 0 hertz to f of s over 2. You don't see the negative side because the negative side is simply a mirror image of the positive side. And that's always the case with real valued signals. The negative frequencies are always a mirror image of the positive frequencies, so they're typically ignored. They're there, arguably, but they're redundant information. If we were to plot the left-hand side of this frequency domain plot, it would be identical or a mirror image of the right-hand side. So there's no extra information over there, and people think of it as being that let's say you have a 1 megasample per second frequency of sampling frequency. So f of s over 2 is 500 kilohertz. Well, let's say you have a signal of interest that is at, let's say 200 kilohertz. Well, that's going to show up just a little bit to the left of center here on your frequency domain plot. And if you increase the frequency to say 400 kilohertz, then that's going to show up over here. But if you increase the frequency of interest to 600 kilohertz. Let's say you have a signal at 600 kilohertz. Well, that's off the right-hand side of the plot. And so to think of this, to think of where it is located really, I like to think about there being a negative component over here. I know it's going to be a mirror image of the positive component, but if I go off the right-hand side of the screen, then what I'm doing is I'm going over here. And guess what? There's a mirror image of that over here. And so now, oh, guess what? My 600 kilohertz signal clobbers my 400 kilohertz signal. Let's say there's both being present and I'm trying to sample both of them. Well, in the digital domain, they interfere with each other instead of being distinct from one another. Suddenly, as soon as we digitize them, they are no longer distinguishable from one another. And this is a real problem. And most of the time, this is considered something to avoid, a problem to avoid. So if you have, now let's say that we have a real world, this is an analog frequency domain here that I'm going to plot. Real world analog frequency domain, it goes infinitely to the right, and it starts at 0 hertz. And let's say we have some signal here, and then we have some signal here, and we have some signal here, and we want to sample one of these things. Well, let's say we want to sample this one. Then the traditional thing to do is to find its highest frequency of interest and say, let's say we want to capture from here to there. We take this frequency and call that f of s over 2, and we're going to choose our sample rate that is twice that. So our sample rate is going to be f of s. And then we have to filter in the analog domain before we sample. We filter this out, and we filter this out. We filter out all this stuff to the right. In other words, we use a low-pass filter. The frequency response of the filter ideally would look something like this. We would pass these low frequencies, and then we would pass 0 amount of all frequencies higher than that. We call that a low-pass filter. Now, it's possible that instead of low-pass filtering, we could do a band-pass filter. And this is something like this. Let's say 0 hertz is there, and again, we have some signal here, and some signal here, and some signal up here. But let's say the signal we're interested in is, in fact, that one, and not this one over here. Well, there are a couple of different ways we could deal with this. One way would be to take this high frequency and call that f of s over 2 and have a much higher sampling rate than we did in the first case. But the other way would be to say that this down here is, or maybe there, is f of s over 2. Now that's interesting. And then this over here would be f of s. But if we were to band pass sample, if we were to have a filter in the analog domain, we're trying to we block this lower signal, we pass this signal in the middle, and we block all signals higher. That's a band pass filter. We get rid of this stuff, we get rid of that, and then when we sample, we have only this represented in our digital domain. We don't have any aliases clobbering each other once we've digitized this signal. This is a completely valid way to sample this signal, and it's called band-pass sampling. We could, in fact, select a band that's even higher than our sample rate. We could select this band up here or over here. It doesn't matter. We can select any of those because they'll all be aliased once they're digitized. They'll be aliased down to baseband or down to the frequencies in the vicinity of 0 hertz. So that's one reason that the traditional way of thinking of the sampling theorem is arguably wrong, because we can use bandpass sampling to have a sample rate that is actually lower than our signal of interest. But another way that I think the traditional representation of the sampling theorem is wrong is because it talks about a frequency, a sampling frequency being greater than twice the frequency of interest. And that is only the case, that doubling there is only the case if you're dealing with real valued signals. I think that a more elegant statement of the sampling theorem, a more elegant statement is to say that the bandwidth described by a digital signal is equal to the sample rate. Now, this is only true if you're dealing with complex valued signals. But isn't that an elegant statement? The bandwidth is equal to the sample rate. And you can see that every time we look at a frequency domain plot, we always see from negative f of s over 2 through 0 to positive f of s over 2. The bandwidth described by any digital signal is this complete range from negative fs over 2 to positive fs over 2, or that's the sampling rate. The bandwidth is equal to the sampling rate. Now, if you have a real valued signal, then of course this negative stuff is ignored normally because it's just a mirror image of the positive stuff. So there's no additional information over there. In other words, in that case, the bandwidth is half the sampling rate. But I like to think of the sampling theorem as this. The bandwidth is equal to the sample rate. In digital signal processing, we normally represent the frequency domain in a planar plot like this. But it's not truly a plane. The frequency domain is cylindrical. It's periodic. If you go off one edge, you come around the other side. And this is a fundamental characteristic of all digital signals. Anytime there's periodic sampling, you're going to end up with a periodic frequency domain. And I think of the frequency domain of real value signals as being the same exact thing, except that this is flattened. You still go off one side and come around the other side. However, there's bleed through from the positive and negative frequencies. They're mirror images of each other because they bleed through. So you still go around and around and around, but you also have this bleed through effect. Now, we talked a little bit about filtering in the analog domain, and in particular an anti-aliasing filter that we can use for sampling a particular band of interest. And we've also talked a little bit about digital filtering. We've used digital filters in some of the flow graphs that I've demonstrated so far in this series. And for the homework for this lesson, I would like you to experiment with digital filters that we'll talk about more in the next lesson. Go to greatscottgadgets.com/SDR, and under Lesson 9 you'll find the homework assignment. I hope you'll do the homework assignment, and I hope I'll see you next time for Lesson 10. Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 10, Filters. In this lesson we'll learn how digital filters work, and we'll learn a little bit about analog filters. In the Lesson 9 homework, I asked you to create a flow graph that looks like this. It has a noise source, throttled, and visualized with a WX GUI FFT sync. I set the sample rate to 1 million samples per second. Let's see what this looks like. This shows us the frequency domain representation of the noise. And what we're seeing here is that there's some of every frequency present in noise. If we hit the average button, we can see that it's pretty flat. And if we averaged over a longer period of time, we probably see that it's even more flat than that. Every frequency is present in random noise. Now, this is a useful way to visualize the frequency response of a filter. Normally, a filter is something that changes the frequency, how much of each frequency is present in a signal. And by starting with a signal that has every frequency present, we can compare the results of different filters against each other. Let's see what we get here if we install a filter, and I'll use a low-pass filter. I think that's the first one I asked you to try. We'll put it here between the throttle and the FFT sync. And it wants us to specify a cutoff frequency and a transition width. Now I like to specify these with sliders, so I go into instrumentation, no, not instrumentation, GUI widgets, WX GUI slider, and I'll create one that I call cutoff and give it a default value. I think I suggested samp_rate divided by 8, a minimum of samp_rate divided by 1,000. I just want it to be something close to 0, but not actually 0. And a maximum of samp_rate over 2. I'll give it a number of steps, 1,000. And then I can take that cutoff and put it in the cutoff frequency parameter of my low-pass filter. And now it's happier than it was before, but it still wants a transition width. So I'm going to copy and paste and create a new slider with the same characteristics called transition. And then I'll set my transition width here to transition. And let's see how things look. Now this looks a little bit different. And if I use my average button, I can see very clearly what the frequency response of this low-pass filter is. It's a low-pass filter, which means it passes frequencies that are low or that are closer to 0 hertz. But frequencies that are high, that are far away from 0 hertz, are blocked. They're reduced by many dB. And if you adjust the transition width, if I make the transition width narrower, you can see that it takes a little time for this averaging to catch up, but you can see that it has a flat response through this, what's called the pass band, up until the cutoff frequency at 125 kilohertz, also at negative 125 kilohertz. And then there's this shoulder, there's this transition where it goes from the pass band to the stop band. And the width of that shoulder is called the transition width. If I make the transition width a little wider, you can see that my pass band in the middle here doesn't change much at all, but this section between the pass band and the stop band, which is everything outside of the pass band, that transition has widened. If I adjust my cutoff, I can make my filter wider, or I can make it narrower. If I make it very narrow, I might want to also have a narrow transition width. And you can see that very easily in GNU Radio, I can create a low-pass filter and configure it to have whatever pass band I want and however much transition width I want. Now, one thing I asked you to do was to take a look at what happens when you adjust these sliders. Take a look at what happens to your CPU utilization. So I will bring up a window here and run htop, which is my favorite way to visualize CPU utilization. You can see that right now I'm using 30% or so of my CPU. I have 4 cores here, and they're all moderately utilized. And if I increase my transition width a bunch, not much changes. But if I decrease it a bunch, if I make it really quite narrow, I can go smaller and smaller. And as I get really close to 0, you might see things change a little bit. So you see how much more CPU I'm using now? As I go even closer to 0, look at that. I'm way down at 1 kilohertz transition width. That's only 1,000th of my sample rate. And I'm using about twice as much CPU power to do that. Now I have this beautiful looking filter. It has a very sharp transition. Frequencies that I want are passed through. Frequencies that I don't want are blocked, and there's a dramatic cutoff from one part of the edge to the other, past the edge. But it comes at an expense. If I soften my edges a little bit, then I use a lot less CPU time. And in this lesson, we'll explore why that is. Now, I'd like to do a little demonstration for you. I'll stop this flow graph and start a new one. And I'd like to show you what happens if I take a noise source. I'll start out in the same way as the previous flow graph. I'll take a noise source and use instrumentation WX GUI FFT sync. Of course, I'll need a throttle block because I'm doing a pure simulation here. And we always need to throttle our flow graphs if they don't have any connection to any outside hardware like a HackRF. Now, we've seen what happens if I just go like this. I just get a flat response. But I'd like to show you what happens if I do something like a moving average. One way we can do this, if I find my delay block, here we go, it's under miscellaneous, I'll delay the signal by 1 sample. And then I'm going to use an add block, that's under math operators, and add these 2 streams together. Now, to make it a little bit easier to follow, I'll do this all following the throttle block. So I'm taking 1 copy of the signal directly and a second copy of the signal that is delayed by 1 sample. And let's take a look at what that looks like. I'm just adding these 2 together. So in other words, the first and second samples get added together. The second and third samples get added together. The third and fourth samples get added together, and so forth. Now here's what my frequency response looks like. Notice that it's no longer flat all the way across. I actually have a higher frequency response toward the middle and a very poor frequency response out at the edge, at the extremes. In other words, I've created a low-pass filter. It might not look like a very good low-pass filter. The pass band is not very flat, or it's a little hard to tell where the passband starts and where the stop band ends. I'm not really sure, but there's definitely some stopping here and some passing here in the middle. It looks to me like it has a very wide passband, but it's not very flat. But it is a low-pass filter, and we implemented it very simply by just averaging two samples in a row together, or adding them together. I suppose if I divide it by 2, then it would be a true average, but I've just added them together. Now, let's take a look at what that looks like in a scope plot. If I go into Instrumentation WX and use a WX GUI scope sync, then I should be able to see the actual sample values. Now, I'm doing this with complex numbers, which makes it a little bit harder to compare two things against each other. So let's take a look at what this looks like if I go with real numbers. I just highlighted everything and then hit the down arrow to convert the data types to real numbers, which makes it to floats, which makes it a real valued signal. Now things will look a little bit different. Let's take a look back at just the FFT sync for a moment. Now we see just the right-hand side, or just the positive frequencies of my flow graph, of the signal, or the frequency domain representation of my signal. Now, if we look at the scope sync, one thing that would be cool to do would be to compare the output of our adder with the input, or the actual original signal. So what I'll do is I'll go into my scope sync, into properties, set the number of inputs to 2. Now I'm going to take the original signal and plug it into one input, and then the modified signal and plug it into the second input. And that gives me a way to directly compare one versus the other. Now I'll run my flow graph, and you can see that the blue line, which is channel 1, and the green line, which is channel 2, do look very similar to each other. And if I stop it for a moment, you can see something interesting. Do you notice how the blue signal just looks a little bit more spiky than the green signal? It has a little bit more high frequency content. Also notice that the green signal lags behind the blue signal just a little bit. You see how there's a peak in the blue and then the green lags behind it? There's this low peak here, and then the green signal lags behind it. Here's a high peak, the green lags behind it. We've added a little bit of delay, but we've also removed some high frequency content. So how can we do a little bit more of this? What can we do to make this into maybe an even better filter? Well, one thing we can do is we can take more delay. If I copy and paste my delay block, I could have a version of my signal that's delayed by 2 samples. And I can add that to my signal. And I'll go into my add block here and tell it to have 3 inputs instead of 2. Now I'm adding the first 3 samples together, and then the next 3 samples, and the next 3 samples. Well, each set of 3 overlaps each other. Let's take a look at how that looks. I'm still doing a simple moving average, but now I'm averaging across 3 samples at a time instead of 2. And we could even go further if we wanted to. Now let's take a look at how this looks in the scope plot. You can see there's still a delay. It's slightly more delay. You might be able to tell that. See the difference from this peak to the next. And the green signal now actually has a little bit less of the high frequency component than it had before in our previous configuration. Let's confirm that by looking at the FFT sync. I'll just look at the FFT for a moment. Look at that. We have, again, I would call this a low pass filter, but we have this pass band down here near 0 hertz, and then we get this really low drop here at, what is that, about 11 kilohertz, a little less than that. And then we go to this section, I would call this the stop band. Notice the stop band is only, the middle of the stop band here is only about 10 dB down from the middle of our pass band. But it's definitely lower. It's 10 dB lower than our pass band. So we have this very distinct stop here, kind of a funny shaped region between our pass band and our stop band. But it is definitely a low pass filter. Now, one thing you might want to do is increase the sample rate. If we were to do 1,000,000 samples per second, things go a little bit faster here. But otherwise, it looks exactly the same. Our dip here is at about 1/3 of our sample rate. That's interesting. Now, let's take a look at what happens if we do something a little bit different. Instead of a simple moving average, what if we were to do a weighted moving average? A weighted moving average, we would take, in order to do that, we would need a multiply block, or really I'm going to use a multiply const block, which multiplies a signal by some constant. So if I multiplied this signal by a constant, let's say I multiply it by 1, then that doesn't change it at all. I'll set the data type to float. And let me put a bunch of these into my flow graph here. I'm going to put one into the undelayed signal. And then I'm going to copy and paste that. And I'll move things around so this is a little bit less cluttered. But at my delayed signals, the one that's delayed by 1 will get multiplied by a constant. And the one that's delayed by 2 will get multiplied by a constant. Now I have a weighted moving average. If I were to adjust these 3 constants, I can adjust how much each signal is, each copy of the signal, each delayed version of the signal is weighted versus one another. Right now they're all weighted the same because they're all multiplied by 1. But what if we were to create some sliders? I will use a WX GUI slider and create one. I'm going to call this tap 0. And its default value will be 1, but I'll set its minimum to -1 and its maximum to 1. And then I will make a couple more of these. I'll make tap 1, and I'll make tap 2. And I'll go in here and set this first tap, as I call it, to tap 0. That's the constant that I'm multiplying by. This one is tap 1 because it's delayed by 1. And this one is tap 2. It's delayed by 2. Let's see what this looks like. Now it should look exactly the same as it did before because we have all the taps set to 1. So there's no weighting going on. If I average my FFT plot, you can see that my pass band is 10 dB higher than my stop band. But what happens if I adjust these sliders? Oh, look at that. I can actually change the location of the transition in the frequency domain. I can change the shape of that transition. Look at this. If I set things like so, it looks a little bit reminiscent of when I only had 2 taps here, except I have a longer sort of gradually sloping transition. You might think of it that way. You can change the frequency characteristics, the frequency response of this flow graph by adjusting these taps, or I might call them coefficients. I change the signal. Look at that. I can even create a high pass filter. Just by fiddling with these sliders randomly, I found that I can create a high pass filter instead of a low pass filter. And all we're doing is making a moving average that is weighted, and I'm changing the weighting. And those values, those coefficients of the weighting, I call taps. Now what we've created here is called a finite impulse response filter, or an FIR filter. And you can see that there are FIR filter blocks built into GNU Radio. If you look at in the filters section, one of my favorite blocks is the decimating FIR filter. And we'll talk about decimation at some point, but for now, notice the decimation is set to 1, which means it doesn't actually decimate at all. Now, if you create a filter like this, it asks you for taps. So what do you think we might put as taps there? The taps are in fact specified like so. You could type 1, 1, 1, and that would create a 3-tap filter where every coefficient or every tap is 1, which is identical to what we've created in this this flow graph here that has multiple delay blocks and multiple multiply const blocks and that add block. In fact, we can compare the results against each other directly. If I change the data type here to float, float to float with real taps, that's what I want. I can go in here and I'll use this scope sync again to compare two signals with each other. Turn off my FFT sync for a moment. Now you can see I have one filter which is specified through all these different blocks, and then a second filter that is specified just with the decimating FIR filter block. If I stop this flow graph, you'll see that there's a blue curve and a green curve, and they look identical to each other except that there is some variation in the delay from one to the other. They're not necessarily synchronized with each other, but you can see that when I feed the same input to these two different filters, then I actually get the same output, the same curve that comes out of it. Let's see what happens if I change the coefficients. Now, I've only set up the coefficients to be used, these taps, to be used in my multiply const block, but I could also set up the same coefficients to be used in my decimating FIR filter. All I have to do is specify parenthesis tap 0, comma tap 1, comma tap 2, close parentheses, and I should be able to adjust my sliders. Oh, something's not working right there. There we go. Adjust my sliders, and the characteristics of the filter may change, but one filter always produces the same output as the other filter with a slightly different delay. Here we go. Now this is easier to see, I think, if you look at the frequency response of the FFT, which we already did. But the key point I want to make here is that the decimating FIR filter does exactly what we have done in this section of the flow graph. It takes multiple copies of the signal, delayed by different amounts, scales each one by multiplying it, and then adds the result together. It's called a multiply accumulate operation. Multiply accumulate means we do some multiplications and then we add up the result of that multiplication. Now, clearly, we could keep going. We could add more taps if we wanted to. And if we did, consider how much more processing power would be required to do all those extra multiplies and adds. Every single time we add a tap, we add another multiply and another add per sample. Every single time there's a sample, there are multiplies and adds that are a multiple of the number of samples that we have and the number of taps. So the more taps we add, the more CPU power gets used. Now the low-pass filter block that we used in the previous homework is actually an FIR filter. But here's the difference. Instead of specifying taps, what we specify with the low-pass filter block is a cutoff frequency and a transition width. Now, I'm going to ask you in the homework for today's lesson to experiment with different taps and see if you can produce filters that have differing frequency responses. But you don't necessarily have to do that most of the time. When you're working with GNU Radio, you can use this low-pass filter block in GNU Radio Companion and just specify the frequency you want and the transition width you want, and it computes taps for you. In other words, it designs your filter for you. Instead of having to come up with what those coefficients are, you can have this block design your coefficients for you, or determine your coefficients, and that's called filter design. So we'll play a little bit with filter design, but the good news is you don't need to be an expert in filter design. You just need to know a little bit about how the filters work internally. And this is what we've done in this flow graph demonstrates that very clearly. The term finite impulse response means that an impulse, or any sample, any one sample that goes into your filter, has an effect on the output only for a finite period of time, a finite number of samples. And you can see here, there's one sample, a delay of 1, and then a delay of 2. So there are only 3 output samples that can be affected by any one input sample. Those 3 output samples happen, and then it's over. There's no additional effect, long-term effect of any input sample beyond those 3 output samples. So since it's only 3, that's a finite number. We call it a finite impulse response. And the way that finite impulse response filters are implemented is with this multiply accumulate operation. That's also called convolution. Convolution is the name of this operation of doing multiply accumulate across multiple delayed versions of a signal. And the one thing that you might notice is that the low-pass filter block, although it gives you the ability to specify the cutoff frequency and the transition width, it doesn't actually tell you what the taps are. And that's why I had you do that part of the exercise in the homework for Lesson 9 to take a look at your CPU utilization, because something you should learn there is that when your cutoff frequency, and especially when your transition width, is very low in comparison to your sample rate, your CPU utilization goes through the roof. The reason for that is because in order to achieve such a sharp transition, it has to compute a large number of taps. So the tighter your filter is, the more taps it uses, and that's why the CPU utilization goes up. No filter is perfect, and that's why you should always test your filters, whether you design the filter yourself or let GNU Radio design the filter for you. You should test the frequency response of a filter that you're going to use. FIR filters, or FIR filters, have a trade-off that we've observed between the sharpness of the frequency response and the amount of computation required to implement the filter. And other types of filters have similar trade-offs. Even analog filters have trade-offs. An analog RF filter circuit is it doesn't have any computation involved, but it does have a trade-off between the sharpness of the frequency response and things like the size and the cost of the circuitry. And we've talked about in Lesson 9 anti-aliasing filters. Anti-aliasing filters in a software-defined radio receiver allow the intended frequencies to pass into the digital domain and avoid aliases from other frequencies to go into the digital domain. And similar things happen during transmit. And I'd like to take a minute to show you the effect of the anti-aliasing baseband filter in HackRF One. I'm using Osmocom FFT just like I did in Lesson 9, and I have that car key again, the remote keyless entry device. So if I press the button on the car key, you can see the transmission show up. I'll turn on peak hold here, and I want to show you something about the shape of the analog baseband filter. That's the anti-aliasing filter in HackRF. Now, one thing to notice here is that my sample rate is set to 10 million samples per second, and the bandwidth setting is set to 7.25 megahertz. That is actually the configuration for the analog baseband filter, the anti-aliasing filter. And if you if I turn on averaging, for example, if I turn on averaging, you can kind of see how the noise floor tapers off at either edge. Over here above 7.25 megahertz above my center frequency, you can see that there's this downward sloping noise floor, and you can see the same thing on the negative side. But the noise floor isn't necessarily the best way to observe the analog baseband filter because the noise level is fairly low, and some of the noise comes through the antenna, but some of it originates within the HackRF itself in different stages. So the best way to observe the performance of the filter is actually by doing peak hold like this. Now I'll push the button on the remote, and now I'm going to advance my tuning frequency. I'll just go up to 315 megahertz instead of 314. And now notice the peak still stays where it was on the screen, even though I've actually shifted frequencies out from under it. So if I push the button again on the remote, now you can see it's shifted down by a megahertz. Now the frequency of the remote hasn't actually changed, it's just that the frequency here that I'm tuned to has changed. If I go another 1 megahertz, and then another, and then another, now we should be getting around the edge of the filter. Notice how this one was slightly less in amplitude than these. The power level is down, should be about 3 dB if we're right at the edge of the filter, because normally filter bandwidths are specified by their 3 dB point. Did I do 319 yet? There it is. Now look at that. I went another megahertz up, which causes this peak to shift down 1 megahertz, which goes off the bottom of off the side of the screen and onto this side. This is aliasing. We're seeing this peak show up here close to 324 megahertz, but we know that it really wasn't at 324 megahertz. It was actually just below 314 megahertz. But since our sample rate is set to 10 megahertz, we see it show up as an alias on the other side of the screen. However, look at the power level. It's a good 10 or 12 dB less than the peak was when it was actually within our filter bandwidth. But like I said, no filter is perfect. If we keep going higher, 320 megahertz, now we see this. Look how much just shifting 1 megahertz caused an additional 10 dB of power to go away. I'll go up again, and maybe you'll be able to see it, but it's getting really low down here. But this shows you that aliases happen. Aliases, even though we have anti-aliasing filter in our FDR receivers, an anti-aliasing filter isn't perfect. And depending on what this bandwidth setting is, how this is configured, you may get more or less of this aliasing from nearby frequencies that shows up leaking into the edge of your captured bandwidth. Let's try this exercise again, but let's do it with a different bandwidth setting. I'll turn off my peak hold, and I'm going to change my bandwidth setting. I'm going to reduce it down to, say, 2.75 megahertz. Now again, if I turn on averaging, you can actually see that. You see how this little hump in the middle of the noise floor shows up? You may or may not be able to see that depending on the particular circumstances of your capture, but what you'll definitely be able to see is the effect of that baseband filter when you have an actual strong signal. If I turn on peak hold and start my transmitter, and then I go up 1 megahertz and I start my transmitter, you can see that it was about the same power level there. If I go up another megahertz, now look at that. The power level drops off dramatically. I'll keep going up and up. Look at that. At 318 megahertz, I'm only off by 4 megahertz approximately from where my signal of interest was, and I'm not picking it up at all. I should be seeing a little peak right about here where my mouse cursor is, but I'm not really seeing anything at all because this filter is much tighter. It has a bandwidth of 2.75 megahertz instead of a bandwidth of 7.25 megahertz. And so we have the ability to change or configure the bandwidth within certain limits. The narrowest we can make it with HackRF One is 1.7 megahertz, and the widest we can make it is actually, well, it's much wider than our sample rate, in fact. And so we have the ability to control those aliases to different degrees. In general, in order to get the highest quality signal with the lowest amount of unintentional aliases, the thing to do is to make the bandwidth setting as low as possible. That's the analog baseband filter. Make it as low as you can get away with but still capture your whole signal of interest. And then increase your sample rate as much as you're able to. Now that incurs a cost in CPU utilization, but the wider you can make your capture bandwidth compared to your analog filter bandwidth, the cleaner a signal you're going to get, and the less aliasing will be introduced into your digitized signal. Now I'd like to take a look back at the homework from Lesson 9 and continue to look at the effect of different filters. We've seen how a low-pass filter looks. Now let's take a look at what high-pass and band-pass filters look like. So if I put a high-pass filter into my flow graph, I will just delete this low-pass filter for now, and I will configure my high-pass filter to have the same parameters, cutoff and transition, which are my sliders. If I take a look at the frequency response of this flow graph, you can see that my cutoff frequency is now the lower edge of my pass band. If I hit my average here, you can see this a little bit more distinctly. My cutoff frequency is around 125 kilohertz. There it is. And then below that, we see this transition width. If I make the transition width narrower, then you can see that it's a sharper edge to the filter. Now this might look a little bit funny at first, and for that matter, the low-pass filter might have looked a little bit funny at first if you weren't used to thinking about signals as complex valued signals and what that means for the frequency domain. A high-pass filter passes signals that are high in the positive direction and also high in the negative direction. So in some sense, this actually looks sort of like a band pass. If you imagine that this frequency domain is cylindrical, remember that it's periodic. So if you go off one edge of the plot, you come around the other edge. So in that cylinder, depending on how you look at it, this might look like a band pass filter or a band stop filter where we're stopping this band right here. If I change my cutoff frequency, if I make it very high, close to half my sample rate, now you can see I'm only passing these signals that are, or the portion of the signal that is at frequencies well above 400 kilohertz here, or below negative 400 kilohertz, which is getting close to half our sample rate. Now, if I take a look at a bandpass filter, I will, not a band reject filter, but a bandpass filter, and plug that in here. I'll just disable my high pass filter for now. I can set this to cutoff and transition, but now I have this separate parameter, cutoff. I'll call it high cut, but I don't have that slider yet. So I'll create a new slider, copy and paste. My new slider will be called high cut. And I'll give it a default value of, let's say, sample rate over 4 instead of sample rate over 8. Let's take a look at what that looks like. Here we go. Now, this is my bandpass filter. And you might have imagined things as being just one band, but you can see we actually have two bands, some positive frequencies and some negative frequencies. And this is a consequence of having complex valued signals. So this particular filter might not be very useful because most likely your signals of interest are going to be all together, not in two separate frequency bands. So if your signals are all together in one, it would be nice to be able to specify a single band that you want instead of what we have here, which is mirror image bands. But it's interesting to move these around. I can change my cutoff frequency. If I make my cutoff very low and my transition very low, you can see I can get pretty close to 0 hertz there. I can make my high cut higher. I can move these around, but no matter what I do, they're always these mirror images, these two mounds that are mirror images of each other. Now there is a way to specify a filter that has only one of these lobes instead of the other. And the way to do that is and in order to do that, we have to describe a frequency domain that is asymmetric. The negative frequencies are different than the positive frequencies. So how do we describe a signal? How do we make a signal capable of describing both positive and negative frequencies and have them be different from each other? Well, the way we do that is with complex numbers, of course. So what we can do is actually change our block. Instead of having real valued taps, we can change it to have complex valued taps. Now the default for all of these blocks, the band pass, high pass, and low pass filter blocks, the default, if you look in the FIR type, is to have complex input to complex output with real taps. If we go complex input to complex output with complex taps down here, then things look a little bit different. Check this out. This looks maybe more like what you would expect when you hear band pass band pass filter. You would expect to see one pass band. Now I can set my cutoff wherever I want, and I can set my high cut wherever I want, I can set my transition width, but notice I have things configured not to allow me to set these to negatives, but I can set them to negative now because I have complex valued taps. I can go in to my sliders and I could set my cutoff here. I could set the minimum, instead of being very close to 0, let's set the minimum to negative sample rate over 2. And let's set the high cut also to have a minimum of negative samp underscore rate over 2. Now let's take a look at what that looks like. Now I can set my cutoff frequency below 0 if I want to. And I can arbitrarily select any band that is within the bandwidth described in the digital domain by this digital signal. Anything we want, we can set it to. And we can choose a wide transition or a narrow transition and pick out whatever region of the frequency domain we're interested in. FIR filters are not the only types of filters we use in software-defined radio, but they're among the most popular. They can be implemented very efficiently in digital logic, for example in an FPGA, and they can be optimized quite well with vector instructions or SIMD instructions on a general-purpose CPU, and that is in fact how they're implemented by GNU Radio under the hood. Now, the thing that I like the most about FIR filters is how flexible they are. You can implement a filter with whatever frequency response you want simply by changing the coefficients. And I'd like you to explore those coefficients a little bit more in the homework for this lesson. Go to greatscottgadgets.com/SDR to view the homework assignment for Lesson 10. I hope I'll see you next time for Lesson 11. Hi, I'm Michael Ossman of Great Scott Gadgets, and this is Software Defined Radio with HackRF. Lesson 11, Replay. In this lesson, I will give a demonstration of how a captured radio signal can be replayed or retransmitted with software-defined radio. But before I start transmitting, I'd like to say a few words about being a good neighbor on the spectrum. Your country probably has laws governing the transmission of radio signals, and those laws are likely more restrictive than any rules about receiving radio signals. If you'd like to know more about the rules in your area, I recommend pursuing an amateur radio license. In the process of studying for your license, you'll learn a lot about rules that you're subject to, and when you gain your license, you'll gain privilege to transmit on certain frequencies. There's one thing that all of these rules have in common across all countries that I know of, and that is a common goal of sharing the radio spectrum among many different people. The radio spectrum is inherently a shared resource, and so it's important that we are able to use the spectrum without interfering with other users of the spectrum. That's the reason why we have most of these laws. So instead of talking about any particular laws, I'd like to talk about ways that you can be a better neighbor on the spectrum. If you're thinking about transmitting with software-defined radio, one of the things you should consider carefully is frequency of operation. If you're trying to emulate some device that you can legally operate, then emulate it as carefully as possible, and that includes operating on the exact frequency that it operates on. If you're not emulating any particular device, but are just doing some general purpose experimentation that could happen on a wide variety of frequencies, then try to pick a band that is an unlicensed band in your area. For example, ISM bands, or industrial, scientific, and medical bands. ISM bands such as the 2.4 gigahertz band are common in many countries throughout the world. And which particular bands are available in your area varies depending on country, but the 2.4 gigahertz band is one that exists in every country that I know of. The reason that you would use such a band is because it's unlicensed, in that you are allowed to use equipment that operates in that band without you having a license yourself. There may be rules, however, about the authorization of the equipment, even though there aren't rules about the authorization of the user of the equipment. So we call those unlicensed bands, and one of the characteristics that those bands tend to have in common is that users of the unlicensed bands are required to tolerate other users of those bands. And that's very different than licensed spectrum, in which a user is given a particular license to operate some radio system on a particular frequency and has the expectation that no one else is using that frequency. So try to use those unlicensed bands anytime you possibly can, or emulate the particular frequency of operation of a device that you can legally operate. Another consideration that's related to that is the bandwidth. You've seen how software-defined radio receivers collect a range, collect a radio signals over a range of frequencies. And when you transmit with software-defined radio, you also transmit over a range of frequencies. So be careful of your bandwidth, and be careful of neighboring frequencies and users of the spectrum, adjacent channels that may be within that bandwidth. And perhaps the most important thing you need to pay attention to is your transmit power, the output power of your transmitter. The number one thing you can do here is to simply use the least power that you need to accomplish what you're trying to accomplish. Don't start at high power and then scale it down. Start at low power and scale it up, and only scale it up to the point that you need. The power that really matters, of course, is how much power is received by other users of the spectrum. And so location can be important. You can, if you're able to do your experiment in a location that's far away from other users, then you're far less likely to interfere with them. And what you need to consider is the the receivers of other radio systems, much more so than the transmitters. It's a common misconception that you can jam a transmission or jam a transmitter, but you don't really jam transmitters typically. Transmitters normally don't care too much or aren't affected much about aren't affected by other radio signals that are in the area, but receivers can be greatly affected by radio signals that are in adjacent bands even that happen at the same time that can overpower their signal. For example, probably the easiest system to jam that you're familiar with is GPS. The GPS signal received by a receiver has come from such a great distance from a satellite that it is very, very weak, and it's extremely easy to jam a GPS receiver, deliberately or not. Of course, deliberate jamming is the worst thing you can do to be a good neighbor on the spectrum, and that's what we try to avoid when we're trying to be a good neighbor, is not just deliberate jamming, but any unintentional jamming that we might do. So keep in mind how much power you're transmitting that might be received by other radio receivers. One thing you can do is to operate inside a shielded enclosure. We call these Faraday cages. And a big Faraday cage that you can walk into is extremely expensive, but they can be built yourself, and smaller tabletop units can be built yourself. I know some people who use discarded microwave ovens, which are intended to shield 2.4 gigahertz radio signals. So that could be a good option for a do-it-yourself Faraday cage. Operating in a basement, for example, is one way to attenuate your signal before it reaches other users who are outside your basement or who are above ground. Anything you can do to limit the power of operation or the power received by other users is a good thing. And the easiest place to start is by simply having your software-defined radio transmitter configured to transmit at the lowest power that you need. One way to minimize the amount needed is to simply do things at very close range. If you need to transmit a signal from one device to another and you have them centimeters away from each other, then you can probably transmit at a much lower power than you could if that device were in the next room, for example. So have your transmitter and your receiver as close together as possible. Of course, the closest they could be is to actually be connected. And this is a great option in a lot of scenarios. That is to connect your transmitter to your receiver over a cable. A coaxial radio cable is actually a shielded enclosure. It has a shield around a piece of wire that goes through it. Now, if you do connect, say, a HackRF to another HackRF directly, you have to be careful that you don't overpower the receiver. The transmit power is higher than the maximum maximum safe receive power. So what you can do is get one of these little attenuators that can be connected in line with the cable and gives you the ability. This one is a 20 or 30 dB attenuator, and I would recommend using a minimum of 20 dB of attenuation. And it's kind of similar then to operating over the air inside a shielded enclosure. When you transmit over the air, going any distance over the air attenuates the signals quite a bit. I usually think as a rule of thumb that it's something like 30 dB of attenuation. That's the distance. That's the difference between having two antennas that are touching versus two antennas that are almost touching. Just going over a little bit of air gives you maybe 30 dB of attenuation. So if you can put 30 dB of attenuation onto your cable and connect the two devices together, then you emulate what would happen over the air. And that cable is shielded and prevents you from radiating that signal really at all to any measurable extent that anyone would care about. So Another thing you can keep in mind, in addition to using an attenuator on a cable, is that you could use a dummy load. These are little connectors. They look just like the connector that's on the end of a cable, except they have no cable attached. And you screw that on to your transmitter, and it provides a load, meaning that the transmitting device operates as if it had an antenna. It is safe to operate, although sometimes it might be unsafe to operate transmitters without an antenna attached. You can put a dummy load on, and it makes that device safe to transmit, but most of the radio energy gets absorbed in that dummy load instead of being radiated out over an antenna. And that's a good option that you can use if you need to do something over the air, but want to do it at very close range and at as low power as possible. Put a dummy load on your HackRF or other transmitter, and at very close range, you should still be able to pick up just enough of a radio signal to accomplish some experiment. And perhaps the most important thing you can do is to be a good neighbor on the spectrum is to verify that you're transmitting what you think you're transmitting. If you use some test equipment like a spectrum analyzer, or you could even use another software-defined radio platform, you'll be able to measure your output, measure what you're transmitting, ensure that you're on the frequency you think you are. You can check and see that your signal looks like you think it should, and ensure that you're operating over the correct period of time and over the correct frequency and correct bandwidth and correct power levels and so forth. It's something you have to be very careful of with software-defined radio platforms. The general purpose software-defined radio platforms, such as HackRF, may produce output on frequencies that you aren't expecting. Of course, most of the energy should be at the frequency that you've configured it to, but there may be weaker signals, images, or spurs at other frequencies that you weren't expecting. And so those should be weaker, but you can measure those with another software-defined radio platform or with a spectrum analyzer. I mentioned time briefly, and something you can do that's very easy to minimize your potential of interfering with other people is to minimize the amount of time that you transmit. If you only need to transmit for a second, don't transmit for an hour. It's as simple as that. The less time you spend transmitting, the lower the probability is that you'll interfere with any other users. And another thing you might consider if you're thinking of transmitting is amplification. You might be thinking about attaching an external amplifier to software-defined radio platform. Don't do it. If you can possibly avoid it, don't amplify. Don't connect these things to external amplifiers. And if you are tempted to do so, you need to be very careful about the laws. You need to be very careful about everything I've talked about, especially verification and bandwidth. You need to consider those images and spurs that might happen on other frequencies, and so you'll almost certainly need to use a band pass filter, an analog band pass filter that you can put in line between your software-defined radio platform and your amplifier to make sure that you're not amplifying signals at unintended frequencies. But if you can possibly avoid using amplification, do so. One thing you can do to avoid amplification, of course, is to move closer to your target. If your transmitter and your receiver are closer together, you'll have much less need to amplify. Another thing you can do is to use the best antenna you can for the job. If you use a directional antenna and you use a high gain directional antenna, you can likely transmit a signal that will be at significantly higher power at your target receiver without interfering so much with any other receivers that might be in the area. So that's a way that you could avoid having to amplify, is simply by moving closer and using a better antenna. So try those things first. Don't amplify unless it's a last resort. And if you need that external amplification, be very, very careful about all these things, and in particular pay attention to the laws in your area. Now, I'd like to go ahead and give you a demonstration of a capture and replay. And the device that I'm going to use is, the target device, is this radio controlled car. So I'm going to give it a signal from its original transmitter, and we will capture that signal and then see if we can replay it and make the car respond. Before we can replay a signal, we have to capture it. So I'll start by making a flow graph to receive a signal from the remote control. I'll use a source, an Osmocom source, and I will, to start with, just visualize the signal and see how it goes. And I'd like to use an FFT sync, but this time I think instead of using a WX GUI FFT sync, I'm going to use the QT GUI frequency sync. Now the frequency sync gives you a frequency domain plot, so it's very similar to the WX GUI FFT sync, except it's using the QT GUI widgets instead of using the WX GUI widgets. It's just a different library, a different set of tools that you can use. However, you have to be very careful when you're dealing with these things. And the reason I'm selecting QT right now is because this default over here in the generate options has changed in GNU Radio in recent months. And I'm using a newer version now, and I've noticed that it is the default. So I thought I should use it in my videos, although I do still like the WX GUI elements for some things. For this particular video, and probably most of mine going forward, QT will be fine. So if I connect these together, you should see that my flow graph is happy. But let me show you what happens here if I were to take one of these WX GUI elements and connect it into my flow graph. Notice that it is unhappy. It has a red title here. Even if I disable my other QT GUI element, I have a WX GUI element, and nothing is going to happen. It doesn't give me the opportunity to generate a Python program or execute it. And the reason is because the WX GUI element is in my flow graph, even though my options say to generate a QT GUI. You can only have one, not both toolkits. So if I go into my options properties, I can change this, the generate options pull down. I can change it between QT GUI and WX GUI. If I change it to WX, now my flow graph is happy. So you have to have your entire flow graph be either QT or WX. Whichever one you want to use is fine for now, but going forward, the QT GUI elements will probably be better supported and have more active development in the future. But it's a fairly recent change just this year to change the default in GNU Radio Companion from WX to QT. Now, I said I'd like to use QT this time, so I'm going to re-enable this QT GUI sync and get rid of my WX FFT sync, but that means, of course, I have to go back and change my options. I'll go in here in the options block and set the generate options to QT GUI, and now everything should work just fine. So let's run this and see what happens. Oh, wait a minute. I have some things I need to set, don't I, in this Osmocom source. First of all, I need to set a sample rate. I will use a sample rate of 2e6, 2 million samples per second, which is the lowest sample rate I ever recommend anyone use with HackRF One. And then I'll go into my Osmocom source, and I need to set a frequency. I'll set the frequency to 27 megahertz, and the reason I'm choosing 27 megahertz is because the toy has a sticker on it that says 27 megahertz. And of course, I like to set my RF gain to 0, and why don't we start with 16 for my baseband gain and intermediate frequency gain. It's a good starting point. Now let's see what happens. I'll execute this flow graph, I'll give it a name, And here we have an FFT running in real time. One thing you'll notice that's different between the WX GUI FFT sync and the QT GUI frequency sync is that the QT GUI does not have some of the controls that you're used to on the right-hand side. But if you use your third mouse button or your middle mouse button, you can bring up a menu that has a whole bunch of different options, including things like max hold that we've used with the WX GUI FFT sync. So let me try max hold, and I'll pick up my remote control for the toy and try to move the car a little bit and see what happens. Hey, look at that. I'm definitely getting a signal, and I can move it forward or backwards or left or right, and I always see that peak a little bit to the right of 27 megahertz. It looks like it's about 150 kilohertz above 27 megahertz there. So we've definitely found the signal, we're picking it up, and now I'd like to save this waveform so that I can replay it later. How are we going to do that? Let me close this flow graph and add something to my flow graph here. I don't need to add any more instrumentation. What I need to add is saving the data to a file. So I'm going to use a file sync. It's under File Operators. And the regular file sync, you'll notice, has a default data type of complex. So all I have to do is plug that into my source. And I do want to give it a file name. So I'll go into the properties and call the file, let's say /temp/car. And sometimes you might want to add some information to your file name. For example, the sample rate and the frequency of capture, maybe other settings. But for now, I'll just call it /temp/car. And at this point, I could even remove or disable the frequency sync, but I like to be able to visualize things while the flow graph is running. So I'll leave that enabled. So I'll be visualizing the signal with an FFT and at the same time saving the waveform to disk. Now this is the raw digital waveform. It's the information coming from the HackRF being saved directly to a file. I'm not demodulating it, I'm not filtering it, I'm not doing any kind of processing whatsoever. I'm just taking the data from the HackRF and sending it to a file. Let's see what happens this time. It should look exactly the same, but we should end up with a file at the end. So here's my FFT, and then I make the car go forward a couple times, and I waggle its wheels side to side a little bit with the steering, and then close my flow graph. And now I should have a file called /temp/car. So let's take a look at that. I'll go into my /temp directory and look at this file. Here it is. It is how many bytes long? 161 million bytes long. It's a pretty big file. And this is something that you'll find happens when you use this technique. Realize that I was capturing it only 2 million samples per second, which is the minimum sample rate that I recommend with HackRF. And just capturing for a short period of time, I got a file that was 160 megabytes. Really a lot of data in a short period of time. Why is that? Well, let's take a look at this file. I'll just use XXD to do a hex dump for a moment. And you can see, oh, do you see how much redundant information is in this file? See how there's a 0 byte and then a 0 byte and then these 2 bytes and then a 0 byte and a 0 byte and these 2 bytes. There's a lot of zeros in here. And the reason you see this pattern that goes 4 bytes long is because what we are saving is the complex data type, the blue data type here, which is complex valued. And that is a pair of floats for every sample. A floating point number is 32 bits long or 4 bytes long. So what we have here is one floating point number for I, and then another floating point number for Q, and then the next floating point number for I, and floating point number for Q. And there will be a limited number of values used here, even though it's 32 bits well, really 64 bits for a single quadrature sample, there will be a limited number of values that we see because these have been converted from 8-bit signed integers that came over the USB cable. They've been converted from 8-bit integers into 32-bit floats. So this file it grows quite quickly because there are 2 million samples per second, and there are 2 values in every sample, and there are 4 bytes in every one of those floating point values. If we use a different tool, like I like the OD command, which is, I believe stands for octal dump, but I'm going to use it with the floating point option. If I look at the file this way, I can actually dump out the floating point values. And if I were to use, I think it's W4, which is, W8, which is going to be interpreting 8 bytes at a time, a width of 8 bytes on every line. Here I get I and Q, and then that line is repeated. And then I get an I value and a Q value, and an I and a Q, and an I and a Q. So I get 1 sample per line. And I could turn off these stars for repetition if I wanted to. But this gives me an idea of the values that are in this waveform. And we'll probably see different values if we were to look further down the waveform to where there was actually a signal being picked up. But I'm just checking what this file looks like just for fun and to show you what's in there. I don't really want to analyze it using this method because it would take quite a while. It's 160 million bytes to analyze. But this demonstrates, it shows that we have this file called car, and is a capture of my remote control while I was trying to drive the car a little bit. Now let's try to do something with that file in GNU Radio Companion. I'll start a new flow graph, and this time instead of using a file sync, I'll use a file source. And I'll point that file source to the file /temp/car. Of course, the first thing I like to do is visualize things, or instrument my flow graph. I'll again use a Qt GUI frequency sync, and I could plug that straight into my frequency source and run this flow graph. However, I probably want to slow it down with a throttle block so that I don't crush my CPU. Under miscellaneous, grab a throttle, and now I have a flow graph that should make sense, but for the rulers to be correct on the frequency and for it to perform in the same speed as real time, I should go in and set my sample rate to be the same sample rate that I used for the capture, which was 2 million samples per second. We'll give this flow graph a name. And here we have a GUI FFT sync, and there's our signal, 150 kilohertz above center. If I use my third mouse button and set max hold, then we can see that it's consistently at that same frequency. Now, one thing you might notice here is that this is going on for a period of time that is actually longer than my original capture. And the reason for that is that the default setting for a file source is, if we look here, repeat yes. So this flow graph will run forever, repeating that same input. We could change that to no, and if we do that, then the flow graph will only run until it runs out of input in that file. But since I've set it to repeat, which is the default for the file source, then I get to see the same thing over and over again. And sometimes that's what you want, and sometimes it's not. But it's good to know that that's the default. Let's take a look at what we can do with this now. What do you think we should do if we want to replay this file? Well, I think what we could do is simply deliver this from the file source, deliver this waveform to an Osmocom sync. And I don't think we've used an Osmocom sync before, but it shouldn't be much of a surprise that such a thing exists. If you compare it to the Osmocom source, you'll see that they're very similar. They have some of the same characteristics, except one of them is used to receive a signal from a software-defined radio peripheral and deliver it to your flow graph as an output. And the other one is designed to take input from your flow graph and deliver it to the HackRF or other software-defined radio peripheral. So I'm going to delete my source here. All I need is the sync. Or let's just delete it, not just disable it. And I could plug in this sync into my throttle block, but then I would have a 2-clock problem because my HackRF is inherently clock limited already based on the speed that I tell it to go in terms of samples per second. And what I should do is, in fact, connect this directly to the source. The source directly to the sync. It doesn't need to be throttled, and it shouldn't be throttled because it's inherently rate limited. But I should take care with the other settings. Let me take a look and see here. This should be 27 megahertz because that's the same frequency that I use to capture. Now remember that the signal of interest is actually at 27.15 approximately megahertz. But it's a little bit above, it's 150 kilohertz above that center frequency of 27 megahertz in our capture file. If I want to replay it and have it remain 150 kilohertz above 27 megahertz, then I need to have my center frequency exactly the same for my replay as it was in my original capture. Of course, I like to set my RF gain to 0, and these values are actually a little bit different in when we're in a transmit mode. The IF gain is something that affects the transmitter, but the baseband gain actually makes no difference whatsoever because there is no baseband amplifier in the transmit path of HackRF. There is a baseband amplifier on the receive path of HackRF One, but not in the transmit path. So it doesn't really matter what we type here. It does matter what we type here and here. I'll just leave it with the default of 20, and which is roughly in the midpoint of the gain range, and I'll leave the RF gain off for now. Now, will this work? One thing I notice is that I do have 2 clocks in this flow graph, and this might work actually, but I could disable my throttle block and connect this directly to my frequency sync, and this should work fine because the frequency sync isn't going to go any faster than the Osmocom sync. They're both going to be pulling from the same file source, so the data will flow at the same rate to both of them. So this works like this with only 1 clock in my flow graph, and that's the clock in the HackRF that is here through the Osmocom sync. So at this point, I should be able to execute this flow graph and replay this signal, transmit it over the air to my remote controlled car, and see if it actually moves the car. I'm going to hold the car up and run the flow graph and see if I can get the wheels to move. So I start my flow graph, and it's starting up, and here comes the signal. It's transmitting, but the wheels aren't moving. And I suspect this is because I'm simply not transmitting at high enough power. So let me try increasing the power a little bit. Actually, let's try increasing the power quite a bit. If I go into my Osmocom sync and look at the properties, the maximum value that I can use for the IF gain is 47 decibels. That's 27 decibels higher than I had it set before. Let's just try that and see what happens. The signal's transmitting, and yet still the car's wheels aren't moving. Let's investigate what's going on a little bit more closely. One of the benefits of having a saved waveform like this is that we have a consistent test vector. I'm not recapturing the original transmitter every time I run a flow graph and possibly introducing different problems depending on how I'm holding things, or different changes in my environment, like interference. Everything should be the same every time I read data out of this waveform. So let's take a look at what is in this waveform a little bit more in more detail. One of the tools I like to use when I'm working with a file like this is a new piece of software called Inspectrum. And if I type Inspectrum -R 2E6, it knows how to parse sample rates like that. I give it a sample rate, and I give it my file name, and it brings up what is called a spectrogram. Let me increase the size of this window a little bit so you can see more of what's going on. This spectrogram is a two-dimensional picture of the information that is saved in that file. What we have is time on the vertical axis and frequency on the horizontal axis. Let me scroll down a little bit until we see something going on. Here we go. You can see that bright line down the middle. That corresponds to the spike that we get at 0 Hertz in the center of our FFT sync in GNU Radio Companion. And then we see things happening a little bit above center, just like we did in the FFT sync in GNU Radio Companion. And I can change things like the FFT size, which affects the width of the analysis. And I can change the zoom, which affects the height. Look at that. I can also change the color scheme depending on basically setting thresholds of which colors are applied to which power levels. And if I adjust things like so, you can see that it really pops out at me what kind of waveform this is. The frequency is very consistent because everything falls in this vertical line. But the power level goes on and off very dramatically. This is, if I scroll around to the beginning, you can see this is the beginning of on-off keying. Now it's pretty cool that we can see that just by looking at the waveform with this tool. But we don't actually need to know what type of modulation it is, theoretically, in order to do this replay exercise. We don't have to decode this information. We don't have to understand its modulation at all. We just have to have a capture that fully contains the signal that we're interested in. And we seem to have that. If I scroll up, you can see there's a bunch of stuff, a bunch of time here where nothing happens. And then I have my signal. And then there's another burst and another burst, and these probably correspond to different times that I moved the control sticks on the remote control. And then at the end, there's some empty time after I have transmitted anything. So I have some emptiness at the beginning, some emptiness at the end, and a very clear on-off keying signal right down a consistent frequency just above my center frequency. Now, this is useful perhaps, but it isn't really showing me what might be wrong with my signal. And I suspect what might be wrong is actually the power level. Do you notice, if I turn up my power max here, do you see how it turns red almost the same point at which this spike in the middle turns red? That indicates that my power level, the power level of this received signal, is only approximately the power level of this defect here. And that is a little bit troubling. Let me take a closer look in GNU Radio Companion. If I perhaps use something other than just a frequency sync, let's try and instrument our flow graph with a time sync, which is a time domain plot. So this is very similar to a scope sync in the WX GUI options. There's a WX GUI scope sync that gives us a time domain view, like an oscilloscope. But I'm going to use the Qt GUI time sync, which gives us a time domain view using the Qt GUI options. And I'm going to run it through my throttle block and turn on my throttle block and turn off my Osmocom sync for now. And I'm repeating this file and running it through these syncs to see what I get. Okay, so now I have my FFT on the bottom and my scope plot above. Okay, do you see how that looks now in the time domain? In between bursts of activity, I get this very low valued signal, very close to 0. And then during bursts of activity, you see something that looks sinusoidal. Now, if I were to zoom in a little bit, and one of the ways you can do that using this QT plot is by dragging a rectangular area within here. If I want to just zoom in, I can just choose an area to zoom in to and see what I get. There we go. Now I'm going to middle click and select stop. And that will pause the flow. It doesn't pause the flow graph, it just pauses this view. And inspect a little bit this background noise here that happens between bursts of activity. Do you see how everything's between 0 and negative 0.1? It's offset from 0 a little bit, which is no big deal, but that's an explanation and we'll talk about this later a little bit in more detail perhaps, but that's an explanation for this 0 hertz spike in the middle. There's some portion of the signal all the time that is a little bit off from 0. And that's perfectly normal in a receiver like HackRF to produce that type of a small defect. If I restart here and then try to stop it, oh, I missed. I'm not doing a very good job here. If I try to stop it when there is actually a signal present, you can see that the signal itself is also fairly weak. It isn't a whole lot bigger than a greater amplitude than the background noise between bursts of activity. The background noise was kind of between 0 and negative 0.1. And this activity, the actual burst of a transmission, is only ranging between, about 0.1 and negative 0.15 in amplitude. And one of the things I like to do with the time sync is use a stem plot. And this is similar to using the dot large option in the WX GUI scope sync. It gives me a dot, a bold dot for every sample, and then it has a vertical stem that extends to 0. And if I zoom in on this a little bit more, you can see the pattern of activity here. Notice that these are only extending about 0.1. The amplitude is fairly small if you think of amplitude being, let's say, maximum amplitude should be between negative 1 and positive 1. That's the scale that we expect, because when the Osmocom source receives information from the HackRF, it takes these 8-bit values and then scales them and assigns them floating point values that are between negative 1 and 1. In other words, we're using a very small portion of our dynamic range. How much vertical scale we have available to us is from negative 1 to 1. But how much are we using? Only about 1/10 of that. And if I zoom in, you can actually start to see a little bit that these have sort of distinct values. There are only so many different values that are getting used. And this is even more apparent probably if we look at the background noise between packets. Do you see how these blue dots are all at the same value? Well, except for one here. And these red dots are mostly at the same value, a couple that are a little bit different. There are just a few very distinct values that are being that have samples assigned to them. So you can actually see, and if we were to scale these up by 256, you would see that these are integers. So for example, this might be 0, and this might be a negative 1, and then this dot would be at negative 2, and so forth, something like that. What we're seeing is that very little of our dynamic range is being used. And we could actually amplify our signal in the digital domain. Let's think about how we would do that. How would you make a signal stronger in the digital domain before we even take this waveform and give it to the HackRF. Can we scale these values up? Sure we can. We can scale samples by multiplying them. So I'm going to close this flow graph and institute a new block in my flow graph. I'm going to use a math operator, multiply const. And if I put a multiply const into my flow graph, let's say I put it just before the throttle here. If I were to set the constant to 1, then that should have no effect. I'd be multiplying every sample by 1. But what if I multiply everything by, say, 6? Let's see what happens. Things look pretty much the same, except notice that the FFT sync, everything has shifted up a bit, and in our scope plot, we can see that the sample values are in fact extending from about 0.5 to -1. If we were to remove the DC offset or just shift it up a little bit, we could even gain a little bit more dynamic range, but not a whole lot. Now we're using most of the full scale that is available to us. And I want you to realize what happens here. When we were looking at the sample values using the OD command, like so, you see how all of these values are close to 0, but there's only certain ones because they were converted from signed 8-bit integers. They were divided by 127 or 128, and so they were scaled into numbers between 0 and numbers between 1 and -1. And so there were only so many of these values that get used, and that's why you see a lot of repetition in this file, a lot of the same value over and over again because they're small integers. And if we have, let's say, only 4 different values being used, then that means we're really only using 2 bits of our dynamic range. We have 8-bit samples, but the high 6 bits are always set to 0. So we're not using very much of our dynamic range. We can use more of our dynamic range when we transmit this file if we are to multiply it like we are here. And this is a way that we can amplify our signal in the digital domain before converting it to the analog domain. Now let's see what happens if we transmit this file with our flow graph with the multiply const through the HackRF. All I have to do is re-enable my Osmocom sync here, and I'll run it, connect it to the output of the multiply const. Let's launch this flow graph and see what happens. Flow graph is active, and it should be transmitting its signal very soon. There it is! It's moving the wheels. And if I leave the flow graph running, it will repeat the same thing over and over again. But I don't think I should leave it running for very long because I don't think I'm being as good a neighbor on the spectrum as I could be. One of the best ways to ensure that we're being a good neighbor on the spectrum is to verify what we're transmitting by using a receiver at the same time as we transmit. So I have a second HackRF One plugged in, and I can actually add into my flow graph an independent graph here. I'm going to make an Osmocom source, and I'll plug that into my FFT sync, or my frequency domain plot. Notice that this is isolated. It's separate from the main part of my flow graph. And I might as well turn off the time sync here. All I want to do is view over the air what was transmitted. It's going to go from the file source into this multiply const block, then out the HackRF, the first HackRF using the Osmocom sync, and then it's going to go over the air, and this independent part of the flow graph is going to tune the other HackRF to a frequency that allows it to pick up the transmission over the air and visualize it. So I do need to update this Osmocom source. It should of course have a frequency set. I could set it to 27 megahertz, but actually I think I'm going to set it to 26, and I'll show you why in a little bit. And of course I like to set the gain to 0, and maybe I'll use a little bit more IF and baseband gain. I'll set those to 24. This should work, except that I don't know if it's going to correctly select one HackRF for the sync and the other HackRF one for the source. So I'd like to go in and configure these explicitly to talk to specific devices. I'm using the HackRF info command to get information about both of the HackRF ones that I have connected to my computer. And you can see that they have separate serial numbers. I'm just going to take the last section of the first HackRF, and as long as that last section is unique compared to the last section of the other one, and that's all I need. And I'll go into my Osmocom source, or actually my Osmocom sync property, and set the device arguments field to HackRF equals serial number. That specifies that sync should use that particular HackRF one. And then I'll take the other serial number and paste that into my Osmocom source and tell this block to use explicitly the other HackRF one. There is one more thing I'd like to do before I execute this flow graph, and that's to increase the sample rate on my receiving HackRF one. I'd just like to cast a wider net and see what's going on. I'll set this to maybe sample rate times 4, which will be 8 million samples per second. And of course that means that the visible bandwidth of our frequency sync will change by 4 times as well. So I'll set those to 8 million samples per second, whereas my transmitter is only operating at 2 million samples per second. And let's execute this flow graph and see what we get. Now you can see this very distinct peak that is 1 megahertz above our center frequency, and then some other stuff happening 150 kilohertz above that. This is interesting. So we have our center spike, our DC offset, and this is basically a defect of the receiving HackRF right now. But we also see this spike 1 megahertz higher. That's actually the DC offset that was received by the HackRF, the first HackRF in the first place, and now we're retransmitting that spike. That's not very good, is it? This signal up here, 150 kilohertz higher, is actually the signal that we're intending to transmit. And then this spike 150 kilohertz below it is something that we shouldn't really be transmitting. And if we do a max hold here, you can see even more distinctly this mound. Do you see how the noise floor has a mound in the middle of it that kind of is about 2 megahertz wide? Well, that is the transmit bandwidth of our transmitting HackRF. And we've actually captured some background noise, and we're retransmitting it within that bandwidth. So not only are we transmitting this spike here that we shouldn't be, we're also transmitting a bunch of broadband noise. It's not very powerful, but it's noise that we shouldn't be transmitting if what we're interested in transmitting is this signal that's right here at 1.15 megahertz above our tuned frequency. So what can we do to be a better neighbor on the spectrum? The first thing that I would think of is to filter, and just filter out this signal of interest before we transmit it. Let's give that a try. Sometimes I like to use a low-pass filter. I'll center a frequency at 0, I'll center a signal at 0 hertz, and then use a low-pass filter. But this time, just for expediency, I'll use a band-pass filter with complex taps so that I can specify a positive frequency without also specifying its mirror image negative frequency. I'll set the low cutoff to 100 kilohertz, the high cutoff to 200 kilohertz, and the transition width to 50 kilohertz. This is maybe a bit wider than I need it, but I'll definitely grab that 150 kilohertz signal right in the middle there, in the middle of the passband. And that's what I'm interested in. So I'll connect this in between my multiply const and my Osmocom sync. And let's give this a go. Now things look a little bit cleaner. Do you see how we are in fact transmitting, if I use my max hold here, we are in fact transmitting that DC offset just a little bit, but it's very weak. And then we transmit a much stronger signal. That's the signal of interest that we're trying to transmit. And we're not transmitting that broadband noise anymore over 2 megahertz of bandwidth, although we are transmitting broadband noise over this 100 kilohertz of bandwidth right here. Even between bursts, between the intentional bursts, we are transmitting a little bit of noise. So we're definitely being a much better neighbor on the spectrum than we were, although it looks like there may be some ways that we could still be a better neighbor on the spectrum yet. One thing I noticed that we could do, just to simplify our flow graph a little bit, is that instead of multiplying by this constant here, we could just use the gain parameter in the band pass filter. And sometimes I like to do this and sometimes I don't. The reason I don't sometimes do this is because I like to keep blocks separate that have separate functions just to make them easier to read. But it would be more efficient probably if I put the gain of 6 in the bandpass filter and stopped using this multiply const block. So I'll just disable that and go straight from the file source to the bandpass filter. We should see that things look the same this way, exactly the same as they would with that separate multiply const block. Now, can you think of ways that we might be able to even be a better neighbor on the spectrum than this? One way I could think of would be to trim our capture so that we don't have a bunch of excess time between the intentional transmissions that we're looking at. Another thing would be to try to address this background noise that we have between. It happens actually during our intentional transmissions and between our intentional transmissions. And there's inherently always some background noise every time we capture something. But what is important here is the ratio between this intended transmission and the background noise, the noise that we're transmitting. And depending on the quality of our capture, that signal to noise ratio has been set at the time that we made that original capture. If we had a very weak capture, if we weren't using very much dynamic range, then we have a fairly poor signal to noise ratio, and that means when we transmit, we're going to be transmitting a higher proportion of noise than we maybe could be. But if we were to recapture our signal and do it in such a way that we use more of our dynamic range and have a better signal to noise ratio in our capture, then when we retransmit it, this noise here would be much lower in proportion to our transmitted signal. So we could be a better neighbor on the spectrum actually just by having a better capture in the first place. Of course, the very cleanest way we could possibly transmit this would be actually decoding the information that was transmitted and synthesizing our new waveform that is generated in our CPU without actually capturing any noise at all. That would be the absolute cleanest way we could accomplish this. But what we've done here is a simple capture and replay. It's not the absolute cleanest we could possibly do, but it's pretty good considering how easy it is to accomplish. Keep in mind that we didn't have to decode this signal. We didn't have to even understand what the modulation was. Even if we don't know what the modulation is, we could still capture a signal once we've identified it and then replay it and find out if that replay actually does anything. It's a pretty powerful tool to have in our toolbox, being able to replay a signal. It's useful for testing systems to see if they respond to a replayed packet, and it's also extremely useful to create as a means of creating a repeatable test vector that we can use using a HackRF One to produce a signal that then could be used to test some other system. For homework for this lesson, I'd like you to find your own toy or other simple radio device, something that is likely to be a waveform that could have some effect when replayed, and capture it yourself and do an analysis similar to the analysis that we did with the transmission for this car. I'd like you to look at things like how much dynamic range is being used, and I'd also like you to get to know the HackRF transfer utility in order to capture the waveform instead of just using GNU Radio Companion all the time. Go to greatscottgadgets.com/SDR and look for the homework assignment under Lesson 11. I hope I'll see you next time for Lesson 12.